Chapter 12, Part 1 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by Rouse. Chapter 12, The Mathematics of the Renaissance, 1450 to 1637. The last chapter is a digression from the chronological arrangement to which, as far as possible, I have throughout adhered, but I trust by references in this chapter to keep the order of events and discoveries clear. I return now to the general history of mathematics in Western Europe. Mathematicians had barely assimilated the knowledge obtained from the Arabs, including their translations of Greek writers, when the refugees who escaped from Constantinople after the fall of the Eastern Empire brought the original works and traditions of the Greek science into Italy. Thus, by the middle of the 15th century, the chief results of Greek and Arabian mathematics were accessible to European students. The invention of printing about that time rendered the dissemination of discoveries comparatively easy. It is almost a truism to remark that until printing was introduced, a writer appealed to a very limited class of readers. But we are perhaps apt to forget that when a medieval writer published a work, the results were known only to a few of his contemporaries. This had not been the case in classical times, for then and until the 4th century of our era, Alexandria was the recognized center for the reception and dissemination of new works and discoveries. In medieval Europe, on the other hand, there was no common center through which men of science could communicate with one another. And to this cause, the slow and fitful development of medieval mathematics may be partially ascribed. The introduction of printing marks the beginning of the modern world in science as in politics, for it was contemporaneous with the assimilation by the indigenous European school, which was born from scholasticism and whose history was traced in Chapter 8, of the results of the Indian and Arabian schools, whose history and influence were traced in chapters 9 and 10, and of the Greek schools, whose history was traced in chapters 2 to 5. The last 2 centuries of this period in our history, which may be described as the Renaissance, were distinguished by great mental activity in all branches of learning. The creation of a fresh group of universities, including those in Scotland, of a somewhat less complex type than the medieval universities above described, testified to the general desire for knowledge. The discovery of America in 1492 and the discussions that preceded the Reformation flooded Europe with new ideas which by the invention of printing were widely disseminated. But the advance in mathematics was at least as well marked as that in literature and that in politics. During the first part of this time, the attention of mathematicians was to a large extent concentrated on syncopated algebra and trigonometry. The treatment of these subjects is discussed in the first section of this chapter, but the relative importance of the mathematicians of this period is not very easy to determine. The middle years of the Renaissance were distinguished by the development of symbolic algebra. This is treated in the second section of this chapter. The close of the 16th century saw the creation of the science of dynamics. This forms a subject of the first section of chapter 13. About the same time and in the early years of the 17th century, considerable attention was paid to pure geometry. This forms a subject of the second section of chapter 13. The development of syncopated algebra and trigonometry. Regiomontanus. Amongst the many distinguished writers of this time, Johann Regiomontanus was the earliest and one of the most able. He was born at Königsberg on June 6, 1436, and died at Rome on July 6, 1476. His real name was Johann Müller, but following the custom of that time, he issued his publications under a Latin pseudonym, which in his case was taken from his birthplace. To his friends, his neighbors, and tradespeople he may have been Johann Muller, but the literary and scientific world knew him as Regiomontanus, just as they knew Zepernik as Copernicus and Schwarzerd as Melanchthon. It seems to me as pedantic as it is confusing to refer to an author by his actual name when he is universally recognized under another. I shall therefore in all cases as far as possible use that title only, whether Latinized or not, by which a writer is generally known. Regiomontanus studied mathematics at the University of Vienna, then one of the chief centres of mathematical studies in Europe, under Purbach, who was a professor there. His first work, done in conjunction with Purbach, consisted of an analysis of the Almagest. In this, the trigonometrical functions sine and cosine were used, and a table of natural signs were introduced. Purbach died before the book was finished, and it was finally published at Venice, but not until 1496. As soon as this was completed, Regiomontanus wrote a book on astrology, which contains some astronomical tables and a table of natural tangents. This was published in 1490. Leaving Vienna in 1462, Regiomontanus travelled for some time in Italy and Germany, and at last in 1471 settled for a few years at Nuremberg, where he established an observatory, opened a printing press, and probably lectured. 3 tracts on astronomy by him were written here. A mechanical eagle which flapped its wings and saluted the Emperor Maximilian I on his entry into the city bears witness to his mechanical ingenuity and was reckoned among the marvels of the age. Thence Regiomontanus moved to Rome to an invitation from Sixtus IV, who wished him to reform the calendar. He was assassinated shortly after his arrival at the age of 40. Regiomontanus was among the first to take advantage of the recovery of the original texts of the Greek mathematical works in order to make himself acquainted with the methods of reasoning and the results there used. The earliest notice in modern Europe of the algebra of Diophantus is a remark of his that he had seen a copy of it at the Vatican. He was also well read in the works of the Arab mathematicians. The fruit of this study was shewn in De Trianguli, written in 1464. This is the earliest modern systematic exposition on trigonometry, plane as spherical, though the only trigonometrical functions introduced are those of the sine and cosine. It is divided into 5 books. The first 4 are given up to plane trigonometry, and in particular to determining triangles from the 3 given conditions. The 5th book is devoted to spherical trigonometry. The work was printed in 5 volumes at Nuremberg in 1533, nearly a century after the death of Regiomontanus. As an example of the mathematics of this time, I quote one of his propositions at length. It is required to determine a triangle when the difference of the 2 sides, the perpendicular on the base, and the difference between the segments into which the base is thus divided are given. Book 2, proposition 23. The following is the solution given by Regiomontanus. Sit talis triangulus ABG, cujus duo latera AB et AG differentia habeant nota HG, ductaque perpendiculari AD duorum casium BD et DG differentia set EG. Hae duae differentiae sint datae et ipsa perpendicularis AD data. Digo quod omnia latera trianguli nota clagudentur. Per artem res sensus hoc problema absolvimus. Deter ergo differentia laterum ut 3, differentia casium duodecim, et perpendicularis 10. Pono probassi unum rem e pro aggregato laterum 4 res, ne proportio basis ad congerium laterum et un HG ad GE silicet unius ad 4. Eret ergo BD dimediere minus 6, sed AB eret duo resdemptis dimedie 3.
Duco A, B and C producontur quattro census et duo quadrantum demptis sex rebus. Item BD incet faci quarte census et trigantia sex minus sex rebus, huic ado quadrantum de decem qui est centum. Colliguntur quartae census et centum trigintia sex minus sex rebus, aequalis videlicet quattor censibus et duo quartae demptus sex rebus. Restaurando itaque defectus et offerendo utrobique equalia. Quimad modum ars ipse percipit, habimus census aliquat aequalis numero. Unde cognitio re patibit, et inda tria latera trianguli mores suo inutescet. To explain the language of the proof, I should add that Regiomontanus always called the unknown quantity res, and its square census or zensus. But though he uses these technical terms, he writes the words in full. He commences by saying that he will solve the problem by means of a quadratic equation per artem re et census, and that he will suppose that the difference of the sides of the triangle to be 3, the difference of the segments of the base to be 12, and the altitude of the triangle to be 10. He then takes for his unknown quantity unum rem or x, the basis of the triangle. Therefore the sum of the sides will be 4 times x. Therefore BD will be equal to half x minus 6, dimidi re minus 6, and AB will be equal to 2x minus 3 halves, duo res demptis dimidia 3. Hence AB squared, AB in C, will be 4x squared plus 2 1/4 minus 6x. Quarto census et duo et quarte demptus sex rebus, and BD squared will be 1/4 x squared plus 36 minus 6x. To BD squared he adds AD squared, quadrantum de decem, which is 100, and states that the sum of these two are equal to AB squared. This, he says, will give the value of x squared, census, whence a knowledge of x, cognitio rei, can be obtained, and the triangle determined. To express this in the language of modern algebra, we have AG squared minus DG squared equals AB squared minus DB squared. Therefore, AG squared minus AB squared equals DG squared minus DB squared. But by the given numerical conditions, AG minus AB equals 3 equals 1/4 of the quantity DG minus DB. Therefore, AG plus AB equals 4 multiplied by the quantity DG plus DB, which equals 4x. Therefore, AB equals 2x minus 3 halves, and BD equals half x minus 6. Hence, the quantity 2x minus 3 halves all squared equals the quantity half x minus 6 all squared plus 100, from which x can be found and all the elements of the triangle determined. It is worth noticing that Regiomontanus merely aimed at giving a general method, and the numbers are not chosen with any special reference to the particular problem. Thus in his diagram he does not attempt to make GE anything like 4 times as long as GH, and since x is ultimately found to be equal to 1/3 of the square root of 321, the point D really falls outside the base. The order of the letters ABG used to denote the triangle is of course derived from the Greek alphabet. Some of the solutions which he gives are unnecessarily complicated, but it must be remembered that algebra and trigonometry were still only in the rhetorical stage of development, and when every step of the argument is expressed in words at full length, it is by no means easy to realize all that is contained in a formula. It will be observed from the above example that Regiomontanus did not hesitate to apply algebra to the solution of geometrical problems. Another illustration of this is to be found in his discussions of a question which appears in Brahmagupta's Siddhanta. The problem was to construct a quadrilateral having its sides of given lengths which should be inscribable in a circle. The solution given by Regiomontanus was effected by means of algebra and trigonometry. This was published by C.G. von Meur in Nuremberg in 1786. The Algorithmus Demonstratus of Jordanus, which was first printed in 1534, was until recently universally attributed to Regiomontanus. This work, which is concerned with algebra and arithmetic, was known to Regiomontanus, and it is possible that the text which has come down to us contains additional matter contributed by him. Regiomontanus was the most prominent mathematician of his generation, and I have dealt with his works in some detail as typical of the most advanced mathematics of the time. Of his contemporaries I shall do little more than mention the names of a few of those who are best known. None were quite of the first rank, and I should sacrifice the proportion of the parts of the subject were I to devote much space to them. Purbach. I may begin by mentioning George Purbach, first the tutor, then the friend of Regiomontanus, born near Linz on May 14, 1423, and died at Vienna on April 8, 1461, who wrote a work on planetary motions which was published in 1460, an arithmetic published in 1511, a table of eclipses published in 1514, and a table of natural signs published in 1541. Cusa. Next I may mention Nicholas von Cusa, who was born in 1401 and died in 1464. Although the son of a poor fisherman and without influence, he rose rapidly in the church, and in spite of being a reformer before the Reformation, became a cardinal. His mathematical writings deal with the reform of the calendar and the quadrature of the circle. He argued in favour of the diurnal rotation of the earth. Chouquet. I may also here notice a small treatise on arithmetic known as Le Tripartite by Nicolas Chouquet, a Bachelor of Medicine in the University of Paris, which was written in 1484. This work indicates that the extent of mathematics then taught was somewhat greater than was generally believed a few years ago. It contains the earliest known use of the radical sign with indices to mark the root taken, 2 for a square root, 3 for a cube root, and so on, and also a definite statement on the rules of signs. The words plus and minus are denoted by the contraction P with a bar over it and M with a bar over it. The work is in French. Introduction of the signs plus and minus. In England and Germany, algorists were less fettered by precedent and tradition than in Italy, and introduced some improvements in notation which were hardly likely to occur to an Italian. Of these the most prominent were the introduction of the current symbols for addition, subtraction, and equality. The earliest instances of the use of the signs plus and minus, of which we have any knowledge, occur in the 15th century. Johannes Widmann of Eger, born about 1460, matriculated at Leipzig in 1480, and probably by profession a physician, wrote Mercantile Arithmetic, published at Leipzig in 1489. In this book these signs are used, not however as symbols of operation, but apparently merely as marks signifying excess or deficiency. The corresponding use of the word surplus or overplus is still retained in commerce. It is noticeable that the signs generally occur only in practical mercantile questions. Hence it has been conjectured that they were originally warehouse marks. Some kinds of goods were sold in a sort of wooden chest called a ladle, which when full was apparently expected to weigh roughly either 3 or 4 centners. If one of these cases were a little higher, say 5 pounds, than 4 centners, Widmann describes it as 4c minus 5 pounds. If it were 5 pounds heavier than the normal weight, it is described as 4c plus 5 pounds, and there are some slight reasons for thinking that these marks were chalked on the chests as they came into the warehouses. The symbols are used as if they would be familiar to his readers. It will be observed that the vertical line in the symbol for excess printed above is somewhat shorter than the horizontal line. This is also the case with Stifel and most of the early writers who used the symbol. Some presses continued to print it in this, its earliest form, till the end of the 17th century. Xylander, on the other hand, in 1575 has the vertical bar much longer than the horizontal line, and the symbol is something like plus. We infer that the more usual case was for a chest to weigh a little less than its reputed weight, and as the sign minus placed between the two numbers was a common symbol to signify some connection between them, that seems to have been taken as the standard case, while the vertical bar was originally a small mark superadded on the sign minus to distinguish the two symbols. I am far from saying that this account of the origin of our symbols plus and minus is established beyond doubt, but it is the most plausible that has yet been advanced. Another suggested derivation is that plus is a contraction of p, the initial letter in the Old German of plus, while minus is the limiting form of m for minus written rapidly. De Morgan proposed yet another derivation. The Hindus sometimes used a dot to indicate subtraction, and this dot might be thought to have been elongated into a bar, and thus give the sign for minus, while the origin of the sign for plus was derived from it by a superadded bar as explained above. But I take it that at a later time he abandoned this theory for what has been called the warehouse explanation. Another conjecture, ingenious but unsupported by any evidence, is that the symbol for plus is derived from the Latin abbreviation ampersand for et, while that for minus is obtained from the bar from which it is often written over the contracted form of a word to signify that certain letters have been left out. I should perhaps here add that till the close of the 16th century the sign plus connecting two quantities like a and b was also used in the sense that if a were taken as the answer to some question, one of the given conditions would be too little by b. This was a relation which constantly occurred in the solutions of questions by the rule of false assumption. Lastly, I would repeat again that these signs in Widman are only abbreviations and not symbols of operation. He attached little or no importance to them, and no doubt would have been amazed if he had been told that their introduction was preparing the way for a revolution of the processes used in algebra. The Algorithmus of Jordanus was not published until 1534. Widman's work was hardly known outside Germany, and it is to Pacioli that we owe the introduction into general use of syncopated algebra, that is, the use of abbreviations for certain of the more common algebraical quantities and operations, but where in using them the rules of syntax are observed. Pacioli. Lucas Pacioli, sometimes known as Lucas di Burgio, and sometimes but more rarely as Lucas Paciolus, was born in Burgo in Tuscany about the middle of the 15th century. We know little of his life except that he was a Franciscan friar and that he lectured in mathematics at Rome, Pisa, Venice, and Milan, and that at the last named city he was the first occupant of a chair of mathematics founded by Sforza. He died at Florence about the year 1510. His chief work was printed at Venice in 1494 and is termed Summa di Arithmetica Geometrica Proporzioni e Proporzionalità. It consists of two parts, first dealing with arithmetic and algebra, the second with geometry. This was the earliest printed book on arithmetic and algebra. It is mainly based on the writings of Leonardo of Pisa, and its importance in the history of mathematics is largely due to its wide circulation. In arithmetic, Pacioli gives rules for the four simple processes and a method for extracting square roots. He deals pretty fully with all questions connected with mercantile arithmetic, in which he works out numerous examples, and in particular discusses at great length bills of exchange and the theory of bookkeeping by double entry. This part was the first systematic exposition of algoristic arithmetic and has already been alluded to in chapter 11. It and similar work by Tartaglia are the two standard authorities on the subject. Most of the problems are solved by the method of false assumption, but there are several numerical mistakes. The following example will serve as an illustration of the kind of arithmetical problems discussed. I buy for 1,440 ducats at Venice 2,400 sugar loaves, whose net weight is 7,200 lire. I pay as a fee to the agent 2%, to the weighers and porters on the whole 2 ducats. I afterwards spend in boxes, cords, canvas, and in fees to the ordinary packers in the whole 8 ducats. For the tax or octroi duty on the first amount 1 ducat per cent. Afterwards for duty and tax at the office of exports 3 ducats per cent. For writing directions on the boxes and booking their passage 1 ducat. For the bark on Rimini 13 ducats. In compliments to the captains and in drink for the crews of armed barks on several occasions 2 ducats. In expenses for provisions for myself and servant for 1 month 6 ducats. For expenses for several short journeys overland here and there, for barbers, for washing of linen, and of boots for myself and servant 1 ducat. Upon my arrival in Rimini I pay to the captain of the port for port dues in the money of that city 3 lire. For porters, disembarkation on land, and carriage to the magazine 5 lire. As tax upon entrance 4 soldi a load, which are in number 32, such being the custom. For booth at the fair 4 soldi per load. I further find that the measures used at the fair are different to those used at Venice, and that 140 lire of weight are there equivalent to 100 at Venice, and that 4 lire of their silver coinage are equal to a ducat of gold. I ask therefore at how much must I sell 100 lire in Rimini in order that I may gain 10% upon my whole adventure, and what is the sum which I must receive in Venetian money. In the algebra he finds expressions for the sum of the squares and the sum of the cubes of the first n natural numbers. The larger part of this book is taken up with simple and quadratic equations and problems on numbers which lead to such equations. He mentions the Arabic classification of cubic equations, but adds that their solution appears to be as impossible as the quadrature of the circle. The following is the rule he gives for solving a quadratic equation of the form x squared plus x equals a. It is rhetorical and not syncopated, and will serve to illustrate the inconvenience of that method. Si res e census numero coi quantur, a rebus dimidius sumpto censum producere debus. Adereque numero cudius a redice totiens tol semis rerum, census latusque redibit. He confines his attention to the positive roots of equations. Though much of the matter described above is taken from Leonardo's Liber Abaci, yet the notation in which it is expressed is superior to that of Leonardo. Pacioli follows the Arabs in calling the unknown quantity the thing, in Italian cosa. Hence algebra was sometimes known as the Cossack art, or in Latin res, and sometimes denotes it by co or r or rj. He calls the square of it census or zensus, and sometimes denotes it by ce ce or z. Similarly the cube of it, or cuba, is sometimes represented by q cu or c. The fourth power, or censo di censo, is written either at length or as ce di ce ce space di space ce, or as cece. It may be noticed that all his equations are numerical, so that he did not rise to the conception of representing known quantities by letters as Jordanus has done and as is the case in modern algebra. But M. Libri gives two instances in which in a proportion he represents a number by a letter. He indicates addition and equality by the initial letters of the word plus and equalis, but he generally evades the introduction of a symbol for minus by writing his quantities on that side of the equation which makes them positive, though in a few places he denotes it by m with a bar over it for minus, or by de for demptus. This is a commencement of syncopated algebra. There is nothing striking in the results he arrives at in the second or geometrical part of the work, nor in two other tracts on geometry which he wrote, in which were printed at Venice in 1508 and 1509. It may be noticed, however, that like Regiomontanus he applies algebra to aid him in investigating the geometrical properties of figures. The following is a problem which will illustrate the kind of geometrical questions he attacked. The radius of the inscribed circle of a triangle is 4 inches, and the segments into which one side is divided by the point of contact are 6 inches and 8 inches respectively. Determine the other sides. To solve this, it is sufficient to remark that RS equals the triangle, which equals the square root of s times the quantity s minus a times the quantity s minus b times the quantity s minus c, which gives 4s equals the square root of s times the quantity s minus 14 times 6 times 8, all under the square root. Hence s equals 21. Therefore the required sides are 21 minus 6 and 21 minus 8, that is 15 and 13. But Pacioli makes no use of these formulae with which he was acquainted, but gives an elaborate geometrical construction and then uses algebra to find the lengths of the various segments of the lines he wants. The work is too long for me to reproduce here, but the following analysis of it will afford sufficient materials for its reproduction. Let ABC be the triangle, DEF be the points of contact with the sides, and O the center of the given circle. Let H be the point of intersection of OB and DF, and K that of OC and DE. Let L and M be the feet of the perpendiculars drawn from E and F on BC. Draw EP parallel to AB and cutting BC in P. Then Pacioli determines in succession the magnitudes of the following lines: OB, OC, FD, FH, ED, and EK. He then forms a quadratic equation from the solution of which he obtains the values MB and MD. Similarly, he finds the values LC and LD. He now finds in succession the values of EL, FM, EP, and LP, and then by similar triangles obtains the value of AB, which is 13. This proof was, even 60 years later, quoted by Cardan as incomparably simple and excellent, and the very crown of mathematics. I cite it as an illustration of the involved and inelegant methods then current. The problems enunciated are very similar to those in the De Triangulis of Regiomontanus. Leonardo da Vinci. The fame of Leonardo da Vinci as an artist has overshadowed his claim to consideration as mathematician, but he may be said to have prepared the way for a more accurate conception of mechanics and physics, while his reputation and influence drew some attention to the subject. He was an intimate friend of Pacioli. Leonardo was the illegitimate son of a lawyer of Vinci in Tuscany, was born in 1452, and died in France in 1519 while on a visit to Francis I. Several manuscripts by him were seized by the French revolutionary armies at the end of the last century, and Venturi, at the request of the Institute, reported on those concerned with physical or mathematical subjects.
Leaving out of account Leonardo's numerous and important artistic works, his mathematical writings are concerned chiefly with mechanics, hydraulics, and optics, his conclusions being usually based on experiments. His treatment of hydraulics and optics involves but little mathematics. The mechanics contain numerous and serious errors. The best portions are those dealing with the equilibrium of a lever under any forces, the laws of friction, the stability of a body as affected by the position of its center of gravity, the strength of beams, and the orbit of a particle under a central force. He also treated a few easy problems by virtual moments. A knowledge of the triangle of forces is occasionally attributed to him, but I think it is most probable that his views on the subject were somewhat indefinite. Generally, one may say that all his mathematical work is unfinished and consists largely of suggestions which he had not the patience to verify or discuss in detail. Dürer. Albrecht Dürer was another artist of the same time who was also known as a mathematician. He was born at Nuremberg in May 21st, 1471, and died there on April 6, 1528. His chief mathematical work was issued in 1525 and contains a discussion of perspective and some geometry and certain graphical solutions. Latin translations of it were issued in 1532, 1555, and 1605. Copernicus. An account of Nicholas Copernicus, born at Thorn on February 19, 1473, and died at Frauenburg on May 7, 1543, and his conjecture that the earth and planets all revolved around the sun belong to astronomy rather than to mathematics. I may, however, add that Copernicus wrote a short textbook on trigonometry, published at Wittenberg in 1542, which is clear, though it contains nothing new. It is evident from this and his astronomy that he was well read in the literature of mathematics, and was himself a mathematician of considerable power. I describe his statement as to the motion of the earth as a conjecture because he advocated it only on the ground that it gave a simple explanation of natural phenomenon. Galileo in 1632 was the first to try to supply anything like a proof of this hypothesis. By the beginning of the 16th century, the printing press began to be active, and many of the works of the earlier mathematicians became now for the first time accessible to all students. This stimulated inquiry, and before the middle of the century numerous works were issued, which, though they did not include any great discoveries, introduced a variety of small improvements, all tending to make algebra more analytical. Record. The sign now used to denote equality was introduced by Robert Record. Record was born at Tenby in Pembrokeshire about 1510 and died at London in 1558. He entered at Oxford and obtained a fellowship at All Souls College in 1531. Thence he migrated to Cambridge, where he took a degree in medicine in 1545. He then returned to Oxford and then lectured there, but finally settled in London and became physician to Edward VI and to Mary. His prosperity must have been short-lived, for at the time of his death he was confined to the King's Bench prison for debt. In 1540 he published an arithmetic termed the Ground of Arts, in which he employed the signs plus for plus and minus for minus, plus sign which betokeneth too much, as this line minus plain without a cross line betokeneth too little. And there are faint traces of his having used these signs as symbols of operation and not as mere abbreviations. In this book the equality of two ratios is indicated by two equal and parallel lines whose opposite ends are joined diagonally, for example a greater than or equal to sign. A few years later, in 1557, he wrote an algebra under the title Whetstone of Wit. This is interesting as it contains the earliest introduction of the sign equals for equality, and he says he selected that particular symbol because then two parallel straight lines, no two things can be more equal. M. Charles Henry has however pointed out that this sign is a not uncommon abbreviation for the word est in medieval manuscripts, and this would seem to indicate a more probable origin. In this work, records showed how the square root of an algebraical expression could be extracted. He also wrote on astronomy. These works give a clear view of the knowledge of the time. Rudolf Riese. About the same time in Germany, Rudolf and Riese took up the subjects of algebra and arithmetic. Their investigations formed the basis of Stifel's well-known work. Christoph Rudolf published his algebra in 1525. It is entitled Die Cross, and it is founded on the writings of Pacioli and perhaps of Jordanus. Rudolf introduced the sign of surd for the square root, the symbol being the corruption of the initial letter of the word radix, and similarly 3 surds denoted a cube root and 2 surds denoted a fourth root. Adam Riese was born near Bamberg, Bavaria in 1489 of humble parentage, and after working for some years as a miner, set up a school. He died at Annaberg on March 30th, 1559. He wrote a treatise on practical geometry, but his most important book was his well-known Arithmetic, which may be described as algebraical, issued in 1536 and founded on Pacioli's work. Riese used the symbols plus and minus. End of section 16. Recording by Paul King, pjk.scripts.mit.edu/pkj. Chapter 12, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. Rouse. Chapter 12, Part 2. The Mathematics of the Renaissance, 1450 to 1637. Part 2. Stifel. The methods used by Rudolf and Riese and their results were brought into general notice through Stifel's work, which had wide circulation in Germany. Michael Stifel, sometimes known by the Latin name of Stifelius, was born at Essling in 1486 and died at Jena in April 19th, 1567. He was originally an Augustine monk, but he accepted the doctrines of Luther, of whom he was a personal friend. He tells us in his algebra that his conversion was finally determined by noticing that Pope Leo X was the beast mentioned in the Revelation. To shew this, it was only necessary to add up the numbers represented by the letters in Leo Decimus. The M had to be rejected since it clearly stood for mysterium, and the result amounts to exactly 10 less than 666, 666, thus distinctly implying that it was Leo X. Luther accepted his conversion, but frankly told him that he had better clear his mind of any nonsense about the number of the beast. Unluckily for himself, Stifel did not act on this advice. Believing that he had discovered the true way of interpreting the biblical prophecies, he announced that the world would come to an end on October 3rd, 1533. The peasants of Holzdorf, of which place he was pastor, knowing of the scientific reputation, accepted his assurance on this point.
Some gave themselves up to religious exercises, others wasted their goods in dissipation, but all abandoned their work. When the day foretold had passed, many of the peasants found themselves ruined. Furious at having been deceived, they seized the unfortunate prophet, and he was lucky in finding a refuge in the prison at Wittenberg, from which he was after some time released by the personal intercession of Luther. Stiefel wrote a small treatise on algebra, but his chief mathematical work is his Arithmetica Integra, published at Nuremberg in 1544, with a preface by Melanchthon. The first two books of the Arithmetica Integra deal with surds and incommensurables, and are Euclidean in form. The third book is on algebra, and is noticeable for having called general attention to the German practice of using the signs plus and minus to denote addition and subtraction. There are faint traces of these signs being occasionally employed by Stiefel as symbols of operation and not only as abbreviations. This application of them was apparently new. He not only employed the usual abbreviation for the Italian words which represent the unknown quantity and its powers, but in at least one case where there was several unknown quantities he represented them respectively by the letters A, B, C, and so on, thus reintroducing the general algebraic notation which had fallen into disuse since the time of Jordanus. It used to be said that Stiefel was the real inventor of logarithms, but it is now certain that this opinion was due to a misapprehension of a passage in which he compares the geometrical and arithmetical progressions. Tartaglia. Niccolo Fontana, generally known as Nicholas Tartaglia, that is, Nicholas the Stammerer, was born at Brescia in 1500 and died in Venice in December 14, 1557. After the capture of the town by the French in 1512, most of the inhabitants took refuge in the cathedral, and were then massacred by the soldiers. His father, who was a postal messenger at Brescia, was amongst the killed. The boy himself had his skull split through in 3 places, while both his jaws and his palate were cut open. He was left for dead, but his mother got into the cathedral, and finding him still alive managed to carry him off. Deprived of all resources, she recollected that dogs when wounded always lick the injured place, and to that remedy he attributed his ultimate recovery, but the injury to his palate produced an impediment in his speech, from which he received his nickname. His mother managed to get sufficient money to pay for his attendance at school for 15 days, and he took advantage of it to steal a copybook, from which he subsequently taught himself how to read and write. But so poor were they that he tells us that he could not afford to buy paper, and was thus obliged to make use of the tombstones as slates on which to work his exercises. He commenced his public life by lecturing at Verona, but he was appointed at some time before 1535 to a chair of mathematics at Venice, where he was living when he became famous, through his acceptance of a challenge from a certain Antonio de Fiori or Florido. Fiori had learnt from his master, one Scipione Ferreo, who died at Bologna in 1526, an empirical solution of a cubic equation of the form x cubed plus qx equals r. This solution was previously unknown in Europe, and it is probable that Ferreo had found the result in an Arab work. Tartaglia, in answer to a request from Colla in 1530, stated that he could effect a solution of a numerical equation of the form x cubed plus px squared equals r. Fiori, believing that Tartaglia was an impostor, challenged him to a contest. According to this challenge, each of them was to deposit a certain stake with the notary, and whoever could solve the most problems out of a collection of 30 propounded by the other was to get the stakes, 30 days being allowed for the solution of the questions proposed. Tartaglia was aware that his adversary was acquainted with the solution of a cubic equation of some
particular form, and suspecting that the questions proposed to him would all depend on the solution of such a cubic equation, set himself the problem to find a general solution, and certainly discovered how to obtain a solution of some if not all cubic equations. His solution is believed to have depended on a geometrical construction, but led to a formula which is often but unjustly described as Cardan's. When the contest took place, all the questions proposed to Tartaglia were, as he had suspected, reducible to the solution of a cubic equation, and he succeeded within 2 hours in bringing them to a particular cases of the equation x cubed plus qx equals r, of which he knew the solution. His opponent failed to solve any of the problems proposed to him, which as a matter of fact were all reducible to numerical equations of the form x cubed plus px squared equals r. Tartaglia was therefore the conqueror. He subsequently composed some verses commemorative of his victory. The chief works of Tartaglia are as follows. His Nova Scienza, published in 1537. In this he investigated the fall of bodies under gravity, and he determined the range of a projectile, stating that it was a maximum when the angle of projection was 45 degrees. But this seems to have been a lucky guess. 2. An Arithmetic, published in 2 parts in 1556. 3. A Treatise on Numbers, published in 4 parts in 1560. And sometimes treated as a continuation of the arithmetic. In this he shewed how the coefficients of x in the expansion of 1 plus x to the power n could be calculated from those in the expansion of 1 plus x quantity to the power of n minus 1 for the cases where n is equal to 2, 3, 4, 5, or 6. It is possible that he also wrote a treatise on algebra and the solution of cubic equations, but if so, no copy is now extant. The other works were collected into a single edition and republished at Venice in 1606. The treatise on arithmetic and numbers is one of the chief authorities for our knowledge of the early Italian algorism. It is verbose, but gives a clear account of the different arithmetical methods then in use, and he has numerous historical notes which, as far as we can judge, are reliable, and are the authorities for many of the statements in the last chapter. It contains an immense number of questions on every kind of problem which would be likely to occur in mercantile arithmetic, and there are several attempts to frame algebraical formulae suitable for particular problems. These problems give incidentally a good deal of information as to the ordinary life and commercial customs of the time. Thus we find that the interest demanded on first-class security in Venice ranged from 5 to 12% a year, while the interest on commercial transactions ranged from 20% a year upwards. Tartaglia illustrates the evil effects of the law forbidding usury by the manner in which it was evaded in farming. Farmers who were in debt were forced by their creditors to sell all their crops immediately after the harvest, the market being thus glutted. The price obtained was very low, and the moneylenders purchased the corn in the open market at an extremely cheap rate. The farmers then had to borrow their seed corn on condition that they replaced an equal quantity, or paid the then price of it, in the month of May when corn was dearest. Again, Tartaglia, who had been asked by the magistrates at Verona to frame for them a sliding scale by which the price of bread would be fixed by that of corn, enters into a discussion on the principles which it was then supposed should regulate it. In another place he gives the rules at that time current for preparing medicines. Pacioli had given in his arithmetic some problems of an amusing character, and Tartaglia imitated him by inserting a large collection of mathematical puzzles. He half apologizes for introducing them by saying that it was not uncommon at dessert to propose arithmetical questions to the company by way of amusement, and he therefore adds some suitable problems. He gives several questions on how to guess a number thought of by one of the company, or the relationships caused by the marriage of relatives, or difficulties arising from inconsistent bequests. Other puzzles are such as the following. There are three men, young, handsome, and gallant, who have three beautiful ladies for wives. All are jealous, as well as the husbands of the wives, as the wives of the husbands. They find on the bank of a river over which they have to pass a small boat which can hold no more than two persons. How can they pass so as to give rise to no jealousy? A ship carrying as passengers 15 Turks and 15 Christians encounters a storm, and the pilot declares that in order to save the ship and crew, one half of the passengers must be thrown into the sea. To choose the victims, the passengers are placed in a circle, and it is agreed that every ninth man shall be cast overboard, reckoning from a certain point. In what manner must they be arranged so that the lot may fall exclusively upon the Turks? Three men robbed a gentleman of a vase containing 24 ounces of balsam. Whilst running away they met in a wood with a glass seller, of whom in a great hurry they purchased 3 vessels. On reaching a place of safety they wish to divide the booty, but they find that their vessels contain 5, 11, and 13 ounces respectively. How can they divide the balsam into equal portions? These problems, some of which are of Oriental origin, form the basis of the collections of mathematical recreations by Bachet de Meziriac, Ozanam, and Montucla. Cardan. The life of Tartaglia was embittered by a quarrel with his contemporary Cardan, who, having under a pledge of secrecy obtained Tartaglia's solution of a cubic equation, and published it. Girolamo Cardan was born at Pavia on September 24, 1501, and died at Rome on September 21, 1576. His career is an account of the most extraordinary and inconsistent acts. A gambler, if not a murderer, he was also the ardent student of science, solving problems which had long baffled all investigation. At one time of his life he was devoted to intrigues which were a scandal even in the 16th century. At another he did nothing but rave on astrology, and yet at another he declared that philosophy was the only subject worthy of man's attention. His was the genius that was closely allied to madness. He was the illegitimate son of a lawyer of Milan, and was educated at the universities of Pavia and Padua. After taking his degree he commenced the life of a doctor, and practised his profession at Sacco and Milan from 1524 to 1550. It was during this period that he studied mathematics and published his chief works. After spending a year or so in France, Scotland, and England, he returned to Milan as a professor of science, and shortly afterwards was elected to a chair at Pavia. Here he divided his time between debauchery, astrology, and mechanics. His 2 sons were as wicked and passionate as himself. The elder was in 1560 executed for poisoning his wife, and about the same time Cardan in a fit of rage cut off the ears of the younger who had committed some offence. For this scandalous outrage he suffered no punishment, as the Pope Gregory XIII took him under his protection. In 1562 Cardan moved to Bologna, but the scandals connected with his name were so great that the university took steps to prevent his lecturing, and only gave way under pressure from Rome. In 1570 he was imprisoned for heresy on account of his having published the horoscope of Christ, and when released he found himself so generally detested that he determined to resign his chair. At any rate, he left Bologna in 1571, and shortly afterwards moved to Rome. Cardan was the most distinguished astrologer of his time, and when he settled at Rome he received a pension in order to secure his services as astrologer to the papal court. This proved fatal to him, for, having foretold that he should die on a particular day, he felt obliged to commit suicide in order to keep up his reputation, or so at least the story runs. The chief mathematical work of Cardan is the Ars Magna, published at Nuremberg in 1545. Cardan was much interested in the contest between Tartaglia and Fiori, and as he had already begun writing this book he asked Tartaglia to communicate his method of solving a cubic equation. Tartaglia refused, whereupon Cardan abused him in the most violent terms, but shortly afterwards wrote saying that a certain Italian nobleman had heard of Tartaglia's fame and was most anxious to meet him, and begged him to come to Milan at once. Tartaglia came, and though he found no nobleman awaiting him at the end of his journey, he yielded to Cardan's importunity and gave him the rule he wanted. Cardan on his side, taking a solemn oath that he would never reveal it, and would not even commit it to writing in such a way that after his death anyone could understand it. The rule is given in some doggerel verses which are still extant. Cardan asserts that he was given merely the result, and that he obtained the proof himself, but this is doubtful. He seems to have at once taught the method, and one of his pupils, Ferrari, reduced the equation of the fourth degree to a cubic, and so solved it. When the Ars Magna was published in 1545, the breach of faith was made manifest. Tartaglia was not unnaturally very angry, and after acrimonious controversy he sent a challenge to Cardan to take part in a mathematical duel. The preliminaries were settled, and the place of meeting was to be a certain church in Milan, but when the day arrived Cardan failed to appear, and sent Ferrari in his stead. Both sides claimed the victory, though I gather that Tartaglia was the more successful. At any rate his opponents broke up the meeting, and he was fortunate in escaping with his life. Not only did Cardan succeed in his fraud, but modern writers generally attribute the solution to him, so that Tartaglia has not even that posthumous reputation which is at least his due. The Ars Magna is a great advance on any algebra previously published. Hitherto algebraists had confined their attention to those roots of equations which were positive. Cardan discussed negative and even imaginary roots, and proved that the latter would always occur in pairs, though he declined to commit himself to any explanation as to the meaning of these sophistic quantities, which he said were ingenious though useless. Most of his analysis of cubic equations seemed to have been original. He shewed that if the three roots were real, Tartaglia's solution gave them in a form which involved imaginary quantities. Except for the somewhat similar researches of Bombelli a few years later, see below, page 231, that the theory of imaginary quantities received little further attention from mathematicians until Euler took the matter up after the lapse of nearly 2 centuries. Gauss first put the subject on a systematic and scientific basis, introduced the notation of complex variables, and used the symbol I to denote the square root of -1. The modern theory is chiefly based on his researches. Cardan found the relations connecting the roots with the coefficients of an equation. He was also aware of the principle that underlies Descartes' rule of signs. But as he followed the then general custom of writing his equations as the equality of two expressions, in each of which all the terms were positive, he was unable to express the rule concisely. He gave a method of approximating to the root of a numerical equation founded on the fact that if a function has opposite signs when two numbers are substituted on it, the equation obtained by equating the functions to 0 will have a root between those two numbers. Cardan's solution of a quadratic equation is geometrical and substantially the same as that given by Al-Khwarizmi. His solution of a cubic equation is also geometrical and may be illustrated by the following case, which he gives in chapter 11. To solve the equation x squared plus 6x equals 20, or any equation of the form x squared plus qx equals r, take two cubes such that the rectangle under their respective edges is 2 or 1/3 q, and the difference of their volumes is 20 or r. The x will be equal to the difference between the edges and the cubes. To verify this, he first gives a geometrical lemma to shew that if from a line AC a portion CB be cut off, then the cube on AB will be less than the difference between the cubes on AC and BC by 3 times the right parallelepiped whose edges are respectively equal to AC, BC, and AB. This statement is equivalent to the algebraical identity a minus b quantity cubed equals a cubed minus b cubed minus 3ab multiplied by the quantity a minus b. And the fact that x satisfies the equation is then obvious. To obtain the lengths of the edges of the two cubes, he has only to solve a quadratic equation for which the geometrical solution previously given sufficed. Like all previous mathematicians, he gives separate proofs of his rule for the different forms of equations which can fall under it. Thus he proves the rule independently for equations of the form x cubed plus px equals q, x cubed equals px plus q, x cubed plus px plus q equals 0, and x cubed plus q equals px. It will be noticed that with geometrical proofs this was almost a necessity, but he did not suspect that the resulting formulae were general. The equations he considers are numerical, but in some of his analysis he uses literal coefficients. Shortly after Cardan came a number of mathematicians who did good work in developing the subject, who are hardly of sufficient importance to require a detailed mention here. Of these, the most celebrated are perhaps Ferrari and Rheticus. Ferrari. Ludovico Ferraro, usually known as Ferrari, whose name I have already mentioned in connection with the solution of a biquadratic equation, was born at Bologna on February 2, 1522, and died on October 5, 1565. His parents were poor, and he had taken into Cardan's service as an errand boy, but was allowed to attend his master's lectures and subsequently became the most celebrated pupil. He is described as a neat, rosy little fellow, with a bland voice, a cheerful face, and an agreeable short nose, fond of pleasure, of great natural powers, but with the temper of a fiend. His manners and numerous accomplishments procured him a place in the service of the Cardinal Ferrando Gonzaga, where he managed to make a fortune. His dissipations told on his health, and he retired in 1565 to Bologna, where he began to lecture on mathematics. He was poisoned the same year either by his sister, who seems to have been the only person for whom he had any affection, or by her paramour. Such work as he produced is incorporated in Cardan's Ars Magna or Bombelli's Algebra, but nothing can be definitely assigned to him except the solution of a biquadratic equation. Colla had proposed the solution of the equation x to the fourth plus 6x squared plus 36 equals 60x as a challenge to mathematicians. This particular equation had probably been found in some Arabic work. Nothing is known about the history of this problem except that Ferrari succeeded where Tartaglia and Cardan had failed. Rheticus. Georg Joachim Rheticus, born at Feldkirch in February 15, 1514, and died at Kaschau on December 4, 1576, was professor at Wittenberg and subsequently studied under Copernicus, whose works were produced under the direction of Rheticus. Rheticus constructed the various trigonometrical tables, some of which were published by his pupil Otho in 1596. These were subsequently completed and extended by Vieta and Pitiscus and are the basis of those still in use. Rheticus also found the values of sine of 2 theta and sine of 3 theta in terms of sine theta and cosine theta. I add here the names of some other celebrated mathematicians of about the same time, though their works are now of little value to any save antiquarians. Franciscus Maurolicus, born at Messina of Greek parents in 1494 and died in 1575, translated numerous Latin and Greek mathematical works and discussed the conics regarded as sections of a cone. His works were published at Venice in 1575. Jean Borel, born in 1492 and died at Grenoble in 1572, wrote an algebra founded on that of Stiefel, and a history of the quadrature of the circle. His works were published at Lyons in 1559. Wilhelm Xylander, born at Augsburg on December 26, 1532, and died on February 10, 1576 at Heidelberg, where since 1558 he had been a professor, brought out an edition of the works of Psellus in 1556, an edition of Euclid's Elements in 1562, an edition of the Arithmetic of Diophantus in 1575, and some of the minor works which were collected and published in 1577. Federigo Commendino, born at Urbino in 1509 and died there on September 3, 1575, published a translation of the works of Archimedes in 1558, selections from Apollonius and Pappus in 1566, Euclid's Elements in 1572, and selections from Aristarchus, Ptolemy, Hero, and Pappus in 1574, all being accompanied by commentaries. Jacques Peltier, born at Le Mans on July 25, 1517 and died at Paris in July 1582, wrote several textbooks on algebra and geometry. Most of the results of Stiefel and Cardan are included in the former. Adrian Romanus, born at Louvain on September 29, 1561 and died on May 4, 1625, professor of mathematics and medicine at the University of Louvain, was the first to prove the usual formula for the sine of a plus b. And lastly, Bartholomeus Pitiscus, born on August 24, 1561 and died at Heidelberg, where he was professor of mathematics on July 2, 1613, published his Trigonometry in 1599. This contains the expression for the sine of a plus b and the sine of a minus b, and also the cosine of a plus b and the cosine of a minus b in terms of the trigonometrical ratios of a and b. About this time also several books were produced which, if they did not extend the boundaries of the subject, they systematized it. In particular I may mention those of Ramus and Bombelli. Ramus. Peter Ramus was born at Cuth in Picardy in 1515 and was killed at Paris in the massacre of St. Bartholomew on August 24, 1572. He was educated at the University of Paris, and on taking his degree he astonished and charmed the university with the brilliant declamation he delivered on the thesis that everything Aristotle had taught was false. He lectured, for it will be remembered that in the early days there were no professors, first at Le Mans and afterwards at Paris, and at the latter he founded the first chair of mathematics. Besides some works on philosophy, he wrote treatises on arithmetic, algebra, geometry, founded on Euclid, astronomy, founded on the works of Copernicus, and physics, which were long regarded on the continent as the standard textbooks on these subjects. They are collected in an edition of his works published at Bâle in 1569. Bombelli. Closely following the publication of Cardan's great work, Raffaello Bombelli published in 1572 an algebra which is a systematic exposition of what was then known on the subject. In the preface he alludes to Diophantus, who, in spite of the notice of Regiomontanus, was still unknown in Europe, and traces the history of the subject. He discusses radicals, real and imaginary. He treats the theory of equations and shews that in the irreducible case of a cubic equation the roots are all real, and he remarks that the problem to trisect a given angle is the same as that of the solution of the cubic equation. Finally, he gave a large collection of problems. Bombelli is chiefly distinguished in connection with the improvement of the notation of algebra which he introduced. The symbols then ordinarily used for the unknown quantity and its powers were letters which stood for the abbreviations of these words. Those most frequently adopted were R or Rj for radix or res x, Z or C for zensus or census x squared, C or K for cubus x cubed, etc. Thus x squared plus 5x minus 4 would have been written
1ZP period 5RM period 4, where P stands for plus and M stands for minus. Xylander, in his edition of the Arithmetic of Diophantus in 1575, used other letters, and the symbols plus and minus would have been written in the above expressions thus: 1q plus 5n minus 4. A similar notation was sometimes used by Vieta and even by Fermat. The advance made by Bombelli was that he introduced a symbol like a semicircle holding a 1 above it, which I'll just call cup 1 for the unknown quantity, and cup 2 for its square, and cup 3 for its cubed, and so on, and therefore he wrote x squared plus 5x minus 4 as 1 cup 2 p period 5 cup 1 m period 4. Stevenius in 1586 employed 1 in a circle, 2 in a circle, and 3 inside a circle in a similar way, which I'll call circle 1, circle 2, circle 3, and suggested, though he did not use a corresponding notation for fractional indices, he would have written the above expression as 1 circle 2 plus 5 circle 1 minus 4 circle 0. But whether the symbols were more or less convenient, they were still only abbreviations for words, and were subject to all the rules of syntax. They merely afforded a sort of shorthand which the various steps and results could be expressed concisely. The next advance was the creation of symbolic algebra, and the chief credit of that is due to Vieta. The development of symbolic algebra. We have now reached a point beyond which any considerable development of algebra, so long as it was strictly syncopated, could hardly proceed. It is evident that Stifel and Bombelli and other writers of the 16th century had introduced, or were on the point of introducing, some of the ideas of symbolic algebra. But so far as the credit of inventing symbolic algebra can be put down to any one man, we may perhaps assign it to Vieta, while we may say that Harriot and Descartes did more than any other writers to bring it into the general use. It must be remembered, however, that it took time before all these innovations became generally known, and they were not familiar to the mathematicians until the lapse of some years after they had been published. End of section 17. Recording by Paul King. pjk.scripts.mit.edu/pkj Chapter 12, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 12, Part 3. The Mathematics of the Renaissance, 1450 to 1637. Vieta. Franciscus Vieta, Francois Viete, born in 1540 at Fontenay near La Rochelle and died in Paris in 1603. He was brought up as a lawyer and practiced for some time at the Parisian bar. He then became a member of the provincial parliament in Brittany, and finally in 1580, through the influence of the Duc de Rohan, he was made Master of Requests, an office attached to the Parliament at Paris. The rest of his life was spent in the public service. He was a firm believer in the divine right of kings, and possibly a zealous Catholic. After 1580 he gave up most of his leisure to mathematics, though his great work In Artem Analyticam Isagoge, in which he explained how algebra could be applied to the solution of geometrical problems, was not published till 1591. His mathematical reputation was already considerable when one day the ambassador from the Low Countries remarked to Henry IV that France did not possess any geometricians capable of solving a problem which had been propounded in 1593 by his countryman
Adrian Romanus to all the mathematicians of the world, and which required the solution of an equation of the 45th degree. The king thereupon summoned Vieta and informed him of the challenge. Vieta saw that the equation was satisfied by a chord of a circle of unit radius, which subtends an angle 2 pi over 45 at the centre, and in a few minutes he gave back to the king two solutions of the problem written in pencil. In explanation of this feat I should add that Vieta had previously discovered how to form the equation connecting sine n theta with sine theta and cos theta. Vieta in his turn asked Romanus to give the geometrical construction to describe a circle which should touch three given circles. This was the problem which Apollonius had treated in his De Tactionibus, a lost book which Vieta at a later time conjecturally restored. Romanus solved the problem with the aid of the conic sections, but failed to do it by Euclidean geometry. Vieta gave a Euclidean solution which so impressed Romanus that he travelled to Fontenay, where the French court was then settled, to make Vieta's acquaintance, an acquaintanceship which rapidly ripened into a warm friendship. Henry was much struck with the ability shewn by Vieta in this matter. The Spaniards had at the time a cipher containing nearly 600 characters, which was periodically changed, and which they believed to be impossible to decipher. A despatch having been intercepted, the king gave it to Vieta, and asked him to try to read it and find the key to the system. Vieta succeeded, and for 2 years the French used it, greatly to their profit, in the war which was then raging. So convinced was Philip II that the cipher could not be discovered, that when he found his plans known, he complained to the Pope that the French were using sorcery against him, contrary to the practice of the Christian faith. Vieta wrote numerous works on algebra and geometry. The most important are In Artem Analyticam Isagoge, Tours 1591, the Supplementum Geometriae, and a collection of geometrical problems, Tours 1593, and the De Numerosa Potestatum Resolutione, Paris 1600. All of these were printed for private circulation only, but they were collected by F. van Schooten and published in one volume at Leyden in 1646. Vieta also wrote the De Equationum Recognitione et Emendatione, which was published after his death in 1615 by Alexander Anderson. The In Artem is the earliest work on symbolic algebra. It also introduced the use of letters for both known and unknown quantities, a notation for the powers of quantities, and enforced the advantage of working with homogeneous equations. To this an appendix called Logistes Speciosa was added on addition and multiplication of algebraical quantities and on the powers of a binomial up to the sixth. Vieta implies that he knew how to form the coefficients of these 6 expansions by means of the arithmetical triangle as Tartaglia had previously done. But Pascal was the first to give the general rule for forming it for any order, which is equivalent to saying that he could write down the coefficients of x in the expansion 1 plus x quantity to the power n if those in the expansion of 1 plus x quantity to the power n minus 1 were known. Newton was the first to give the general expression for the coefficient of x raised to the power p in the expansion of 1 plus x quantity to the power n. Another appendix known as Zetetica on the solution of equations was subsequently added to the In Artem. The In Artem is memorable for 2 improvements in algebraic notation which were introduced here, though it is probable that Vieta took the idea from both other authors. One of these improvements was that he denoted the known quantities by the consonants B, C, D, etc., and the unknown quantities by the vowels A, E, I, etc. Thus in any problem he was able to use a number of unknown quantities. In this particular point he seems to have been forestalled by Jordanus and Stifel. The present custom of using the letters at the beginning of the alphabet A, B, C to represent known quantities, and those toward the end X, Y, Z to represent the unknown quantities, was introduced by René Descartes in 1637.
The other improvement was this. To this time it had been the custom to introduce new symbols to represent the square, cube, and so on of quantities which had already occurred in the equations. Thus if r or n stood for x, z, c, or q stood for x squared, and c or k for x cubed, etc. So long as this was the case, the chief advantage of algebra was that it afforded a concise statement of results, every statement of which was reasoned out. But when Vieta used a to denote the unknown quantity x, he sometimes employed a quadratus a cubus to represent x squared and x cubed, which at once shewed the connection between the different powers. And later the successive powers of a were commonly denoted by the abbreviations aq, ac, aqq, etc. Thus Vieta would have written the equation 3ba squared minus da plus a cubed equals z as b3 in a quadratur minus d plano in a plus a cubo equatur z solido. It will be observed that the dimensions of the constants b, d, and z are chosen so as to make the equation homogeneous. This is characteristic of all his work. It will also be noticed that he does not use a sign for equality. In fact, the particular sign equals, which we use to denote equality, was employed by him to represent the difference between. Vieta's notation is not so convenient as that previously used by Bombelli and Stevinus, but it was more generally adopted. Occasional instances of an approach to index notation, such as a to the power q, are said to occur in Vieta's works. These two steps were almost essential to any further progress in algebra. In both of them Vieta had been forestalled, but it was his good luck in emphasizing their importance to be the means of making them generally known at a time when opinion was ripe for such an advance. The De Equationem Recognitione et Emendatione is mostly on the theory of equations. Vieta here shewed that the first member of an algebraical equation, phi of x equals 0, could be resolved into linear factors, and explained how the coefficients of x could be expressed as functions of the roots. He also indicated how from a given equation another could be obtained whose roots were equal to those of the original, increased by a given quantity or multiplied by a given quantity, and he used this method to get rid of the coefficients of x in a quadratic equation and of the coefficient of x squared in a cubic equation, and was thus enabled to give the general algebraic solution of both. His solution of a cubic equation is as follows. First, reduce the equation to the form x cubed plus 3a squared x equals 2b cubed. Next, let x equal a squared over y minus y, and we get y to the sixth plus 2b cubed y cubed equals a to the sixth, which is a quadratic in y cubed. Hence y can be found, and therefore x can be determined. His solution of a biquadratic is similar to that known as Ferrari's. He first got rid of the term involving x cubed, thus reducing the equation to the form x to the fourth plus a squared x squared plus b cubed x equals c to the power 4. He then took the terms involving x squared and x to the right hand side of the equation and added x squared y squared plus a quarter y to the fourth to each side, so that the equation became quantity x squared plus half y squared all squared equals x squared multiplied by the quantity y squared minus a squared, subtract b cubed x plus a quarter y to the fourth plus c to the fourth. He then chose y so that the right hand side of this equality is a perfect square. Substituting this value of y, he was able to take the square root of both sides and thus obtain two quadratic equations for x, each of which can be solved. The De Numerosa Potestatem Resolutione deals with the numerical equations. In this, a method of approximating to the values of positive roots is given, but it is prolix and of little use, though the principle, which is similar to that of Newton's rule, is correct. Negative roots are uniformly rejected. This work is hardly worthy of Vieta's reputation. Vieta's trigonometrical researches are included in various tracts which are collected in Schutten's edition. Besides some trigonometrical tables, he gave the general expression for the sine or chord of an angle in terms of the sine and cosine of its submultiples. Delambre considers this as the completion of the Arab system of trigonometry. We may take it then that from this time the results of elementary trigonometry were familiar to mathematicians. Vieta also elaborated the theory of right-angled spherical triangles. Among Vieta's miscellaneous tracts will be found a proof that each of the famous geometrical problems of the trisection of an angle and the duplication of the cube depends on the solution of a cubic equation. There are also some papers connected with an angry controversy with Clavius in 1594 on the subject of the reformed calendar, in which Vieta was not well advised. Vieta's works on geometry are good, but they contain nothing which requires mention here. He applied algebra and trigonometry to help him in investigating the properties of figures. He also, as I have already said, laid great stress on the desirability of always working with homogeneous equations, so that if a square or a cube were given, it should be denoted by expressions like a squared or b cubed, but not by terms like m or n which do not indicate the dimensions of the quantities they represent. He had a lively dispute with Scaliger on the latter publishing a solution of the quadrature of the circle, and succeeded in shewing the mistake into which his rival had fallen. He gave a solution of his own which as far as it goes is correct, and stated that the area of a square is to that of the circumscribing circle as the square root of a half times the square root of the quantity a half plus the square root of a half, multiplied by the quantity in brackets the square root of a half plus the quantity square root of a half plus the square root of a half, end of quantity, ad infinitum. This is one of the earliest attempts to find the value of pi by means of an infinite series. He was well acquainted with the extant writings of the Greek geometricians, and introduced the curious custom, which during the 17th and 18th centuries became fashionable, of restoring lost classical works. He himself produced a conjectural restoration of De Tactionibus of Apollonius. Girard. Vieta's results in trigonometry and the theory of equations were extended by Albert Girard, a Dutch mathematician who was born in Lorraine in 1590 and died in 1633. In 1626 Girard published at The Hague a short treatise on trigonometry, to which were appended tables of the values of the trigonometrical functions. This work contains the earliest use of the abbreviations sin, sin, tan, tan, and sec, sec, for sine, tangent, and secant. The supplemental triangles in a spherical trigonometry are also discussed, and seem to have been discovered by Girard independently of Vieta, and he also gave the expression for the area of the spherical triangle in terms of the spherical excess. This was discovered independently by Calivari. In 1627 Girard brought out an edition of Malraux's geometry with considerable additions. Girard's chief discoveries are contained in his Invention nouvelle en algèbre, published at Amsterdam in 1629. This contains the earliest use of brackets, a geometrical interpretation of the negative sign, the statement that the number of roots in an algebraical equation is equal to its degree, the distinct recognition of imaginary roots, and probably implies also a knowledge that the first member of an algebraical equation phi of x equals 0 could be resolved into linear factors. Girard's researches were unknown to most of his contemporaries and exercised no appreciable influence on the development of mathematics. The invention of logarithms by Napier of Merchistown in 1614 and their introduction into England by Briggs and others have already been mentioned in chapter 11. Napier. John Napier was born in Merchistown in 1550 and died on April 4th, 1617. He spent most of his time on the family estate near Edinburgh and took an active part in the political and religious controversies of the day. The business of his life was to shew that the Pope was the Antichrist, but his favourite amusement was the study of mathematics and science. As soon as the use of exponents became common in algebra, the introduction of logarithms would naturally follow, but Napier reasoned out that the result without the use of any symbolic notation to assist him, and the invention of logarithms was so far from being a sudden inspiration that it was the result of efforts of many years with a view to abbreviate the processes of multiplication and division. It is likely that Napier's attention may have been partly directed to the desirability of facilitating computations by the stupendous arithmetical efforts of some of his contemporaries, who seem to have taken a keen pleasure in surpassing one another in the extent to which they carried out multiplications and divisions. The trigonometrical tables by Rheticus, which were published in 1596 and 1613, were calculated in a most laborious way. Vieta himself delighted in arithmetical calculations which must have taken hours or days of hard work, and of which the results often served no useful purpose. L. van Keulen (1539 1610) practically devoted his life to finding a numerical approximation to the value of pi, finally in 1610 obtaining it correct to 35 places of decimals, while, to cite one more instance, P. A. Cataldi (1548 1626), who is chiefly known for his invention in 1613 of the form of continued fractions, though he failed to establish any of their properties, must have spent years in numerical calculations. In regard to Napier's other work, I may again mention that in his Rhabdologia, published in 1617, he introduced an improved form of rod by the use of which the product of two numbers can be found in a mechanical way. They can also be used for finding the quotient of one number by another. He also invented two other rods called virgulae, by which the square and the cube roots can be extracted. I should add that in spherical trigonometry he discovered certain formulae known as Napier's analogies, and also enunciated a rule of circular parts for the solution of right-angled spherical triangles. Briggs. The earliest table of common logarithms was constructed by Briggs and published in 1617. Henry Briggs was born near Halifax in 1556. He was educated at St. John's College, Cambridge, and took his degree in 1581 and obtained a fellowship in 1588. He was elected to the Gresham Professorship of Geometry in 1594, and in 1619 became Savilian Professor at Oxford, a chair which he held until his death on January 26, 1631. It may be interesting to add that the chair of geometry founded by Sir Thomas Gresham in 1596 was the earliest professorship of mathematics established in Great Britain. Some 20 years earlier, Sir Henry Savile had given at Oxford open lectures on Greek geometry and geometricians, and in 1619 he endowed the chairs of geometry and astronomy in that university, which are still associated with his name. Both in London and at Oxford, Briggs was the first occupant of the chair of geometry. He began his lectures at Oxford with the ninth proposition of the first book of Euclid, that being the furthest point to which Savile had been able to carry his audiences. At Cambridge, the Lucasian chair was established in 1663, the earliest occupants being Barrow and Newton. The almost immediate adoption through Europe of logarithms for astronomical and other calculations was mainly the work of Briggs. Amongst others, he convinced Kepler of the advantages of Napier's discovery, and the spread of the use of logarithms was rendered more rapid by the zeal and reputation of Kepler, who by his tables of 1625 and 1629 brought them into vogue in Germany, while Cavalieri in 1624 and Edmund Wingate in 1626 did similar service for Italian and French mathematicians respectively. Harriot. Thomas Harriot, born at Oxford in 1560 and died in London on July 2nd, 1621, did a great deal to extend and codify the theory of equations. The early part of his life was spent in America with Sir Walter Raleigh. While there he made the first survey of Virginia and North Carolina, the maps of these being subsequently presented to Queen Elizabeth. On his return to England he settled in London and gave up most of his time to mathematical studies. The majority of the propositions I have assigned to Vieta are to be found in Harriot's writings, but it is uncertain whether they were discovered by him independently of Vieta or not. In any case, it is probable that Vieta had not fully realized all that was contained in the propositions he had enunciated. The full consequences of these, with numerous extensions and systematic exposition of the theory of equations, were given by Harriot in his Artis Analyticae Praxis, which was first printed in 1631. The Praxis did not differ essentially from a good modern textbook. It is far more analytical than any algebra that preceded it, and marks a great advance in both symbolism and notation. It was widely read and proved one of the most powerful instruments in bringing analytical methods into general use. Harriot was, I believe, the earliest writer who realized the advantage to be obtained by taking all of the terms of an equation to one side of it. He was the first to use angle bracket signs to denote greater than and less than. When he denoted the unknown quantity by a, he represented a squared by a cubed by aaa, and so on. This is a distinct improvement on Vieta's notation. The same symbolism was used by Wallis as late as 1685, but concurrently with the modern index notation which was introduced by Descartes. Extracts from some of the other writings of Harriot were published by Rigaud in 1833. Oughtred. Among those who contributed to the general adoption in England of those various improvements and additions to algorism and algebra was William Oughtred, who was born at Eton on March 5th, 1574, and died at his vicarage of Albury in Surrey on June 30th, 1660. It is usually said that the cause of his death was the excitement and delight which he experienced at hearing the House of Commons had voted the king's return. But a recent critic adds that it should be remembered that by way of excuse that he, Oughtred, was then 86 years old. Oughtred was educated at Eton and King's College, Cambridge, of the latter of which colleges he was a fellow and for some time a mathematical lecturer. His Clavis Mathematica, published in 1631, is a good systematic textbook on arithmetic, and it contains practically all that was then known on the subject. In this work he introduced the symbol times for multiplication, and the symbol double colon in proportion. Previously to this time, a proportion such as a colon b equals c colon d was usually written as a minus sign b minus sign c minus sign d, but he denoted it by a dot b colon colon c dot d. Wallis says that some found fault with the book on account of the style, but that they only displayed their own incompetence, for Oughtred's words would be always full but not redundant. Pell makes a somewhat similar remark.
Oughtred also wrote a treatise on trigonometry published in 1657, in which abbreviations for sine, cosine, etc. were employed. This was really an important advance, but the works of Girard and Oughtred in which they were used were neglected and soon forgotten, and it was not until Euler reintroduced the contractions for the trigonometrical functions that they were generally adopted. We may say roughly that henceforth elementary arithmetic, algebra, and trigonometry were treated in a manner which is not substantially different from that now in use, and that the subsequent improvements introduced were additions to the subjects then known, and not a rearrangement of them on new foundations. The origins of the more common symbols in algebra. It may be convenient if I collect here in one place the scattered remarks I have made on the introduction of the various symbols of the more common operations in algebra. The latter Greeks and the Hindus and Jordanus indicated addition by mere juxtaposition. It will be observed that this is still the custom in arithmetic, where for example 2 1/2 stands for 2 plus 1/2. The Italian algebraists, when they gave up expressing every operation in words at full length, and introduced syncopated algebra, usually denoted plus by its initial letter P, or a line being sometimes drawn through the letter to shew that it was a symbol of operation and not a quantity, but the practice was not uniform. Pacioli, for example, sometimes denoted it by P with a bar on top, and sometimes by E, and Tartaglia commonly denoted it by the Greek letter phi. The German and English algebraists, on the other hand, introduced the sign plus almost as soon as they used algorism, but they spoke of it as signum additorem and employed it only to indicate excess. They also used it in the sense referred to previously. Widman used it as an abbreviation for excess in 1489. By 1630 it was part of the recognized notation of algebra and was used as a symbol of operation. Subtraction was indicated by Diophantus as an inverted and truncated Greek letter phi. The Hindus denoted it by a dot. The Italian algebraists, when they introduced syncopated algebra, generally denoted minus by M, big capital M or lowercase m, a line being sometimes drawn through the letter, but the practice was not uniform. Pacioli, for example, denoting it sometimes by M with a bar over it, and sometimes by DE for demptus. The German and English algebraists introduced the present symbol by which they described signum subtractorum. It is most likely that the vertical bar in the symbol for plus was superimposed on the symbol for minus to distinguish the two. In origin, both symbols were probably mercantile marks. It may be noticed that Pacioli and Tartaglia found the sign minus already used to denote a division, a ratio, or a proportion indifferently. The present sign was in general use by about the year 1630 and was then employed as a symbol of operation. Oughtred in 1631 used the sign times to denote multiplication. Harriot in 1631 denoted the operation by a dot. Descartes in 1637 indicated it by juxtaposition. I am not aware of any symbols for it which were in previous use. Leibniz in 1686 employed the sign an inverted semicircle facing down to denote multiplication and a semicircle facing up to denote division. Division was ordinarily denoted by the Arab way of writing quantities in the form of a fraction by means of a line drawn between them in any of the forms a minus b, a slash b, or a over b. Oughtred in 1631 employed a dot to denote either division or a ratio. I do not know when the colon was first introduced to denote a ratio, but it occurs in a work by Clairaut published in 1760. I believe that the then current symbol for division, with a dash inside a colon, is only a combination
of the dash and the colon. It was used by John Hendrik Run at Zurich in 1659 and John Pell in London in 1668. The current symbol for equality was introduced by Record in 1557. Xylander in 1575 denoted it by two parallel vertical lines, but in general till the year 1600 the word was written at length, and from then until the time of Newton, say about 1680, it was more frequently represented by an alpha or a reverse alpha than by any other symbol. Each of these latter signs were used as a contraction for the first two letters of the word aequalis. I may add that Vieta, Schouten, and others employed the sign equals to denote the difference between. Thus a equal sign b meant with them what we denote by a minus b. The symbol double colon to denote proportion or by the equality of two ratios was introduced by Oughtred in 1631 and it was brought into common use by Wallis in 1686. There is no object in having a symbol to indicate equality of two ratios which is different from that used to indicate equality of other things, and it is better to replace it by the sign equals. The sign right angle bracket for is greater than and the sign left angle bracket for is less than were introduced by Harriot in 1631, but Oughtred simultaneously invented different symbols for greater than less than, and these latter were frequently used until the beginning of the 18th century, e.g. by Barrow. The symbol equal sign with a stroke through it for is not equal to, a right angle bracket with a stroke through it for is not greater than, and a left angle bracket with a stroke through it for is not less than, are of recent introduction. The vinculum was introduced by Vieta in 1591, and the brackets were first used by Girard in 1629. The different methods of representing the power to which a magnitude was raised have already been briefly alluded to. The earliest known attempt to frame a symbolic notation was made by Bombelli in 1572 when he represented an unknown quantity by 1 inside an upturned semicircle, and its square by 2 inside an upturned semicircle, and its cube by a 3 inside an upturned semicircle, etc. In 1586 Stevinus used 1 written inside a circle, 2 written inside a circle, 3 written inside a circle in a similar way, and suggested, though he did not use a corresponding notation for fractional indices. In 1591 Vieta improved on this by denoting the different powers of a by a quad, a cub, etc., so that he could indicate the powers of different magnitudes. Harriot in 1631 further improved on Vieta's notation by writing AA for a squared, AAA for a cubed, etc. And this remained in use for 50 years concurrently with the index notation. In 1634 P. Herragonus in his Cursus Mathematicus, published in 5 volumes at Paris in 1634 to 1637, wrote A2, A3 for a squared, a cubed. The symbol surd to denote the square root was first introduced by Rudolph in 1526. A similar notation had been used by Bhaskara. The idea of using exponents to mark the power to which a quantity was raised was due to Descartes and was introduced by him in 1637, but he used only positive integral indices, a to the 1, a squared, a cubed, and so on. Wallis in 1659 explained the meaning of negative fractional indices in expressions such as x to the power of -1 or x to the power of 2/3, etc., the latter conception having been foreshadowed by Erasmus and perhaps by Stevinus. Finally, the idea of an index unrestricted in magnitude such as the n in the expansion of a to the power n, I believe, is due to Newton and was introduced by him in connection with the binomial theorem in the letters for Leibniz written in 1676. The symbol 8 written sideways for infinity was first employed by Wallis in 1655 in his Arithmetica Infinitorum, but does not occur again until 1713 when it is used in James Bernoulli's Ars Conjectandi. The sign was sometimes employed by the Romans to denote the number 1000, and it has been conjectured that this led to its being applied to represent any very large number. There are but few special symbols in trigonometry. I may however add here the following note which contains all that I have been able to learn on the subject. The current sexagesimal division of angles is derived from the Babylonians through the Greeks. The Babylonian unit angle was the angle of an equilateral triangle. Following their usual practice, this was divided into 60 equal parts or degrees. A degree was subdivided into 60 equal parts or minutes, and so on. The word sine was used by Regiomontanus and was derived from the Arabs. The terms secant and tangent were introduced by Thomas Finck, born in Denmark in 1561 and died in 1646, in his Geometriae Rotundae, Bale 1583. And the word cosecant, I believe, was first used by Rheticus in his Opus Palatinum, 1596. The terms cosine and cotangent were first employed by E. Gunter in his Canon Triangularum, London, 1620. The abbreviations sin, sin, tan, tan, sec for secant were used in 1626 by Albert Gerard, and those of cos, cos, and cot for cotangent by Oughtred in 1657, but these contractions did not come into general use till Euler reintroduced them in 1748. The idea of trigonometrical functions originated with John Bernoulli, and this view of the subject was elaborated in 1748 by Euler in his Introductio in Analysen Infinitorum. End of section 16. Recording by Paul King, pjk.scripts.mit.edu/pkj.
Chapter 13 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by W. Rouse. Chapter 13. The Close of the Renaissance, circa 1586 to 1637. The closing years of the Renaissance were marked by a revival of interest in nearly all branches of mathematics and science. As far as pure mathematics is concerned, we have already seen that during the last half of the 16th century there had been a great advance in algebra, theory of equations, and trigonometry. And we shall shortly see in the second section of this chapter that in the early part of the 17th century some new processes in geometry were invented. If, however, we turn to applied mathematics, it is impossible not to be struck by the fact that even as late as the middle or end of the 16th century no marked progress in the theory had been made from the time of Archimedes. Statics of solids and hydrostatics remained in much the state in which he had left them, while dynamics as a science did not exist. It was Stevinus who gave us the first impulse to the renewed study of statics, and Galileo who laid the foundation of dynamics, and to their works the first section of this chapter is devoted. The development of mechanics and experimental methods. Stevinus. Simon Stevinus was born in Bruges in 1548 and died at The Hague in the 17th century. We know very little of his life save that he was originally a merchant's clerk at Antwerp, and at a later period of his life was the friend of Prince Maurice of Orange, by whom he was made quartermaster general of the Dutch army. To his contemporaries he was the best known for his works on fortifications and military engineering, and the principles he laid down are said to be in accordance with those which are now usually accepted. To the general populace he was also well known on account of his invention of a carriage which was propelled by sails. This ran on the seashore, carried 28 people, and easily outstripped horses galloping by the side. His model of it was destroyed in 1802 by the French when they invaded Holland. It was chiefly owing to the influence of Stevinus that the Dutch and French began a proper system of bookkeeping in the national accounts. I have already alluded to the introduction in his arithmetic, published in 1585, of exponents to mark the power to which quantities were raised. He is said to have suggested the use of fractional but not negative exponents. For instance, he wrote 3x squared minus 5x plus 1 as 3 followed by 2 in a circle for x squared minus 5 followed by a 1 in a circle signifying x plus 1 followed by a solid dot in a circle. His notation for decimal fractions was of a similar character. In the same book he likewise suggested a decimal system of weights and measures. He also published a geometry which is ingenious, though it does not contain many results which were not previously known. It is, however, on his statics and hydrostatics, published in Flemish at Leyden in 1586, that his fame will rest. In this work he enunciated the triangle of forces, a theorem which some think was the first propounded by Leonardo da Vinci. Stevinus regarded this as the fundamental proposition of the subject. Previous to the publication of his work, the science of statics had rested on the theory of the lever, but since then it has been usual to commence by proving the possibility of representing forces by straight lines, and so of reducing many theorems to geometrical propositions, and in particular to obtaining in that way a proof of the parallelogram, which is equivalent to the triangle of forces. Stevinus is not clear in his arrangement of the various propositions and discussions of their sequence, and the new treatment of the subject was not definitely established before the appearance in 1687 of Varignon's work on mechanics. Stevinus also found the force which must be exerted along the line of the greatest slope to support a given weight on an inclined plane, a problem the solution of which had long been in dispute. He further distinguished between stable and unstable equilibrium. In hydrostatics he discussed the question of the pressure which a fluid can exercise, and explained the so-called hydrostatic paradox. Stevinus was somewhat dogmatic in his statements and allowed no one to differ from his conclusions. And those, says he in one place, who cannot see this, may the author of nature have pity upon their unfortunate eyes, for the fault is not in the thing, but in the sight which we are not able to give them. Galileo. Just as the modern treatment of statics originates with Stevinus, so the foundation of the science of dynamics is due to Galileo. Galileo Galilei, born in Pisa on February 18, 1564, and died near Florence on January 8, 1642. His father, a poor descendant of an old and noble Florentine house, was himself a fair mathematician and a good musician. Galileo was educated at the monastery in Vallombrosa, where his literary ability and mechanical ingenuity attracted considerable attention. He was persuaded to become a novitate of the order in 1580, but his father, who intended him to be a doctor, at once removed him and sent him in 1581 to the University of Pisa to study medicine. It was there that he noticed that the great bronze lamp which still hangs from the roof of the cathedral performed its oscillations in equal times, quite independently of whether the oscillations were large or small, a fact which he verified by counting his pulse. He had been hitherto purposely kept in ignorance of mathematics, but one day, by chance hearing a lecture on geometry, he was so fascinated by the science that he thenceforward devoted all of his spare time to its study, and finally he got leave to discontinue his medical studies. He left university in 1586 and almost immediately commenced his original researches. He published in 1587 an account of the hydrostatic balance, and in 1588 an essay on the centre of gravity in solids. The fame of these works secured for him the appointment to the mathematical chair at Pisa, the stipend, as was the case with most professorships, being very small. During the next 3 years he carried on from the Leaning Tower that series of experiments on falling bodies which established the first principles of dynamics. Unfortunately, the manner in which he promulgated his discoveries and the ridicule he threw on those who opposed him gave not an unnatural offence, and in 1591 he was obliged to resign his position. At this time he seems to have been much hampered by want of money. Influence was however exerted on his behalf with the Venetian Senate, and he was appointed professor at Padua, a chair which he held for 18 years, 1592 to 1610. His lectures there seem to have been chiefly on the mechanics and hydrostatics, and the substance of them is contained in his treatise on mechanics, which was published in 1612. In these lectures he repeated his Pisan experiments and demonstrated that falling bodies did not, as was then believed, descend with velocities proportional, amongst other things, to their weights. He further shewed that, if it were assumed that they were descended with a uniformly accelerated motion, it was possible to deduce the relations of connecting velocity, space, and time, which did actually exist. At a later date, by observing the times of descent of bodies sliding down inclined planes, he shewed that this hypothesis was true. He also proved that the path of a projectile was a parabola, and in doing so implicitly used the principles laid down in the first 2 laws of motion as enunciated by Newton. He gave an accurate definition of momentum, which some writers have thought may be taken to imply a recognition of the truth of the 3rd law of motion. The laws of motion are however nowhere enunciated in the precise and definite form, and Galileo must be regarded rather as preparing the way for Newton than as being himself the creator of the science of dynamics. In statics, he laid down the principle that in machines what was gained in power was lost in speed, and in the same ratio. In the statics of solids he found the force which can support a given weight on an inclined plane. In hydrostatics he propounded the more elementary theorems on pressure and on floating bodies, while among hydrostatical instruments he invented the thermometer, though in a somewhat imperfect form. It is, however, as an astronomer that most people regard Galileo, and though strictly speaking his astronomical researches lie outside the subject matter of this book, it may be interesting to give the leading facts. It was in the spring of 1609 that Galileo heard that a tube containing lenses had been made by Lippershey in Holland, which served to magnify objects seen through it. This gave him the clue, which he constructed a telescope of that kind which still bears his name, and of which an ordinary opera glass is an example. Within a few moments he had produced instruments which were capable of magnifying 32 diameters, and within a year he had made and published observations on the solar spots, the lunar mountains, Jupiter's satellites, the phases of Venus, and Saturn's ring. Honours and emoluments were showered on him, and he was enabled in 1610 to give up his professorship and retire to Florence. In 1611 he paid a temporary visit to Rome, and exhibited in the gardens of the Vatican the new worlds revealed by the telescope. It would seem that Galileo had always believed in the Copernican system, but was afraid of promulgating it on account of the ridicule it excited. The existence of Jupiter's satellite seemed however to make this truth almost certain, and he now boldly preached it. The orthodox party resented his action, and on February 24, 1616, the Inquisition declared that to suppose the sun the centre of the solar system was absurd, heretical, and contrary to Holy Scripture. The edict of March 5, 1616, which carried this into effect, had never been repealed, though it has long been tacitly ignored. It is well known that toward the middle of the 17th century the Jesuits evaded it by treating the theory as an hypothesis from which, though false, certain results would follow. In January 1632 Galileo published his dialogues on the system of the world, in which in clear and forcible language he expounded the Copernican theory. In these, apparently through jealousy of Kepler's fame, he does not so much as mention Kepler's laws, the first two of which had been published in 1609 and the third in 1619, and he rejects Kepler's hypothesis that the tides are caused by the attraction of the moon. He rests the proof of the Copernican hypothesis on the absurd statement that it would cause tides because different parts of the earth would rotate with different velocities. He was more successful in shewing that mechanical principles would account for the fact that a stone thrown straight up would fall again to the place from which it was thrown, a fact which had previously been one of the chief difficulties in the way of any theory which supposed the earth to be in motion. The publication of this book was certainly contrary to the edict of 1616. Galileo was at once summoned to Rome, forced to recant, do penance, and was only released on good behaviour. The documents recently printed shew that he was threatened with the torture, but that there was no intention of carrying the threat into effect. When released, he again took up his work on mechanics, and by 1636 had finished a book which was published under the title Discorsi intorno a due nuove scienze at Leyden in 1638. In 1637 he lost his sight, but with the aid of pupils he continued his experiments on mechanics and hydrostatics, and in particular on the possibility of using a pendulum to regulate a clock, and on the theory of impact. An anecdote of this time has been preserved, which may or may not be true, but is sufficiently interesting to bear repetition. According to one version of the story, Galileo was one day interviewed by some members of a Florentine guild who wanted their pumps altered so as to raise water to a height which was greater than 30 feet, and thereupon he remarked it might be desirable to first find out why the water rose at all. A bystander interfered and said there was no difficulty about that because nature abhorred a vacuum. Yes, said Galileo, but apparently it is only a vacuum which is less than 30 feet. His favourite pupil Torricelli was present, and thus had his attention directed to the question, which he subsequently elucidated. Galileo's work may, I think, be fairly summed up by saying that his researches on mechanics are deserving of high praise, and that they are memorable for clearly enunciating the fact that science must be founded on laws obtained by experiment. His astronomical observations and his deductions therefrom were also excellent, and were expounded with a literary and scientific skill which leaves nothing to be desired. But though he produced some of the evidence which placed the Copernican theory on a satisfactory basis, he did not himself make any special advance in the theory of astronomy. Francis Bacon. The necessity of an experimental foundation for science was advocated with even greater effect by Galileo's contemporary Francis Bacon, Lord Verulam, who was born in London on January 22, 1561, and died on April 9, 1626. He was educated at Trinity College, Cambridge. His career in politics and at the bar culminated in his becoming Lord Chancellor with the title Lord Verulam. The story of his subsequent degradation for accepting bribes was well known. His chief work is the Novum Organum, published in 1620, which he lays down the principles which should guide those who are making experiments on which they propose to find a theory of any branch of physics or applied mathematics. He gave rules by which the results of induction could be tested, hasty generalizations avoided, and experiments used to check one another. The influence of this treatise in the 18th century was great, but it is probable that during the preceding century it was little read, and the remark repeated by several French writers that Bacon and Descartes are the creators of modern philosophy rests on a misapprehension of Bacon's influence on his contemporaries. Any detailed account of this book belongs, however, to the history of scientific ideas rather than to that of mathematics. Before leaving the subject of applied mathematics, I may add a few words on the writings of Guldinus, Wright, and Snell. Guldinus. Habakkuk Guldinus, born in St. Gall on June 12, 1577, and died at Graz, November 3, 1643, was of Jewish descent, but was brought up as a Protestant. He was converted to Roman Catholicism and became a Jesuit when he took the Christian name of Paul, and it was to him that the Jesuit colleges in Rome and Graz owed their mathematical reputation. The two theorems known by the name of Pappus, to which I alluded, were published by Guldinus in the fourth book of his De Centro Gravitatis, Vienna, 1635–1642. Not only were the rules in question taken without acknowledgment from Pappus, according to Montecle, the proof of them was given by Guldinus was faulty, even though he was successful in applying them to the determination of the volumes and surfaces of certain solids. The theorems were however previously unknown, and their enunciation excited considerable interest. Wright. I may here also refer to Edward Wright, who is worthy of mention for having put the art of navigation on a scientific basis. Wright was born in Norfolk at about 1560 and died in 1615. He was educated at Caius College, Cambridge, of which society he was subsequently a fellow. He seems to have been a good sailor, and he has special talent for the construction of instruments. About 1600 he was elected lecturer on mathematics by the East India Company. He then settled in London and shortly afterwards was appointed mathematical tutor to Prince Henry of Wales, the son of James I. His mechanical ability may be illustrated by an orrery of his construction, by which it was possible to predict eclipses for over 17,000 years in advance. It was shewn in the Tower as a curiosity as late as 1675. In the maps in use before the time of Gerard Mercator, a degree, whether of latitude or longitude, had been represented in all cases by the same length, and the course to be pursued by a vessel was marked on the map by a straight line joining the ports of arrival and departure. Mercator had seen that this led to considerable errors, and had realized that to make this method of tracing the course of a ship at all accurate, the space assigned on the map to a degree of latitude ought to gradually increase as the latitude increased. Using this principle, he had empirically constructed some charts which were published about 1560 or 1570. Wright set himself the problem to determine the theory on which such maps should be drawn, and succeeded in discovering the law of the scale of the maps, though his rule is strictly correct for small arcs only. The result was published in the second edition of Blundeville's Exercises. In 1599, Wright published his Certain Errors in Navigation Detected and Corrected, in which he explained the theory and inserted a table of meridional parts. The reasoning shews considerable geometrical power. In the course of the work he gives the declinations of 32 stars, explains the phenomenon of the dip, parallax, and refraction, and adds a table of magnetic declinations, but he assumes the Earth to be stationary. In the following year he published some maps constructed on his principle. In these the northernmost point of Australia is shewn, the latitude of London is taken to be 51 degrees 32 minutes. Snell. A contemporary of Guldinus and Wright was Wilbrod Snell, whose name is still well known through his discovery in 1619 of the law of refraction in optics. Snell was born at Leyden in 1591 and occupied a chair of mathematics at the university there, and died there on October 30th, 1626. He was one of those infant prodigies who occasionally appear. At the age of 12 he was acquainted with the standard mathematical works. I will here only add that in geodesy he laid down the true principles for measuring the arc of a meridian, and in spherical trigonometry he discovered the properties of the polar or supplemental triangle. Residual interest in pure geometry. The close of the 16th century was marked not only by the attempt to find a theory of dynamics based on laws derived from experiment, but also by a revived interest in geometry. This was largely due to the influence of Kepler. Johann Kepler, one of the founders of modern astronomy, was born of humble parents near Stuttgart on December 27, 1571, and died at Ratisbon on November 15, 1630. He was educated under Maestlin at Tübingen. In 1593 he was appointed professor at Graz, where he made the acquaintance of a wealthy and beautiful widow whom he married, but found too late that he had purchased his freedom from pecuniary troubles at the expense of domestic happiness. In 1599 he accepted an appointment as assistant to Tycho Brahe, and in 1601 succeeded his master as astronomer to the Emperor Rudolf II. But his career was dogged by bad luck. First his stipend wasn't paid, next his wife went mad and then died, and though he married again in 1611 this proved even more unfortunate venture than before, for though to secure a better choice he took the precaution to make a preliminary selection of 11 girls whose merits and demerits he carefully analyzed in a paper which is still extant, he finally selected the wrong one, while to complete his discomfort he was expelled from his chair and narrowly escaped condemnation for heterodoxy. During this time he depended for his income on telling fortunes and casting horoscopes, for, as he says, nature, which has conferred upon every animal the means of existence, has designed astrology as an adjunct and ally to astronomy. He seems, however, to have no scruple in charging heavily for his services, and to the surprise of his contemporaries was found at his death to have a considerable hoard of money. He died while on a journey to try and recover for the benefit of his children some of the arrears of his stipend. In describing Galileo's work I alluded briefly to the three laws in astronomy that Kepler had discovered, and in connection with which his name will be always associated, and I have already mentioned the prominent part he took in bringing logarithms into general use on the continent. These are familiar facts, but it is not known so generally that Kepler was also a geometrician and algebraist of considerable power, and that he, Desargues, and perhaps Galileo may be considered as forming a connecting link between the mathematicians of the Renaissance and those of modern times. Kepler's work in geometry consists rather in certain general principles which he laid down and illustrated by a few cases than in any systematic exposition of the subject. In a short chapter on conics inserted in his Paralipomena, published in 1604, he lays down what has been called the principle of continuity, and gives an example of the statement that a parabola is at once the limiting case of an ellipse and of a hyperbola. He illustrates the same doctrine by reference to the foci of conics. The word focus was introduced by him, and he also explains that the parallel lines should be regarded as meeting at infinity. In his Stereometrica, which was published in 1615, he determines the volume of certain vessels and the areas of certain surfaces by means of infinitesimals instead of by the long and tedious method of exhaustions. These investigations, as well as those of 1604, arose from a dispute with a wine merchant as to the proper way of gauging the contents of a cask. This use of infinitesimals was objected to by Guldinus and other writers as inaccurate, but though the methods of Kepler are not altogether free from objection, he was substantially correct, and by applying the law of continuity to infinitesimals he prepared the way for Cavalieri's method of indivisibles and the infinitesimal calculus of Newton and Leibniz. Kepler's work on astronomy lies outside the scope of this book. I will mention only that it was founded on the observations of Tycho Brahe, whose assistant he was. His three laws of planetary motion were the result of many and laborious efforts to reduce the phenomenon of the solar system to certain simple rules. The first two were published in 1609 and stated that the planets describe ellipses around the sun being a focus, and that the line joining the sun to any planet sweeps over equal areas in equal times. The third was published in 1619 and stated that the square of the periodic times of the planets are proportional to the cubes of the major axes of their orbits. I thought to add that he attempted to explain why these motions took place by a hypothesis which is not very different from Descartes' theory of vortices. Kepler also devoted considerable time to the elucidation of theories of visions and refractions in optics. While the conception of the geometry of the Greeks were being extended by Kepler, a Frenchman, whose name until recently was almost unknown, was inventing a new method of investigating the subject, a method which is now known as projective geometry. This was the discovery of Desargues, whom I put with some hesitation at the close of this period and not among the mathematicians of modern times.
Desargues. Gerard Desargues, born at Lyon in 1593 and died in 1662, was by profession an engineer and architect, but gave some courses of gratuitous lectures in Paris from 1626 to about 1630, which made a great impression upon his contemporaries. Both Descartes and Pascal had a high opinion of his work and abilities, and both made considerable use of the theorems he had enunciated. In 1636 Desargues issued a work on perspective, but most of his researches were embodied in his Brillant Project on conics, published in 1639, a copy of which was discovered by Charles in 1845. I take the following summary of it from Charles Taylor's work on conics. Desargues commences with the statement of the doctrine of continuity as laid down by Kepler. Thus the points at the opposite ends of a straight line are regarded as coincident. Parallel lines are treated as meeting at a point at infinity, and parallel planes on a line at infinity, while a straight line may be considered as a circle whose centre is at infinity. The theory of involution of 6 points with its special cases is laid down, and the projective property of pencils in involution is established. The theory of polar lines is expounded, and its analogue in space suggested. A tangent is defined as the limiting case of a secant, and an asymptote as a tangent at infinity. Desargues shews that the lines which join 4 points in a plane determine 3 pairs of lines in involution on any transversal, and from any conic through the 4 points another pair of lines can be obtained which are in involution with any 2 of the former. He proves that the points of intersection of the diagonals and the 2 pairs of opposite sides of any quadrilateral inscribed in a conic are a conjugate triad with respect to the conic, and when one of the 3 points is infinity, its polar is a diameter. But he fails to explain the case in which the quadrilateral is a parallelogram, although he had formed the conception of a straight line which was wholly at infinity. The book therefore may be fairly said to contain the fundamental theorems on involution, homology, poles and polars, and perspective. The influence exerted by the lectures of Desargues on Descartes, Pascal, and the French geometricians of the 17th century was considerable, but the subject of projective geometry soon fell into oblivion, chiefly because the analytical geometry of Descartes was so much more powerful as a method of proof or discovery. The researches of Kepler and Desargues will serve to remind us that the geometry of the Greeks was not capable of much further extension. Mathematicians were now beginning to seek new methods of investigation, and were extending the conceptions of geometry. The invention of analytical geometry and of the infinitesimal calculus temporarily diverted attention from pure geometry. But at the beginning of the present century there was a revival of interest in it, and since then it has been a favourite subject of study with many mathematicians. Mathematical knowledge at the close of the Renaissance. Thus, by the beginning of the 17th century, we may say that the fundamental principles of arithmetic, algebra, theory of equations, and trigonometry had been laid down, and the outlines of the subject as we know them have been traced. It must be however remembered that there were no good elementary textbooks on these subjects, and a knowledge of them was therefore confined to those who could extract it from the ponderous treatises in which it lay buried. Though much of the modern algebraical and trigonometrical notation had been introduced, it was not familiar to mathematicians, nor was it even universally accepted, and it was not until the end of the 17th century that the language of these subjects was definitely fixed. Considering the absence of good textbooks, I am inclined rather to admire the rapidity with which it came into universal use, than to cavil at the hesitation to trust it alone which many writers shewed. If we turn to applied mathematics, we find on the other hand that the science of statics had made but little advance in the 18 centuries that had elapsed since the time of Archimedes, while the foundations of dynamics were laid by Galileo only at the close of the 16th century. In fact, as we shall see later, it was not until the time of Newton that the science of mechanics was placed on a satisfactory basis. The fundamental conceptions of mechanics are difficult, but the ignorance of the principles of the subject shewn by mathematicians of this time is greater than would have been anticipated from their knowledge of pure mathematics. With this exception, we may say that the principles of analytical geometry and of the infinitesimal calculus were needed before there was likely to be much further progress. The former was employed by Descartes in 1637, the latter invented by Newton and possibly independently by Leibniz some 30 or 40 years later, and their introduction may be taken as marking the commencement of the period of modern mathematics.
End of section 19. Recorded by Paul King, Oakville, Ontario. http://pjk.scripps.mit.edu/pkj Chapter 14 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a recording by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics, Chapter 14. Features of modern mathematics. The division between this period and that treated in the last 6 chapters is by no means so well defined as that which separates the history of Greek mathematics from the mathematics of the Middle Ages. The methods of analysis used in the 17th century and the kind of problems attacked changed but gradually, and the mathematicians at the beginning of this period were in immediate relations with those at the end of the last considered. For this reason, some writers have divided the history of mathematics into 2 parts only, treating the schoolmen as the lineal successors of the Greek mathematicians, and dating the creation of modern mathematics from the introduction of the Arab textbooks into Europe. The division I have given is, I think, more convenient, for the introduction of analytical geometry and of the calculus completely revolutionized the development of the subject, and it therefore seems preferable to take their invention as marking the commencement of modern mathematics. The time that has elapsed since these methods were invented has been a period of incessant intellectual activity in all departments of knowledge, and the progress made in mathematics has been immense. The greatly extended range of knowledge and the rapid intercommunication of ideas due to printing increase the difficulties of a historian, while the mass of materials which has to be mastered, the absence of perspective, and even the echoes of old controversies combine to make it very difficult to give a clear and just account of the development of the subject. As, however, the leading facts are generally known, and the works published during this time are accessible to any student, I may deal more concisely with the lives and writings of modern mathematicians than with those of their predecessors, and confine myself more strictly than before to those who have materially affected the progress of the subject. Roughly speaking, we may say that 5 distinct stages in the history of this period can be discerned. First of all, there is the invention of analytical geometry by Descartes in 1637, and almost at the same time the introduction of the method of indivisibles, by the use of which areas, volumes, and the positions of centres of mass can be determined by summation in a manner analogous to that effected nowadays by the aid of the integral calculus. The method of indivisibles was soon superseded by the integral calculus. Analytical geometry, however, maintains its position as part of the necessary training of every mathematician, and is incomparably more potent than the geometry of the ancients for all purposes of research. The latter is still no doubt an admirable intellectual training, and it frequently affords an elegant demonstration of some proposition the truth of which is already known, but it requires a special procedure for every particular problem attacked. The former, on the other hand, lays down a few simple rules by which property can be at once proved or disproved. In the second place, we have the invention of the fluxional or differential calculus about 1666, and possibly an independent invention of it in 1674. Wherever a quantity changes according to some continuous law, and most things in nature do so change, the differential calculus enables us to measure its rate of increase or decrease. And from its rate of increase or decrease, the integral calculus enables us to find the original quantity. Formerly, every separate function of x, such as 1 plus x quantity to the power n, or the logarithm of 1 plus x, the sine of x, or the arctan of x, etc., could be expanded in ascending powers of x only by means of such special procedure as was suitable for that particular problem. But by the aid of the calculus, the expansion of any function of x in ascending powers of x is in general reducible to one rule which covers all cases alike. So again the theory of maxima and minima, the determination of the lengths of curves and the areas enclosed by them, the determination of surfaces of volumes and the centres of mass, and many other problems are each reducible to a single rule. The theories of differential equations, of the calculus of variations, of finite differences, etc., are the developments of the ideas of the calculus. These two subjects, analytical geometry and the calculus, became the chief instruments of further progress in mathematics. In both of them, a sort of machine was constructed to solve a problem. It was only necessary to put in the particular function dealt with, or the equation of the particular curve or surface considered, and on performing certain simple operations the result came out. The validity of the process was proved once and for all, and it was no longer requisite to invent some special method for every separate function, curve, or surface. In the third place, Huygens laid the foundation of a satisfactory treatment of dynamics, and Newton reduced it to an exact science. The latter mathematician proceeded to apply the new analytical methods not only to numerous problems in the mechanics of solids and fluids on the earth, but to the solar system. The whole of mechanics, terrestrial and celestial, was thus brought within the domain of mathematics. There is no doubt that Newton used the calculus to obtain many of his results, but he seems to have thought that, if his demonstrations were established by the aid of a new science which was at that time generally unknown, his critics, who would not understand the fluxional calculus, would fail to realize the truth and importance of his discoveries. He therefore determined to give geometrical proofs of all of his results. He accordingly cast the Principia into a geometrical form, and thus presented it to the world in a language which all men could then understand. The theory of mechanics was extended and was systematized into its modern form by Laplace and Lagrange toward the end of the 18th century. In the fourth place, we may say that during this period the chief branches of physics have been brought within the scope of mathematics. This extension of the domain of mathematics was commenced by Huygens and Newton when they propounded their theories of light, but it was not until the beginning of this century that sufficiently accurate observations were made in the most physical subjects to enable mathematical reasoning to be applied to them. From the results of the observations and experiments which have been since published, numerous and far-reaching conclusions have been obtained by the use of mathematics, but we now want some more simple hypotheses from which we can deduce those laws which at present form our starting point. If, to take one example, we could say in what electricity consisted, we might get some simple laws or hypotheses from which, by the aid of mathematics, all the observed phenomenon could be then deduced, in the same way as Newton deduced all the results of physical astronomy from the law of gravitation. All lines of research seem moreover to indicate that there is an intimate connection between the different branches of physics, e.g. between light, heat, electricity, and magnetism. The ultimate explanation of this and of the leading facts in physics seems to demand a study of molecular physics. A knowledge of molecular physics in its turn seems to require some theory as to the constitution of matter. It would further appear that the key to the constitution of matter is to be found in chemistry or chemical physics. So the matter stands at present. Helmholtz in Germany and Maxwell and Lord Kelvin, Sir William Thomson, in Great Britain have done a great deal in applying mathematics to physics, but the connection between the different branches of physics and the fundamental laws of those branches, if there be any simple ones, are riddles which are not yet solved. This history does not pretend to treat of problems which are now the subject of investigation, and though mathematical physics forms a large part of modern mathematics, I shall not discuss it in any detail. Fifthly, this period has seen an immense extension of pure mathematics. Much of this is the creation of comparatively recent times, and I regard the details of it as outside the limits of this book, though in chapter 19 I have allowed myself to mention some of the subjects discussed. The most striking features of this extension are the developments of higher geometry, of higher arithmetic, or the theory of numbers, of higher algebra, including the theory of forms, and of the theory of equations, and also the discussion of functions of double and multiple periodicity, and notably the creation of a theory of functions. End of section 20. Recording by Paul King. pjk.scripps.mit.edu/pkj. Chapter 15 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A Short Account of the History of Mathematics by Rouse. Chapter 15. History of Mathematics from Descartes to Huygens, circa 1635 to 1675. I propose in this chapter to consider the history of mathematics during the 40 years in the middle of the 17th century. I regard Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens as the leading mathematicians of this time. I shall treat them in that order, and I shall conclude with a brief list of the more eminent remaining mathematicians of the same date. I have already stated that the mathematicians of this period, and the remark applies more particularly to Descartes, Pascal, and Fermat, were largely influenced by the teaching of Kepler and Desargues, and I would repeat again that I regard these latter and Galileo as forming a connecting link between the writers of the Renaissance and those of modern times. I should also add that the mathematicians considered in this chapter were contemporaries, and although I have tried to place them roughly in such an order that their chief works shall come in chronological arrangement, it is essential to remember that they were in relation with one another, and in general were acquainted with one another's researches as soon as they were published. Descartes. Subject to the above remarks, we may consider Descartes as the first of the modern school of mathematics. René Descartes was born near Tours on March 31, 1596, and died at Stockholm on February 11, 1650. He was thus a contemporary of Galileo and Desargues. His father, who as the name implies was of a good family, was accustomed to spend half the year at Rennes when the local parliament in which he held a commission as a councillor was in session, and the rest of the time on his family estate at Les Cartes at La Haye. René, the second of a family of 2 sons and 1 daughter, was sent at the age of 8 years to the Jesuit school at La Flèche, and of the admirable discipline and education there given he speaks most highly. On account of his delicate health he was permitted to lie in bed till late in the morning. This was a custom which he had always followed, and when he visited Pascal in 1647 he told him that the only way to do good work in mathematics and to preserve his health was never to allow anyone to make him get up in the morning before he felt inclined to do so, an opinion which I chronicle for the benefit of any schoolboy into whose hands this work may fall. On leaving school in 1612, Descartes went to Paris to be introduced to the world of fashion. Here, through the medium of the Jesuits, he made the acquaintance of Midorge, and renewed his schoolboy friendship with Father Mersenne, and together with them he devoted the 2 years of 1615 and 1616 to the study of mathematics. At the time, a man of position usually entered either the army or the church. Descartes chose the former profession, and in 1617 joined the army of Prince Maurice of Orange, then at Breda. Walking through the streets he saw a placard in Dutch which excited his curiosity, and stopping the first passer asked him to translate it into either French or Latin. The stranger, who happened to be Isaac Beekman, the head of the Dutch college at Dort, offered to do so if Descartes would answer it, the placard being in fact a challenge to all the world to solve a geometrical problem there given. Descartes worked it out within a few hours, and a warm friendship between him and Beekman was the result. This unexpected test of his mathematical attainments made the uncongenial life of the army distasteful to him, but under family influence and tradition he remained a soldier, and was persuaded at the commencement of the 30 Years' War to volunteer under the court at Bucquoy in the army of Bavaria. He continued all this time to occupy his leisure with mathematical studies, and was accustomed to date the first ideas of his new philosophy and of his analytical geometry from 3 dreams he experienced on the night of November 10, 1619 at Neuburg, when campaigning on the Danube. He regarded this as the critical day of his life, and one which determined his whole future.
He resigned his commission in the spring of 1621 and spent the next 5 years in travel, during most of which time he continued to study pure mathematics. In 1626 we find him settled at Paris, a little well-built figure, modestly clad in green taffety, and only wearing a sword and feather in token of his quality as a gentleman. During the first 2 years there he interested himself in general society and spent his leisure in the construction of optical instruments, but these pursuits were merely the relaxations of one who failed to find in philosophy that theory of the universe which he was convinced finally awaited him. In 1628 Cardinal de Bray, the founder of the Oratorians, met Descartes and was so much impressed by his conversation that he urged on him the duty of devoting his life to the examination of truth. Descartes agreed, and the better to secure himself from interruption moved to Holland, then at the height of its power. There for 20 years he lived, giving up all his time to philosophy and mathematics. Science, he says, may be compared to a tree. Metaphysics is the root, physics is the trunk, and the three chief branches are mechanics, medicine, and morals, these forming the three applications of our knowledge, namely to the external world, to the human body, and to the conduct of life, and with these subjects alone his writings are concerned. He spent the first 4 years, 1629 to 1633, of his stay in Holland in writing Le Monde, which embodies an attempt to give a physical theory of the universe, but finding that its publication was likely to bring on him the hostility of the church, and having no desire to pose as a martyr, he abandoned it. The complete manuscript was published in 1664. He then devoted himself to composing a treatise on universal science. This was published at Leyden in 1637, titled The Discourse on Method, and was accompanied with 3 appendices entitled Optics, Meteorology, and Geometry. It is from the last of these that the invention of analytical geometry dates. In 1641 he published a work called Meditations, in which he explained at some length his views of philosophy as sketched out in the Discourse. In 1644 he issued the Principia Philosophiae, as a greater part of which was devoted to physical science, especially the laws of motion and the theory of vortices. In 1647 he received a pension from the French court in honour of his discoveries. He went to Sweden on the invitation of the Queen in 1649 and died a few months later of inflammation of the lungs. In appearance Descartes was a small man with a large head, projecting brow, prominent nose, and black hair coming down to his eyebrows. His voice was feeble. Considering the range of his studies he was by no means widely read, and he despised both learning and art unless something tangible could be extracted therefrom. In disposition he was cold and selfish. He never married and left no descendants, though he had one illegitimate daughter who died young. As to his philosophical theories, it would be sufficient to say that he discussed the same problems which have been debated for the last 2000 years. It is hardly necessary to say that the problems themselves are of great interest, but from the nature of the case no solution ever offered is capable either of proof or disproof, and whenever a philosopher like Descartes believes that he has at last finally settled a question, it has been easy for his successors to point out the fallacy in his assumptions. All that can be effected is to make one explanation somewhat more probable than another. I have read somewhere that philosophy has always been chiefly engaged with the interrelations of God, nature, and man. The earliest philosophers were Greeks, who occupied themselves mainly with the relations between God and nature, and dealt with man separately. The Christian Church was so absorbed in the relation of God to man as to entirely neglect nature.
Finally, modern philosophers concern themselves chiefly with the relations between man and nature. Whether this is a correct historical generalization of the views which have been successfully prevalent, I do not care to discuss here, but the statement as to the scope of modern philosophy marks the limitations of Descartes' writings, and they may be taken as the commencement of the modern school. Descartes' chief contributions to mathematics were his analytical geometry and his theory of vortices, and it is on his researches in connection with the former of these subjects that his reputation rests. Analytical geometry does not consist merely, as sometimes is loosely said, in the application of algebra to geometry, that had been done by Archimedes and many others, and had become the usual method of procedure in the works of the mathematicians of the 16th century. The great advance made by Descartes was that he saw that a point in a plane could be completely determined if its distances, say x and y, formed two fixed lines drawn at right angles in the plane, were given with the convention familiar to us as to the interpretation of positive and negative values, and that though an equation f of xy equals 0 was indeterminate and could be satisfied by an infinite number of values of x and y, yet these values of x and y determine the coordinates of a number of points which form a curve of which the equation f of xy equals 0 expresses some geometrical property, that is, a property true of the curve at every point on it. Descartes assured that a point in space could be similarly determined by three coordinates, but he confined his attention to plane curves. It was at once seen by Descartes and his successors that in order to investigate the properties of a curve it was sufficient to select any characteristic geometrical property as a definition, and to express it by means of an equation between the current coordinates of any point on the curve, that is, to translate the definition into a language of analytical geometry. The equation so obtained contains implicitly every property of the curve, and any particular property can be deduced from it by ordinary algebra without troubling about the geometry of the figure. The points in which the two curves intersect can be determined by finding the roots common to their two equations. I need not go further into details, for nearly everyone to whom the above is intelligible will have read analytical geometry and be able to appreciate the value of its invention. Descartes' Geometrie is divided into three books. The first two of these treat of analytical geometry, and the third includes an analysis of the algebra then current. It is somewhat difficult to follow the reasoning, but the obscurity was intentional and due to the jealousy of Descartes.
Translated, I omitted nothing, says he, except design. I had expected that people who have any math skill would not fail to say that I had not said anything that has not already been said about the coordinate system, but I have hopefully made this topic more intelligible. The first book commences with an explanation of the principles of analytic geometry, and contains a discussion of a certain problem which has been propounded by Pappus in the seventh book of his Synagogue, and of which some particular cases have been considered by Euclid and Apollonius. The general theorem has baffled previous geometricians, and it was in the attempt to solve it that Descartes was led to the invention of analytical geometry. The full enunciation of the problem is rather involved, but the most important case is to find the locus of a point such that the product of the perpendiculars on M given straight lines shall be in a constant ratio to the product of the perpendiculars on N given straight lines. The ancients had solved this geometrically for the case m equals 1, n equals 1, and the case m equals 1, n equals 2. Pappus had further stated that if m equals n equals 2, the locus was a conic, but he gave no proof. Descartes also failed to prove this by pure geometry, but he shewed that the curve was represented by an equation of the second degree, that is, it was a conic section. Subsequently, Newton gave an elegant solution of the problem by pure geometry. In the second book, Descartes divides curves into two classes, namely geometrical and mechanical curves. He defines geometrical curves as those which can be generated by the intersection of two lines each moving parallel to one coordinate axis, with commensurable velocities, by which he meant that dy by dx was an algebraical function, as for example is the case in the ellipse and the cissoid. He calls the curve mechanical when the ratio of the velocities of these lines is incommensurable, by which he meant that dy by dx was a transcendental function, as for example is the case in the cycloid and the quadratrix. Descartes confined his discussion to algebraical curves, and did not treat of the theory of mechanical curves. The classification into algebraical and transcendental curves now usual is due to Newton. Descartes also paid particular attention to the theory of the tangents to curves, as perhaps might be inferred from his system of classification just alluded to. Then the current definition of a tangent at a point was a straight line through the point such that between it and the curve no other straight line could be drawn, i.e. the straight line of closest contact. Descartes proposed to substitute for this that the tangent was the limiting position of the secant. Fermat and at a later date Maclaurin and Lagrange adopted this definition. Barrow, followed by Newton and Leibniz, considered the curve as the limit of an inscribed polygon when the sides become indefinitely small, and stated that the side of the polygon when produced became in the limit a tangent to the curve. Roberval, on the other hand, defined a tangent at a point as the direction of the motion at that instant of a point which was describing the curve. The results are the same whichever definition is selected, but the controversy as to which definition was the correct one was none the less lively. Descartes illustrated his theory by giving the general rule for drawing tangents and normals to a roulette. The method used by Descartes for finding the tangent or normal at any point of a given curve was substantially as follows. He determined the centre and radius of a circle which should cut the curve in two consecutive points there. The tangent to the circle at that point will be the required tangent to the curve. In modern textbooks it is usual to express the condition that two of the points in which a straight line, such as y equals mx plus c, cuts the curve shall coincide with the given point. This enables us to determine m and c, and thus the equation of the tangent there is determined. Descartes, however, did not venture to do this, but selecting a circle as the simplest curve, and one to which we know how to draw a tangent, he so fixed his circle as to make it touch the given curve at the point in question, and thus reduce the problem to drawing a tangent to a circle. I should note in passing that he only applied this method to curves which are symmetrical about an axis, and he took the centre of the circle on the axis. Much of the reasoning in these two books is not easy to follow, but a Latin translation of them with explanatory notes was prepared by F. de Boon, and an edition of this with commentary by F. van Schooten was issued in 1659 and had a wide circulation. The third book of Géométrie contains an analysis of the algebra then current, and it has affected the language of the subject by fixing the custom of employing the letters at the beginning of the alphabet to denote known quantities, and those at the end of the alphabet to denote unknown quantities. Descartes further introduced the system of indices now in use, but I would here remind the reader that the suggestion had been made by previous writers, though it had not been generally adopted, but very likely it was the original on the part of Descartes. I think also that Descartes was the first to realize that his letters might represent any quantities, positive or negative, and that it was sufficient to prove a proposition for one general case compared to the old procedure. In this book he made use of the rule for determining a limit to the number of positive and negative roots of an algebraical equation, which is still known by his name, and introduced the method of indeterminate coefficients for the solution of equations. He believed that he had given a method by which algebraical equations of any order could be solved, but in this he was mistaken. He made use of the method of indeterminate coefficients. Of the other two appendices to the discourse was one devoted to optics. The chief interest of this consists in the statement given of the law of refraction. This appears to have been taken from Snell's work. But not only is there no acknowledgment of the source from which it was obtained, but it is enunciated in such a way so as to lead a careless reader to suppose that it is due to the researches of Descartes. Descartes would seem to have repeated Snell's experiments when in Paris in 1626 or 1627, and it is possible that he subsequently forgot how much he owed to the earlier investigations of Snell. A large part of the optics is devoted to determining the best shape for the lenses of a telescope, but the mechanical difficulties in grinding a surface of glass to a required form are so great as to render these investigations of little practical use. Descartes seemed to have been doubtful whether to regard the rays of light as proceeding from the eye and so to speak touching the object, as the Greeks had done, or as proceeding from the object and so affecting the eye. But since he considered the velocity of light to be infinite, he did not deem the point particularly important. The other appendix on meteors contains an explanation of numerous atmospheric phenomena, including the rainbow. Descartes was unacquainted with the unequal refrangibility of rays of light of different colours, and the explanation of the latter is necessarily incomplete. Descartes' physical theory of the universe, embodying most of the results contained in his earlier and unpublished Le Monde, was given in his Principia 1644 and rests on a metaphysical basis. He commences with a discussion on motion and then lays down 10 laws of nature, of which the first two are almost identical with the first two laws of motion as given by Newton. The remaining 8 laws are inaccurate. He next proceeds to discuss the nature of matter, which he regards as uniform in kind, though there are 3 forms of it. He assumes that the matter of the universe must be in motion, and that the motion must result in a number of vortices. He states that the sun is the centre of an immense whirlpool of this matter, in which the planets float and are swept round like straws in a whirlpool of water. Each planet is supposed to be the centre of a secondary whirlpool by which its satellites are carried. These secondary whirlpools are supposed to produce variations of density in the surrounding medium, which constitute the primary whirlpool, and so cause the planets to move on in ellipses and not circles. All these assumptions are arbitrary and unsupported by any investigation. It is not difficult to prove that on his hypothesis the sun would be in the centre of these ellipses and not at a focus, as Kepler had shewn was the case, and that the weight of a body at every place on the surface of the earth except the equator would act in a direction which was not vertical. But it will be sufficient here to say that Newton, in the second book of his Principia in 1687, considered the theory in detail and shewed that its consequences are not only inconsistent with each of Kepler's laws and with the fundamental laws of mechanics, but are also at variance with the 10 laws of nature assumed by Descartes. Still, in spite of its crudeness and its inherent defects, the theory of vortices marks a fresh era in astronomy, for it was an attempt to explain the phenomenon of the whole universe by the same mechanical laws which experiments shews to be true here on earth. Cavalieri, almost contemporaneously with the publication in 1637 of Descartes' geometry, the principles of the integral calculus, so far as they are concerned with summation, were being worked out in Italy. This was effected by what was called the principle of indivisibles, and was the invention of Cavalieri. It was applied to numerous problems connected with the quadrature of curves and surfaces, the determination of volumes, and the positions of centres of mass, to the complete exclusion of the tedious method of exhaustions used by the Greeks. In principle the methods are the same, but the notation of indivisibles is more concise and convenient. It was in its turn superseded at the beginning of the 18th century by the integral calculus, but its use will be familiar to all mathematicians who have read any commentary on the first section of the first book of Newton's Principia in the application of lemmas 2 and 3 to the determination of areas, volumes, and so on. Bonaventura Cavalieri was born at Milan in 1598 and died at Bologna in November 27, 1647. He became a Jesuit at an early age, and on the recommendation of the order he was in 1629 made professor of mathematics at Bologna, and he continued to occupy the chair there until his death. I have already mentioned Cavalieri's name for the part of the book that he took in introducing the use of logarithms into Italy. He was one of the most influential mathematicians of his time, but his subsequent reputation rests mainly on his invention of the principle of indivisibles. The principle of indivisibles has been used by Kepler in 1604 and 1615 in somewhat crude form. It was first stated by Cavalieri in 1629, but he did not publish his results till 1635. In his early enunciation of the principle in 1635, Cavalieri asserted that a line was made up of an infinite number of points, each without magnitude, and a surface of an infinite number of lines, each without breadth, and a volume of infinite number of surfaces, each without thickness. To meet the objections of Guldinus and others, the statement was recast and in its final form used by the mathematicians of the 17th century. It was published in Cavalieri's 6 Geometrical Exercises in 1647, the third of which is devoted to a defense of the theory. These exercises contain the first rigid demonstration of the properties of Pappus. Cavalieri's work on the subject were reissued with his later corrections in 1653. The method of indivisibles is simply that any magnitude may be divided into an infinite number of small quantities which can be made to bear any required ratios, for example equality, one to the other. The analysis given by Cavalieri is hardly worth quoting except as being one of the first steps taken toward the formation of an infinitesimal calculus. One example will suffice. Suppose it be required to find the area of a right-angled triangle. Let the base contain n points and the other side n times a points. Then the ordinates at the successive points of the base will contain a, 2a, and so on to n times a points. Therefore the number of points in the figure is a plus 2a plus plus na, the sum of which is half n squared a plus 1/2 n times a. Since n is very large, we may neglect the 1/2 na as inconsiderable compared with the 1/2 n squared a, and the area is 1/2 na times n, that is 1/2 the altitude times the base. There is no difficulty in criticizing such a proof, but although the form in which it is presented is indefensible, the substance of it is correct. It would be misleading to give the above as the only specimen of the method of indivisibles, and I therefore quote another example, taken from a later writer, which will fairly illustrate the use of the method when modified and corrected by the method of limits. Let it be required to find the area bounded by the parabola APC, the tangent at A, and any diameter DC. Complete the parallelogram ABCD. Divide AD into n equal parts. Let AM contain r of them and mn be the r plus 1th part. Draw MP and NQ parallel to AB and draw PR parallel to AD. Then, when n becomes indefinitely large, the curvilinear area APCD will be the limit of the sum of all parallelograms like PN. Now the ratio of the area PN to the area BD equals the ratio MP times MN is to DC times AD. But by properties of the parabola, MP over DC equals AM squared over AD squared, which is also equal to r squared over n squared. And mn over AD equals 1 over n. Hence, mp times mn over dc times ad equals r squared over n cubed. Therefore, the area of Pn over the area of BD equals r squared over n cubed. Therefore, ultimately, the area of APCD over area BD equals 1 squared plus 2 squared plus 3 squared plus dot 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 plus n minus 1 squared all over n cubed, which is also equal to 1/6 of n times n minus 1 times 2n minus 1 all over n cubed, which in the limit 1 to 3. It is perhaps worth noticing that Cavalieri and his successors always used the method to find the ratios of two areas, volumes, or magnitudes of the same kind and dimensions. That is, they never thought of an area as containing so many units of area. The idea of comparing a magnitude with a unit of the same kind seems to have been due to Wallis. It is evident that in its direct form the method is applicable to only a few curves. Cavalieri proved that if m be a positive integer, then the limit, when n is infinite, of 1 to the m plus 2 to the m plus 3 to the m dot 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 plus n to the m all over n to the m plus 1 is 1 over m plus 1, which is equivalent to saying that he found the integral to x of x to the m from x equals 0 to x equals 1. He also discussed the quadrature of the hyperbola.
End of chapter 21, part 1. Recording by Paul King, http://pjk.scripts.mit.edu/pkj. Chapter 15, Part 2 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. Pascal. Among the contemporaries of Descartes, none displayed greater natural genius than Pascal, but his reputation rests more on what he might have done than on what he actually effected, as during a considerable part of his life he deemed it his duty to devote his whole time to religious exercises. Blaise Pascal was born at Clermont on June 19, 1623, and died at Paris on August 19, 1662. His father, a local judge at Clermont and himself of some scientific reputation, moved to Paris in 1631, partly to prosecute his own scientific studies, partly to carry on the education of his only son who had already displayed exceptional ability. Pascal was kept at home in order to assure his not being overworked, and with the same object it was directed that his education should be at first confined to the study of languages and should not include any mathematics. This naturally excited the boy's curiosity, and one day, being then 12 years old, he asked in what geometry consisted. His tutor replied that it was the science of constructing exact figures and of determining the proportions between their different parts. Pascal, stimulated no doubt by the injunction against reading it, gave up his playtime to the new study, and in a few weeks had discovered for himself many properties of figures, and in particular the proposition that the sum of the angles of a triangle is equal to two right angles. I have read somewhere, but I cannot lay my hand on the authority, that his proof merely consisted in turning the angular points of a triangular piece of paper over so as to meet in the centre of the inscribed circle. A similar demonstration can be got by turning the angular points over so as to meet at the foot of the perpendicular drawn from the biggest angle to the opposite side. His father, struck by this display of ability, gave him a copy of Euclid's Elements, a book which Pascal read with avidity and soon mastered.
At the age of 14 he was admitted to the weekly meetings of Roberval, Mersenne, Midorge, and other French geometricians, from which the French Academy ultimately sprung, being created by ordinance of Louis XIV on December 22, 1666. At 16 Pascal wrote an essay on conic sections, and in 1641, at the age of 18, he constructed the first arithmetical machine, an instrument which 8 years later he further improved and patented. His correspondence with Fermat about this time shews that he was then turning his attention to analytical geometry and physics. He repeated Torricelli's experiments by which the pressure of the atmosphere could be estimated as a weight, and he confirmed his theory of the cause of barometrical variations by obtaining at the same instant readings at different altitudes on the hill of Puy de Dôme. In 1650, when in the midst of these researches, Pascal suddenly abandoned his favourite pursuits to study religion, or, as he says in his Pensées, to contemplate the greatness and the misery of man, and about the same time he persuaded the younger of his two sisters to enter the Port Royal Society. In 1653 he had to administer his father's estate. He now took up his old life again, and made several experiments on pressure exerted by gases and liquids. It was also about this period that he invented the arithmetical triangle, and together with Fermat created the calculus of probabilities. He was meditating marriage when an accident again turned the current of his thoughts to a religious life. He was driving a four-in-hand on November 23, 1654, when the horses ran away. The two leaders dashed over the parapet of the bridge at Neuilly, and Pascal was only saved by the traces breaking. Always somewhat of a mystic, he considered this a special summons to abandon the world. He wrote an account of the accident on a small piece of parchment, which for the rest of his life he wore next to his heart to perpetually remind him of his covenant, and shortly moved to Port Royal, where he continued to live until his death in 1662. Always delicate, he had injured his health by his incessant study. From the age of 17 or 18 he suffered from insomnia and acute dyspepsia, and at the time of his death was completely worn out. His famous provincial letters directed against the Jesuits and his Pensées were written towards the close of his life, and are the first example of that finished form which is characteristic of the best French literature. The only mathematical work that he produced after retiring to Port Royal was the essay of the cycloid in 1658. He was suffering from sleeplessness and a toothache when the idea occurred to him, and to his surprise his teeth immediately ceased to ache. Regarding this as a divine intimation to proceed with the problem, he worked incessantly for 8 days at it, and completed a tolerably full account of the geometry of the cycloid. I now proceed to consider his mathematical works in rather greater detail. His early essay of the geometry of conics, written in 1639 but not published until 1779, seems to have been founded on the teachings of Desargues. Two of the results are important as well as interesting. The first of these is the theorem known now as Pascal's theorem, namely that if a hexagon is inscribed in a conic, the points of the intersection of the opposite sides will lie in a straight line. The second, which is really due to Desargues, is that if a quadrilateral be inscribed in a conic and a straight line be drawn cutting the sides taken in order in the points A, B, C, and D, and the conic in P and Q, then PA times PC over PD times PD equals QA times QC over QB times QD. Pascal's arithmetical triangle, known today as Pascal's triangle, was written in 1653, but not printed until 1665. The triangle is constructed as in the annexed figure. By the way, the annexed figure shows Pascal's triangle as being kind of on its side by today's standards. a 1 at the apex followed by a 1 1, and then in the third row 1 2 1, and in the fourth row 1 3 3 1, and in the fifth row 1 4 6 4 1. So they will refer to these lines as diagonal lines. The horizontal lines, the way they're depicted, are 1 1 1 1 1, 1 2 3 4 5, 1 3 6 10 15, 1 4 10 20 35, and 1 5 15 35 70. And they have that written in actual rows and columns. So taking the latter description, each horizontal line being formed from the one above it by making every number in it equal to the sum of those above it and to the left of it in the row immediately above. For example, in the fourth line, 20 is equal to 1 plus 3 plus 6 plus 10. Then Pascal's arithmetical triangle to any required order is got by drawing a diagonal downwards from the right to left as in the figure. The numbers are what are now called the figurate numbers. Those in the first line are called the numbers of the first order. Those in the second line, 1, 2, 3, 4, 5, and so on, are called natural numbers or numbers of the second order. Those in the third line, numbers of the third order, and so on. It is easily shown that the mth number in the nth row is m plus n minus 2 factorial divided by m minus 1 factorial times n minus 1 factorial. The numbers in any diagonal give the coefficients of the expansion of a binomial. For example, the figures in the fifth diagonal, namely 1, 4, 6, 4, 1, are the coefficients in the expansion of a plus b raised to the power 4. Pascal used the triangle partly for this purpose, and partly to find the numbers of combinations of m things taken n at a time, which he stated correctly to be n plus 1 times n plus 2 times n plus 3 dot 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 times m divided by m minus n factorial. Perhaps as a mathematician Pascal is best known in connection with his correspondence with Fermat in 1654, in which he laid down the principles of the theory of probabilities. This correspondence arose from a problem proposed by a gamester, the Chevalier de Mer, to Pascal, who communicated it to Fermat. The problem was this. Two players of equal skill want to leave the table before finishing the game. Their scores and the number of points which constitute the game being given, it is desired to find in what proportion should they divide the stakes. Pascal and Fermat agreed on the answer but gave different proofs. The following is a translation of Pascal's solution. That of Fermat is given later. The following is my method for determining the share of each player when, for example, two players play a game of 3 points and each player has staked 32 pistoles. Suppose that the first player had gained 2 points and then the second player 1 point. They now have to play for a point on this condition, that if the first player gain, he takes all the money which is at stake, namely 64 pistoles, while if the second player gain, each player has 2 points, so that they are on terms of equality, and if they leave off playing, each ought to take 32 pistoles. Thus, if the first player gain, then 64 pistoles belong to him, and if he loses, then 32 pistoles belong to him. If therefore the players do not wish to play this game but to separate without playing it, the first player would say to the second, I am certain of 32 pistoles even if I lose this game, and for the other 32 pistoles perhaps I shall have them and perhaps you will have them. The chances are equal. Let us divide these 32 pistoles equally and give me also the 32 pistoles of which I am certain. Thus the first player will have 48 pistoles and the second 16 pistoles. Next, suppose that the first player has gained 2 points and the second player none, and they are about to play for a point. The condition is that if the first player gain this point, he secures the game and takes 64 pistoles, and if the second player gain this point, then the players will be in the situation already examined, in which the first player is entitled to 48 pistoles and the second to 16 pistoles. Thus, if they do not wish to play, the first player would say to the second, if I gain this point, I gain 64 pistoles. If I lose it, I am entitled to 48 pistoles. Give me then the 48 pistoles of which I am certain, and divide the other 16, since our chances of gaining the point are equal. Thus the first player will have 56 pistoles and the second player 8 pistoles. Finally, suppose that the first player had gained 1 point and the second player none. If they proceed to play for a point, the condition is that if the first player gain it, the players will be in the situation first examined, in which the first player is entitled to 56 pistoles. If the first player lose the point, each player has then a point, and each is entitled to 32 pistoles. Give me the 32 pistoles of which I am certain, and divide the remainder of the 56 pistoles equally, that is, divide the 24 pistoles equally. Thus the first player will have the sum of 32 and 12 pistoles, that is 44 pistoles, and consequently the second will have 20 pistoles. Pascal proceeds next to consider the similar problem when the game is won by whomever first obtains m plus n points, and one player has m while the other has n points. The answer is obtained by using the arithmetical triangle, or Pascal's triangle. The general solution, in which the skill of the players is unequal, is given in many modern textbooks on algebra and agrees with Pascal's result, though of course the notation of the latter is different and less convenient. Pascal made a most illegitimate use of the new theory in the 7th chapter of his Pensées. He practically puts his argument that, as the value of eternal happiness must be infinite, then even if the probability of a religious life ensuring eternal happiness be very small, still the expectation, which is measured by the product of the two, must be of sufficient magnitude to make it worth while to be religious. The argument, if worth anything, would apply equally to any religion which has promised eternal happiness to those who accepted its doctrines. If any conclusion may be drawn from the statement, it is the undesirability of applying mathematics to questions of morality, of which some of the data are necessarily outside the range of an exact science. It is only fair to add that no one had more contempt than Pascal for those who changed their opinions according to the prospect of material benefit, and this isolated passage is at variance with the spirit of his writings. The last mathematical work of Pascal was that on the cycloid of 1658. The cycloid is the curve traced out by the point on the circumference of a circular hoop which rolls along a straight line. Galileo in 1630 had been the first to call attention to this curve, and had suggested that the arches of bridges should be built in the form of it. It is a graceful curve, but the only bridge with a cycloidal arch of which I have heard is the one built by Essex in the grounds of Trinity College at Cambridge. 4 years later, in 1634, Roberval found the area of the cycloid. Descartes thought little of this solution and defied him to find its tangents, the same challenge also being sent to Fermat, who at once solved the problem. Several questions connected with the curve and with the surface and volume generated by its revolution about its axis, base, or the tangent at its vertex were then proposed by various mathematicians. These and some analogous questions, as well as the positions of the centres of mass of the solids there formed, were solved by Pascal in 1658, and the results were issued as a challenge to the world. Wallis succeeded in solving all the questions except those connected with the centre of mass. Pascal's own solutions were effected by the method of indivisibles, and are similar to those which a modern mathematician would give by the aid of the integral calculus. He obtained by summation what are equivalent to the following integrals: the integral of sine phi d phi, also the integral of sine squared phi d phi, and also the integral of phi times sine phi d phi, one limit being either 0 or half pi. He also investigated the geometry of the Archimedean spiral. These researches, according to D'Alembert, form a connecting link between the geometry of Archimedes and the infinitesimal calculus of Newton. Wallis. John Wallis was born at Ashford on November 22, 1616, and died at Oxford on October 28, 1703. When 15 years old he happened to see a book on arithmetic in the hands of his brother. Struck with curiosity at the odd signs and symbols in it, he borrowed the book, and in a fortnight mastered the subject. It was intended that he should be a doctor, and he was sent to Emmanuel College, Cambridge. While there he kept an act on the doctrine of the circulation of the blood. This is said to have been the first occasion in Europe on which this theory was publicly maintained in disputation. His interests, however, centred on mathematics. He was elected to a fellowship at Queen's College, Cambridge, and subsequently took orders, but on the whole adhered to the Puritan party, whom he rendered great assistance in deciphering the royalist despatches. He however joined the moderate Presbyterians in signing the remonstrance against the execution of Charles I, by which he incurred the lasting hostility of the Independents. In spite of their opposition, he was appointed in 1649 to the Savilian chair of geometry at Oxford, where he lived until his death on October 28, 1703. Besides his mathematical works, he wrote on theology, logic, and philosophy, and was the first to devise a system for teaching deaf mutes. I confine myself to a few notes on his more important mathematical writings. They are notable partly for the introduction of the use of infinite series as an ordinary part of analysis, and partly for the fact that they revealed and explained to all students the principles of those new methods which distinguish modern from classical mathematics. The most important of Wallis's works was his Arithmetica Infinitorum, which was published in 1656. In this treatise the methods of analysis of Descartes and Cavalieri were systematized and greatly extended, but their logical exposition is open to criticism. It at once became the standard book on the subject, and is constantly referred to by subsequent writers. It is prefaced by a short tract on conic sections, which was subsequently expanded into a separate treatise. He commences by proving the law of indices, shews that x to the 0, x to the minus 1, x to the minus 2, and so on represent 1, 1 over x squared, and so on. That x to the power of 1/2 represents the square root of x. That x to the power of 2/3 represents the cube root of x squared, and that generally that x to the exponent minus n represents the reciprocal of x to the power n, and that x to the p over q represents the qth root of x to the p. Leaving the numerous algebraical applications of this discovery, he next proceeds to find by the method of indivisibles the area enclosed between the curve y equals x to the m, the axis of x, and any ordinate x equals h, and he proves that the ratio of this area is equal to that of the parallelogram on the same base and of the same altitude, and is equal to the ratio 1 over m plus 1. He apparently assumed that the same result would be true also for the curve y equals ax raised to the power m, where a is any constant and m is any number positive or negative. But he only discusses the case of which the parabola of m equals 2, and that of the hyperbola in which m equals minus 1. In the latter case his interpretation of the result is incorrect. He then shews that similar results might be written down for any curve of the form y equals the sum of ax raised to the power m, and hence that if the ordinate y on a curve can be expanded in powers of the abscissa x,
its quadrature can be determined. Thus he said that if the equation of a curve were y equals x to the 0 plus x to the 1 plus x squared and so on, its area would be x plus 1/2 x squared plus 1/3 x cubed and so on. He then applies this to the quadrature of the curves y equals quantity x minus x squared to the power 0, y equals the quantity x minus x squared to the power 1, y equals x minus x squared quantity to the power 2, y equals quantity x minus x squared to the power 3 and so on, taken between the limits x equals 0 and x equals 1, and shows that the areas are respectively 1, 1 over 6, 1 over 30, 1 over 140 and so on. He next considers the curve of the form y equals x to the power 1 over m and establishes the theorem that the area bounded by the curve, the axis of x, and the ordinate x equals 1 is to the area of the rectangle on the same base and the same altitude as m over m plus 1. This is equivalent to finding the value of the integral from 0 to 1 of x raised to the power 1 over m dx. He illustrates this by the parabola in which m equals 2. He states, but does not prove, that the corresponding result of the curve of the form y equals x raised to the p over q. This work contains also one of the earliest investigations of the formation and properties of continued fractions, a discussion that was suggested by Bruckner's use of these fractions. Wallis shewed considerable ingenuity in reducing the equations of curves to the forms given above, but as he was unacquainted with the binomial theorem, he could not effect the quadrature of the circle whose equation is y equals quantity x minus x squared to the half, since he was unable to expand this in powers of x. He laid down, however, the principle of interpolation. Thus, as the ordinate of the circle y equals x minus x squared raised to the half is a geometrical mean between the ordinate of the curve y equals quantity x minus x squared raised to the 0 and y equals quantity x minus x squared raised to the 1, it might be supposed that as an approximation the area of the semicircle, the integral from 0 to 1 of quantity x minus x squared dx, which is 1/8 pi, might be taken as the geometrical mean between the values of the integral from 0 to 1 of quantity x minus x squared raised to the 0 dx and the integral of 0 to 1 of quantity x minus x squared raised to the 1 dx, that is, the values 1 and 1/6. This is equivalent to taking 4 multiplied by the root of 2/3, or 3.26 approximately, as the value of pi. But Wallis argued, we have in fact a series 1, 1/6, 1 over 30, 1 over 140 and so on, and therefore the term interpolated between 1 and 1/6 ought to be so chosen as to obey the law of the series. This, by an elaborate method which I need not describe in detail, leads to a value for the interpolated term which is equivalent to taking pi equals 2 times 2 over 1 times 2/3 times 4/3 times 4/5 times 6/5 times 6 over 7 times 8 over 7 times 8 over 9 and so on. The subsequent mathematicians of the 17th century constantly used interpolation to obtain results which we should attempt to obtain by direct analysis. A few years later, in 1659, Wallis published a tract containing the solution of the problems on the cycloid which had been proposed by Pascal. In this he incidentally explained how the principles laid down in his Arithmetica Infinitorum could be used for the rectification of algebraic curves, and gave a solution of the problem to rectify the semicubal parabola x cubed equals ay squared, which had been discovered in 1657 by his pupil William Neal. This was the first case in which the length of a curved line was determined by mathematics, and since all attempts to rectify the ellipse and the hyperbola had been necessarily ineffectual,
It had been previously supposed that no curves could be rectified, as indeed Descartes had definitely asserted to be the case. The cycloid was the second curve rectified, and this was done by Wren in 1658. Early in 1658 a similar discovery, independent of that of Nile, was made by Van Heuraet, and this was published by Van Schooten in his edition of Descartes Geometria in 1659. Van Heuraet's method is as follows. He supposes the curve to be referred to rectangular axes. If this be so, and if xy be the coordinates of any point on it, and n the length of the normal, and if another point whose coordinates are x nu to be taken such that nu to h equals the ratio n to y, where h is a constant, then if ds be the element of the length of the required curve, then we have by similar triangles the ratio ds to dx equals n to y. Therefore HDS equals nu dx. Hence, if the area of the locus of the point x nu can be found, the first curve can be rectified. In this way Van Heuraet effected the rectification of the curve y cubed equals ax squared, and added that the rectification of the parabola y squared equals ax is impossible, since it requires the quadrature of the hyperbola. The solutions given by Nile and Wallis are somewhat similar to that given by Van Heuraet, but no general rule is enunciated, and the analysis is clumsy. A third method was suggested by Fermat in 1660, but it is both inelegant and laborious. In 1665 Wallis published the first systematic treatise on analytical conic sections. I have already mentioned that the Geometrie of Descartes is both difficult and obscure, and to many of his contemporaries to whom the method was new it must have been incomprehensible. Wallis made the method intelligible to all mathematicians. This is the earliest book in which these curves are considered and defined as curves of the second degree, and not as sections of a cone on a circular base. The theory of the collision of bodies was propounded by the Royal Society in 1668 for the consideration of mathematicians. Wallis, Wren, and Huygens sent correct and similar solutions, all depending on what is now called the conservation of momentum. But while Wren and Huygens confined their theory to perfectly elastic bodies, Wallis considered also imperfectly elastic bodies. This was followed in 1669 by a work on statics, centers of gravity, and in 1670 by one on dynamics. These provide a convenient synopsis of what was then known on the subject. In 1685 Wallis published an algebra preceded by a historical account of the development of the subject, which contains a great deal of valuable information. The second edition, issued in 1693 and forming the second volume of his opera, is considerably enlarged. This algebra is noteworthy as containing the first systematic use of formulae. A given magnitude is here represented by the numerical ratio which it bears to the unit of the same kind of magnitude. Thus when Wallis wants to compare two lengths he regards each as containing so many units of length. This perhaps will be made clearer if I say that the relation between the space described in any time by a particle moving with uniform velocity would be denoted by Wallis by the formula s equals vt, where s is the number representing the ratio of the space described to the unit of length, while previous writers would have denoted the same relation by stating what is equivalent to the proportion s1 over s2 equals v1t1 over v2t2. See for example Newton's Principia, book 1, section 1, lemma 10 or 11. It is curious to note that Wallis rejected as absurd the now usual idea of a negative number as being less than nothing, but accepted the view that it is something greater than infinity. The latter opinion may be right and consistent with the former, but it is hardly a more simple one. Fermat. While Descartes was laying down the foundation of analytical geometry, the same subject was occupying the attention of another and hardly less distinguished Frenchman. This was Fermat. Pierre de Fermat, who was born near Montauban in 1601 and died at Castres in January 12, 1665, was the son of a leather merchant. He was educated at home. In 1631 he obtained the post of councillor for the local parliament at Toulouse, and he discharged the duties of the office with scrupulous accuracy and fidelity. There, devoting most of his leisure to mathematics, he spent the remainder of his life, a life which, but for a somewhat acrimonious dispute with Descartes on the validity of analysis used by the latter, was unruffled by any event which calls for special notice. The dispute was due chiefly to the obscurity of Descartes, but the tact and courtesy of Fermat brought it to a friendly conclusion. Fermat was a good scholar and amused himself by conjecturally restoring the work of Apollonius on plane loci. Except for a few isolated papers, Fermat published nothing in his lifetime, and gave no systematic exposition of his methods. Some of the most striking of his results are found after his death on loose sheets of paper written on the margins of works which he had read and annotated, and are unaccompanied by any proof. It is thus somewhat difficult to estimate the dates and originality of his work. After his death his papers and correspondences were printed by his nephew at Toulouse in 2 volumes, 1670 and 1679. A summary of it with notes was published by Brazin in Toulouse in 1853, and a reprint of it was issued at Berlin in 1861. A new edition is now being issued by the French government, which will include some letters on his discoveries and methods in the theory of numbers recently found at Leyden by M. Charles Henry. Fermat was constitutionally modest and retiring, and does not seem to have intended his papers to be published. It is probable that he revised his notes as occasion required, and that his published works represent the final form of his researches, and therefore cannot be dated much earlier than 1660. I shall consider separately: 1. His investigations into the theory of numbers; 2. His use in geometry of analysis and of infinitesimals; and 3. His method of treating questions of probability. 1. The theory of numbers appears to have been the favourite study of Fermat. He prepared an edition of Diophantus, and the notes and comments thereon contain numerous theorems of considerable elegance. This forms the first of 2 volumes of his works. Most of the proofs of Fermat are lost, and it is possible that some of them were not rigorous, an induction by analogy and the intuition of genius sufficing to lead him to correct results. The following examples will illustrate these investigations. A. If p be prime and a be a prime to p, then a to the power of p minus 1 subtract 1 is divisible by p. That is, when you subtract 1 from a to the power of p minus 1, this is equivalent to 0 modulus p. A proof of this, first, given by Euler, is well known. A more general theorem, that of a to the power of phi of n, subtracting 1 from that result, is equivalent to 0 mod n, where a is prime to n and phi of n is the number of integers less than n and prime to it. B. A prime greater than 2 can be expressed as the difference of 2 square integers in one and only one way. Fermat's proof is as follows. Let n be the prime and suppose it equal to x squared minus y squared, that is, to the product x plus y times x minus y. Now by hypothesis the only integral factors of n are n in unity, hence x plus y equals n and x minus y equals 1. Solving these equations we get x equals a half times n plus 1 and y equals a half times n minus 1. C.
He gave a proof of the statement by Diophantus, quoted above, that the sum of the squares of two integers cannot be of the form 4n-1, and that he added a corollary which I take to mean that it is impossible that the product of a square and a prime of the form 4n-1, even if multiplied by a number prime to the latter, can be either a square or the sum of two squares. For example, 44 is a multiple of 11, which is of the form 4 times 3 minus 1. By 4, hence it cannot be expressed as a sum of two squares. He also stated that a number of the form a squared plus b squared, where a is prime to b, cannot be divided by a prime of the form 4n-1. D. Every prime of the form 4n plus 1 is expressible, and that in one way only, as a sum of two squares. This problem was first solved by Euler, who shewed that the number of the form 2 to the power m times 4n-1 can be always expressed as a sum of two squares. E. If a, b, c are integers such that a squared plus b squared equals c squared, then a times b cannot be a square. Lagrange gave a solution of this. F. The determination of a number x such that x squared n plus 1 may be a square where n is a given integer which is not a square. G. There is only one integral solution of the equation x squared plus 2 equals y cubed, and there are only two integral solutions of the equation x squared plus 4 equals y cubed. The required solution are evidently for the first equation x equals 5 and for the second equation x equals 2 and x equals 11. This question was issued as a challenge to the English mathematicians Wallis and Digby. H. No integral values of x, y, z can be found to satisfy the equation x to the n plus y to the n equals z to the n, if n be an integer greater than 2. This proposition, known as Fermat's last theorem, has acquired extraordinary celebrity from the fact that no general demonstration of it has ever been given, but there is no reason to doubt that it is true. Probably Fermat discovered its truth for the case of n equals 3, and then for the case of n equals 4. His proof for the former of these cases is lost, but that for the latter is extant, and a similar proof for the case of n equals 3 was given by Euler. These proofs depend on shewing that if three integral values of x, y, z can be found which satisfy the equation, then it will be possible to find three and other similar integers which satisfy it. In this way, finally, we shew that the equation must be satisfied by three values which obviously do not satisfy it. Thus no integral solution is possible. It would seem that this method is inapplicable to any cases except those of n equals 3 and n equals 4. Fermat's discovery of the general theorem was made later. An easy demonstration can be given on the assumption that a number can be resolved into prime or complex factors in one and only one way. The assumption has been made by some writers, but it is not universally true. It is possible that Fermat made some such supposition, though it is perhaps more likely that he discovered a rigorous demonstration. In 1823 Legendre obtained a proof for the case of n equals 5. In 1832 Lejeune de Richelieu gave one for n equals 14, and in 1840 Lamé and Lebesgue gave proofs for n equals 7. The proposition appears to be true universally, and in 1849 Kummer, by means of ideal primes, proved it to be so for all numbers except, if any, which satisfy three conditions. It is not certain whether any number can be found to satisfy these conditions, but there is no number less than 100 which does so. The proof is complicated and difficult, and there can be no doubt is based on the considerations unknown to Fermat. I may add that, to prove the truth of the proposition where n is greater than 4, it is obviously sufficient to confine ourselves to cases where n is a prime, and the first step in Kummer's demonstration is to shew that in such cases one of the numbers xyz must be divisible by n.
A letter exists now in the University at Leyden which gave an idea of Fermat's methods. The letter is undated, but it would appear that, at the time Fermat wrote it, he had proved the proposition h above only for the case when n equals 3. 2. I next proceed to mention Fermat's use in geometry of analysis and of infinitesimals. It would seem from his correspondence that he had thought out the principles of analytic geometry for himself before reading Descartes' Géométrie, and had realized that from the equation, or as he calls it, the specific property of a curve, all its properties could be deduced. His extant papers on geometry deal however mainly with the application of infinitesimals to the determination of the tangents to curves, and to the quadrature of curves, and to the questions of maxima and minima. Probably these papers are a revision of his original manuscripts, which he destroyed, and were written about 1663, but there is no doubt that he was in possession of the general idea of his methods for finding maxima and minima as early as 1628 and 1629. He obtained the subtangent to the ellipse, cycloid, cissoid, conchoid, and quadratrix by making the ordinates of the curve and a straight line the same for 2 points whose abscissae were x and x minus e. But there is nothing to indicate that he was aware that the process was general, and though in the course of his work he used the principle, it is probable that he never separated it, so to speak, from the symbols of the particular problem he was considering. The first definite statement of the method was due to Barrow and was published in 1669. Fermat also obtained the areas of parabolas and hyperbolas of any order, and determined the centre of mass of a few simple curves and of a paraboloid of revolution. As an example of his method of solving these equations, I will quote his solution of the problem to find the area between the parabola y cubed equals px squared on the axis of x and the line x equals a. He says that if the several ordinates at the points for which x is equal to a times the quantity 1 minus e, and a times the quantity 1 minus e to the power of 2, and so on, be drawn, the area will be split into a number of little rectangles whose areas are respectively ae times pa squared to the power of 1/3, ae times 1 minus e multiplied by the quantity pa squared times the quantity 1 minus e squared, all under a cube root. The sum of these is p to the 1/3 a to the 5/3 times e divided by the quantity 1 minus e to the 5/3, and by a subsidiary proposition, for of course he was not acquainted with the binomial theorem, he finds the limit of this when e vanishes to be 3/5 p to the 1/3 a to the 5/3. The theorems last mentioned were published only after his death, and probably they were not written till he had read the works of Cavalieri and Wallis. Kepler had remarked that the values of a function immediately adjacent to and on either side of a maximum or minimum value must be equal. Fermat applied this principle to a few examples. Thus, to find the maximum value of x times the quantity a minus x, his method is essentially equivalent to taking a consecutive value of x, namely x minus e, where e is very small, and putting x times quantity a minus x equal to quantity x minus e multiplied by the quantity a minus x plus e. Simplifying and ultimately putting e equals 0, we get x equals half a. This value of x makes the given expression a maximum. 3. Fermat must share with Pascal the honour of having founded the theory of probabilities. I have already mentioned the problem proposed to Pascal and which he communicated to Fermat and have there given Pascal's solution. Fermat's solution depends on the theory of combinations and will be sufficiently illustrated by the following example, the substance of which was taken from a letter dated August 24, 1654, which occurs in the correspondence with Pascal. Fermat discusses the case of two players, and supposes that the first wants 2 points to win and the second 3 points. The game will be then certainly decided in the course of 4 trials. Take the letters A and B and write down all the combinations that can be formed of 4 letters. These combinations are the following, 16 in all. Now let big A denote the player who wants 2 points and big B denote the player who wants 3 points. Then in these 16 combinations, every combination in which A occurs twice or oftener represents a case favorable to big A, and every combination in which little b occurs 3 times or oftener represents a case favorable to player big B. Thus, on counting them, it will be found that there will be 11 cases favorable to A and 5 cases favorable to B, and since these cases are all equally likely, A's chance of winning the game is to B's chances as 11 is to 5. The only other problem on this subject which, as far as I know, attracted the attention of Fermat was also proposed to him by Pascal and was as follows. A person undertakes to throw a 6 with a die in 8 throws. Supposing him to have made 3 throws without success, what proportion of the stake should he be allowed to take on condition of giving up his 4th throw? Fermat's reasoning is as follows. The chance of success is 1 in 6, so that he should be allowed to take 1/6 of the stake on condition of giving up his throw. But if we wish to estimate the value of the 4th throw before any throw is made, then the first throw is worth 1/6 of the stake. The second is worth 1/6 of what remains, that is 5/36 of the stake. The third throw is worth 1/6 of what now remains, that is 25 over 216 of the stake. The fourth throw is worth 1/6 of what now remains, and that is 125 over 1296 of the stake. Fermat does not seem to have carried the matter much further, but his correspondence with Pascal shews that his views on the fundamental principles of the subject were accurate. Those of Pascal were not altogether correct. Fermat's reputation is quite unique in the history of science. The problems on numbers which he had proposed long defied all efforts to solve them, and many of them yielded only to the skill of Euler. One still remains unsolved. This extraordinary achievement has overshadowed his other work, but in fact it is all of the highest order of excellence, and we can only regret that he thought fit to write so little. End of part 2. Read by Paul King. pjk.scripts.mit.edu/pkj. Chapter 15, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by Rouse. History of mathematics from Descartes to Huygens circa 1635 to 1675. Part 3.
Huygens. Christian Huygens was born at The Hague on April 14, 1629, and died in the same town on June 8, 1695. He generally wrote his name as Huygens, Hugens, but I follow the usual custom in spelling it as Huygens. It is also sometimes written as Huyghens. His life was uneventful and is a mere record of the dates of his various works. In 1651 he published an essay in which he shewed the fallacy in a system of quadratures proposed by Gregoire de Saint Vincent, who was well versed in the geometry of the Greeks, but had not grasped the essential points in the more modern methods. This essay was followed by tracts on the quadrature of the conics and the approximate rectification of the circle. In 1654 his attention was directed to the improvement of the telescope. In conjunction with his brother he devised a new and better way of grinding and polishing lenses. As a result of these improvements he was able, during the following 2 years, 1655 and 1656, to resolve numerous astronomical questions, as for example the nature of Saturn's appendage. His astronomical observations required some exact means of measuring time, and he was thus led in 1656 to invent the pendulum clock, as described in his tract on Horologium, 1658. The timepieces previously in use had been balance clocks. In the year 1657 Huygens wrote a small work on the calculus of probabilities founded on the correspondence of Pascal and Fermat. He spent a couple of years in England about this time. His reputation was now so great that in 1665 Louis XIV offered him a pension if he would live in Paris, which accordingly then became his place of residence. In 1668 he sent to the Royal Society of London, in answer to a problem they had proposed, a memoir in which, simultaneously with Wallis and Wren, he proved by experiment that the momentum in a certain direction before the collision of two bodies is equal to the momentum in that direction after the collision. This was one of the points in mechanics on which Descartes had been mistaken. The most important of Huygens's work was in his Horologium Oscillatorium, published in Paris in 1673. The first chapter is devoted to the pendulum clocks. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. Amongst other propositions he shews that the cycloid is tautochronous. In the third chapter he defines evolutes and involutes, proves some of their more elementary properties, and illustrates his methods by finding the evolutes of the cycloid and the parabola. These are the earliest instances in which the envelope of a moving line is determined. In the fourth chapter he solves the problem of the compound pendulum and shews that the centres of oscillation and suspension are interchangeable. In the fifth and last chapter he discusses again the theory of clocks, points out that if the bob of the pendulum were made by means of cycloidal checks to oscillate in a cycloid, the oscillations would be isochronous, and finishes by shewing that the centrifugal force on a body which moves in a circle of radius r with uniform velocity v varies directly as v squared and inversely as r. This work contains the first attempt to apply dynamics to bodies of finite size and not merely to particles. In 1675 Huygens proposed to regulate the motion of watches by use of the balance spring, in the theory of which he had been perhaps anticipated in a somewhat ambiguous and incomplete statement made by Hooke in 1658. Watches or portable clocks had been invented early in the 16th century, and by the end of that century were not very uncommon, but they were clumsy and unreliable, being driven by a mainspring and regulated by a conical pulley and verge escapement. Moreover, until 1687 they had only one hand. The first watch whose motion was regulated by a balanced spring was made at Paris under Huygens directions, and presented by him to Louis XIV. The increasing intolerance of the Catholics led to his return to Holland in 1681, and after the revocation of the Edict of Nantes he refused to hold any further communication with France. He now devoted himself to the construction of lenses of enormous focal length. Of these, 3 of focal length 123 feet, 180 feet, and 210 feet was subsequently given by him to the Royal Society in London, in whose possession they still remain. It was about this time that he discovered the achromatic eyepiece for a telescope, which is known by his name. In 1689 he came from Holland to England in order to make the acquaintance of Newton, whose Principia had been published in 1687, the extraordinary merits of which Huygens had at once recognized. On his return in 1690 Huygens published his treatise on light, in which the undulatory theory was expounded and explained. Most of this had been written as early as 1678. The general idea of the theory had been suggested by Robert Hooke in 1664, but he had not investigated its consequences in any detail. This publication falls outside the years considered in this chapter, but here it may be briefly said that according to the wave or undulatory theory, space is filled with an extremely rare ether, and light is caused by a series of waves or vibrations in this ether, which are set in motion by the pulsations of the luminous body. From this hypothesis Huygens deduced that the laws of reflection and refraction explain the phenomenon of double refraction, and gave a construction for the extraordinary ray in biaxial crystals, while he found by experiment the chief phenomenon of polarization. The immense reputation and unrivaled powers of Newton led to the disbelief in the theory which he rejected, and to the general adoption of Newton's emission theory. But it should be noted that Huygens' explanation of some phenomena, such as the colours of thin plates, was inconsistent with the results of experiments, nor was it until Young and Wollaston at the beginning of this century revived the undulatory theory and modified some of its details, and Fresnel elaborated their views, that its acceptance could be fully justified. Besides these works, Huygens took part in most of the controversies and challenges which then played so large a part in the mathematical world, and wrote several minor tracts. In one of these he investigated the form and properties of the quaternary. In another he stated in general terms the rule for finding maxima and minima of which Fermat had made use, and shewed that the subtangent of an algebraical curve fxy equals 0 was equal to y fy by fx, where fy is the derivative of fxy regarded as a function of y. In some posthumous works issued at Leyden in 1703 he further shewed how from the focal lengths of the component lenses the magnifying power of a telescope could be determined, and explained some of the phenomena connected with halos and parhelia. I should add that almost all of his demonstrations, like those of Newton, are rigidly geometrical, and he would seem to have made no use of the differential or fluxional calculus, though he admitted the validity of the methods used therein. Thus, even when first written, his works were expressed in an archaic language, and perhaps received less attention than their intrinsic merits deserved. I have now traced the development of mathematics for a period which we may take roughly as dating from 1635 to 1675 under the influence of Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens. The life of Newton partly overlaps this period. His works and influence are considered in the next chapter. I may dismiss the remaining mathematicians of this time, whom I dare to mention with comparatively slight notice. The following is an alphabetical list of the more remarkable among them. The dates given to those are the birth and death of the mathematician to whose name they are appended. Bachet, 1581 to 1638. Barrow, 1630 to 1677. Brochner, 1620 to 1684. Collins, 1625 to 1683. Coursier, 1604 to 1692. Debonne, 1601 to 1652. De la Lubert, 1600 to 1664. Frenicle, 1605 to 1670. Gregory, 1638 to 1675. Hooke, 1635 to 1703. Hood, 1633 to 1704. Kinckhuysen, 1630 to 1679. Mercator, 1620 to 1687. Mersenne, 1588 to 1648. Midorge, 1585 to 1647. Pell, 1610 to 1685. Ritchie, 1619 to 1692. Roberval, 1602 to 1675. Roemer, 1644 to 1710. St. Vincent, 1584 to 1667. Sluys, 1622 to 1685. Torricelli, 1608 to 1647. Turnhausen, 1631 to 1708. Van Schooten died in 1661. And Wren, 1632 to 1723. In the following notes I have arranged the above-mentioned mathematicians so that as far as possible their chief contributions shall come in chronological order. Bachet. Claude Gaspard Bachet de Mézirac was born in Bourg in 1581 and died in 1638. He wrote the Problème Plaisant, 1612, second and enlarged edition, 1624, which contains an interesting collection of arithmetical tricks and questions, many of which are quoted in chapter 1 of my Mathematical Recreations and Problems, also Les Éléments arithmétiques, which exists in manuscript, and a translation of arithmetic by Diophantus. Bachet was the earliest writer who discussed the solution of indeterminate equations by means of continued fractions. Midorge. Claude Midorge, born in Paris in 1585 and died in 1647, belonged to a distinguished family of the robe, and was himself a councillor at Châtelet, then treasurer to the local parliament at Amiens. He published some works on optics, of which one issued in 1631 is extant, and in 1641 a treatise on conic sections. He also left a manuscript containing solutions of over 1,000 geometrical problems, many of which are said to be ingenious. The enunciations were published by M. Charles Henry in 1882. Mersenne. Marin Mersenne, born in 1588 and died in Paris in 1648, was a Franciscan friar who made it his business to be acquainted and correspond with the French mathematicians of that date and many of their foreign contemporaries. In 1634 he published a translation of Galileo's Mechanics. In 1644 he issued his Cogitata Physico-Mathematica, by which he is best known, containing an account of some experiments in physics. He also wrote a synopsis of mathematics, which was printed in 1664. The preface to the Cogitata contains a statement, probably due to Fermat, that in order that 2p minus 1 may be prime, the only values of p not greater than 257 which are possible are 1, 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257, to which list Herr Seelhoff has shewn we must add the number 61. With this addition, the statement has been verified for all except 23 values of p, namely 61, 71, 89, 101, 103, 107, 109, 127, 137, 139, 149, 157, 163, 167, 173, 181, 193, 197, 199, 227, 229, 241, and 257. Of these values, Mersenne asserted that p equals 67, p equals 127, and p equals 257 make 2 to the exponent p minus 1 a prime, and that the other values make 2p minus 1 a composite number. It is most likely that these results are particular cases of some general theorem on the subject which remains to be discovered. The number 2 to the power 61 minus 1 contains 19 digits, and is the highest number at present known to be prime. Its value in digits is 2305843009213693951. The theory of perfect numbers depends directly on that of Mersenne's numbers. It is probable that all perfect numbers are included in the formula 2 to the power of p minus 1, as opposed to -1 plus 2 to the p, where -1 plus 2 to the p is prime. Euclid proved that any number of this form is perfect. Euler shewed that the formula includes all even perfect numbers, and there is reason to believe, though a rigid demonstration is wanting, that an odd number cannot be perfect. If we assume that the last of these statements is true, then every perfect number is of the above form. Thus if p equals 2, 3, 5, 7, 13, 17, 19, 31, 61, then by Mersenne's rule the corresponding values of -1 plus 2 to the p are prime. They are 3, 7, 31, 127, 8191, 131,071, 524,287, 2,147,483,647, and finally 2,305,943,693,951. And the corresponding perfect numbers are 6, 28, 496, 8,128, 33,550,336, 8,589,869,056, 137,438,691,328. Next is 2,305,843,000,000, 8,139,952,128. And finally 2 undecillion, 658 decillion, 455 nonillion, 991 octillion, 569 septillion, 831 hexillion, 744 quintillion, 654 quadrillion, 692 trillion, 615 billion, 953,842,176. De Beaume. Florimond de Beaume was born in Blois in 1601 and died in 1652. Wrote explanatory notes on the obscure and difficult analytical geometry of Descartes. He also discussed the superior and inferior limits to the roots of an equation. This was not published till 1659. Roberval.
Gilles Personnier de Roberval, born at Roberval in 1602 and died at Paris in 1675, described himself from the place of his birth as de Roberval, a seigneurial title to which he had no right. He discussed the nature of the tangents to the curves, solved some of the easier questions connected with the cycloid, generalized Archimedes' theorems on the spiral, and wrote on mechanics and the method of indivisibles, which he rendered more precise and logical. He was a professor in the University of Paris and in correspondence with nearly all of the leading mathematicians of his time. A complete edition of his works was included in the old Memoir of the Academy of Sciences, published in 1693. Van Schooten. Franz van Schooten, to whom we owe an edition of Vieta's works, succeeded his father, who had taught mathematics to Huygens, Hood, and Sluys as a professor at Leyden in 1646. He brought out in 1659 a Latin translation of Descartes' Geometrie, and in 1657 a collection of mathematical exercises in which he recommended the use of coordinates in space of 3 dimensions. He died in 1661. Saint Vincent. Gregoire de Saint Vincent, a Jesuit, born at Bruges in 1584 and died at Ghent in 1667, discovered the expansion of the logarithm of 1 plus x in ascending powers of x. Although a circle squarer, he is worthy of mention for the numerous theorems of interest which he discovered in his search after the impossible, and Montucla ingeniously remarks that no one ever squared the circle with so much ability except for his principal object with so much success. He wrote 2 books on the subject, one published in 1647 and the other in 1668, which cover some 2,000 or 3,000 closely printed pages. The fallacy in the quadrature was pointed out by Huygens. In the former work he had used indivisibles. An earlier work entitled Theoremata Mathematica, published in 1624, contains a clear account of the method of exhaustions which is applied to several quadratures, notably that of the hyperbola. For further details of St. Vincent's life and works, see L.A.J. Quetelet, Histoire des sciences chez les Blages, Brussels, 1866. Torricelli. Evangelista Torricelli, born at Faenza in October 15, 1608, died at Florence in 1647, wrote on the quadrature of the cycloid and conics, the theory of the barometer, the value of gravity found by observing the motion of 2 weights connected by a string passing over a fixed pulley, the theory of projectiles, and the motion of fluids. His mathematical writings were published in 1644. Hood. Johann Hood, a burgomaster of Amsterdam, was born there in 1633 and died in the same town in 1704. He wrote 2 tracts in 1659. One was on the reduction of equations which have equal roots. In the other he stated what is equivalent to the proposition that if f of xy equals 0 be the algebraical equation of a curve, then its subtangent is negative y of the partial derivative of x with respect to y divided by the partial derivative of x with respect to x. But being ignorant of the notation of the calculus, his enunciation is involved. Frenicle. Bernard Frenicle de Bessy, born in Paris circa 1605 and died in 1670, wrote numerous papers on combinations and on the theory of numbers, and also on magic squares. It may be interesting to add that he challenged Huygens to solve the following system of equations in integers: x squared plus y squared equals z squared, x squared equals u squared plus v squared, and x minus y equals u minus v. A solution was given by M. Pepin in 1880. Frenicle's miscellaneous works, edited by De la Hare, was published in the Memoires de l'Académie, volume 5, 1691. De Laloubert. Antoine de Laloubert, a Jesuit born in Languedoc in 1600, died at Toulouse in 1664, is chiefly celebrated for an incorrect solution of Pascal's problems on the cycloid, which he gave in 1660, but he has a better claim to distinction in having been the first mathematician to study the properties of the helix. Kinckhuysen. Gerard Kinckhuysen, born in Holland in 1630 and died in 1679, wrote in 1660 a textbook on analytical conics, in 1661 an algebra, and in 1669 formed a collection of geometrical problems solved by analytical geometry. Coursier. Pierre Coursier, a Jesuit, born at Troyes in 1604 and died in Auxerre in 1692, wrote on the curves of intersection of a sphere with a cylinder or cone, also on spherical polygons. The latter work was published in 1663. Ricci. Michel-Ange Ricci, born in 1619, made a cardinal in 1681 and died in Rome in 1692, wrote in 1666 a treatise in which he solved by Greek geometry those problems on maxima and minima and on tangents to curves which had been considered by Descartes, Pascal, and Fermat. N. Mercator. Nicholas Mercator, sometimes known as Kaufmann, born in Holstein about 1620, but resided most of his life in England. He went to France in 1683, where he designed and constructed the fountains at Versailles, but when they were finished, Louis XIV refused to make him the payment agreed on unless he would turn Catholic. He died of vexation and poverty in Paris in 1687. He wrote a treatise on logarithms entitled Logarithmotechnia, published in 1668, and discovered the series log of 1 plus x equals x minus x squared over 2 plus x squared over 3 minus x to the power 4 over 4, and so on. He proved this by writing the equation of a hyperbola in the form of y equals 1 over 1 plus x, which would be equal to 1 minus x plus x squared minus x cubed plus, and so on, to which Wallace's formula, stated before, could be applied. The same series had been independently discovered by St. Vincent. Barrow. Isaac Barrow was born in London in 1630 and died at Cambridge in 1677. He went to school first at Charterhouse, where he was so troublesome that his father was heard to pray that if it pleased God to take any of his children, he could best spare Isaac, and subsequently to Felsted. He completed his education at Trinity College, Cambridge. After taking his degree in 1648, he was elected to a fellowship in 1649. He then resided for a few years in college, but in 1655 he was driven out by the persecution of the Independents. He spent the next 4 years in the east of Europe, and after many adventures returned to England in 1659. He was ordained the next year and appointed to the professorship of Greek at Cambridge. In 1662 he was made professor of geometry at Gresham College, and in 1663 was selected as the first occupier of the Lucasian chair at Cambridge. He resigned the latter to his pupil Newton in 1669, whose superior abilities he recognized and frankly acknowledged. For the remainder of his life he devoted himself to the study of divinity. He was appointed the master of Trinity College in 1672, and he held the post until his death. He is described as low in stature, lean and of a pale complexion, slovenly in dress, and an inveterate smoker. He was noted for his strength and courage, and once when travelling in the East he saved the ship by his own prowess from capture by pirates. A ready and caustic wit made him a favourite of Charles II, and induced the courtiers to respect even if they did not appreciate him. He wrote with a sustained and somewhat stately eloquence, and with his blameless life and scrupulous conscientiousness he was an impressive personage of the time. His earliest work was a complete edition of the Elements of Euclid, which he issued in 1655. He published an English translation in 1660 and in 1657 an edition of the Data. His lectures, delivered in 1664, 1665, and 1666, were published in 1683 under the title of Lectiones Mathematicae. These are mostly on the metaphysical basis for mathematical truths. His lectures for 1667 were published in the same year, and suggest the analysis by which Archimedes was led to his chief results. In 1669 he issued his Lectiones Opticae Geometricae. It is said in the preface that Newton revised and corrected these lectures, adding matter of his own, but it seems probable from Newton's remarks in the fluxional controversy that the additions were confined to the parts which dealt with optics. This, which is his most important work in mathematics, was republished with a few minor alterations in 1674. In 1675 he published an edition with numerous comments on the first four books of the Conics of Apollonius and of the extant works of Archimedes and Theodosius. In the optical lectures, many problems connected with the reflection and refraction of light are treated with great ingenuity. The geometrical focus of a point seen by a reflection or refraction is defined, and it is explained that the image of an object is the locus of the geometrical foci of every point on it. Barrow also worked out a few of the easier properties of thin lenses, and considerably simplified the Cartesian explanation of the rainbow. The geometrical lectures contain some new ways of determining the areas of the tangents of curves. The most celebrated of these is the method given for the determination of tangents to curves, and this is sufficiently important to require a detailed notice because it illustrates the way in which Barrow, Hood, and Sluys were working on the lines suggested by Fermat towards the methods of the differential calculus. Fermat had observed that the tangent at point P on a curve was determined if one other point besides P on it were known. Hence, if the length of the subtangent MT could be found, thus determining the point T, then the line TP would be the required tangent. Now Barrow remarked that if the abscissa and ordinate at a point Q adjacent to P were drawn, he got a small triangle PQR, which he called the differential triangle because its sides PR and PQ were the differences of the abscissa and ordinates of P and Q, so that TM to MP equals QR to RP. To find QR to RP, he supposed that XY were the coordinates of P, and x minus e, y minus a, those of Q. Barrow actually used P for x and M for y, but I alter these to agree with the modern practice. Substituting the coordinates of Q in the equation of the curve and neglecting the squares and higher powers of e and a as compared with their first powers, he obtained the ratio e to a. The ratio a over e was subsequently, in accordance with a suggestion made by Sluys, termed the angular coefficient of the tangent at the point. Barrow applied this method to the curves 1. X squared multiplied by the quantity x squared plus y squared equals r squared y squared. 2. X cubed plus y cubed equals r cubed. And 3. X cubed plus y cubed equals rxy, called Lagalande. 4. Y equals the quantity r minus x multiplied by the tangent of pi x divided by 2r, the quadratrix. And 5. Y equals r times tan pi x over 2r. It will be sufficient here if I take as an illustration the simpler case of the parabola y squared equals px. Using the notation given above, we have for the point P y squared equals px, and for the point Q y minus a quantity squared equals p multiplied by the quantity x minus e. Subtracting, we get 2ay minus a squared equals pe.
But if a be an infinitesimal quantity, a squared must be infinitely smaller and therefore may be neglected. Hence the ratio e to a equals the ratio 2y to p. Therefore Tm to y equals e to a equals 2y to p. That is, Tm equals 2y squared divided by p, which is equal to 2x. This is exactly the procedure of the differential calculus, except that we there have a rule by which we can get the ratio a over e or dy by dx directly without the labor of going through a calculation similar to the above for every separate case. Bruckner. William Viscount Bruckner, one of the founders of the Royal Society of London, born in 1620 and died on April 15, 1684, was among the most brilliant mathematicians of his time, and was in intimate relations with Wallis, Fermat, and other leading mathematicians. I mentioned on page 155 his curious reproduction of Brahmagupta's solution of a certain indeterminate equation. Bruckner proved that the area enclosed between the equilateral hyperbola xy equal 1 and the axis of x, and the ordinates x equals 1 and x equals 2 is equal either to 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus and so on, or to 1 minus 1 half plus 1/3 minus a quarter and so on. He also worked out similar expressions for different areas bounded by the hyperbola and straight lines. He wrote on the rectification of the parabola and of the cycloid. It is noticeable that he used infinite series to express quantities whose values he could not otherwise determine. In answer to a request of Wallis to attempt the quadrature of the circle, he shewed that the ratio of the area of the circle to the area of the circumscribed square, that is, the ratio of pi to 4, is equal to the ratio 1 over 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 and so on to 1. Continued fractions had been introduced by Cataldi in his treatise on finding the square roots of numbers published at Bologna in 1613, but he treated them as common fractions. Bruckner was the first writer who investigated or made any use of their properties. For further details see C. Hutton's Mathematical Dictionary. James Gregory. James Gregory, born at Drumoak near Aberdeen in 1638 and died in Edinburgh in October 1675, was successively professor at St Andrews and Edinburgh. In 1660 he publishes Optica Promota, in which the reflecting telescope known by his name is described. In 1667 he issued his Vera Circuli et Hyperbolae Quadratura, in which he showed the areas of the circle and hyperbola could be obtained in the form of infinite convergent series, and here, I believe for the first time, we find a distinction drawn between convergent and divergent series. This work contains a remarkable geometrical proposition to the effect that the ratio of the area of any arbitrary sector to that of the inscribed or circumscribed regular polygons is not expressible by a finite number of algebraical terms. Hence he inferred that the quadrature was impossible. This was accepted by Montucla, but it is not conclusive, for it is conceivable that some particular sector might be squared and this particular sector might be the whole circle. This book contains also the earliest enunciations of the expansions in the series of sine x, cosine of x, inverse sine of x, and inverse cosine of x. It was reprinted in 1668 with an appendix, Geometriae Pars, in which Gregory explained how the volumes of solids of revolution could be determined. In 1671, or perhaps earlier, he established the theorem that theta equals tan theta minus 1/3 tan cubed theta minus 1/5 tan to the 5th theta, and so on. the result being true only if theta lie between negative 1/4 pi and positive 1/4 pi. This is the theorem on which the work of most of the subsequent calculation of approximations to the numerical value of pi has been based. For further detail, see C. Hutton's Mathematical Dictionary. Wren. Sir Christopher Wren was born in Noyle in 1632 and died in London in 1723. Wren's reputation as a mathematician has been overshadowed by his fame as an architect, but he was Savilian Professor of Astronomy at Oxford from 1661 to 1673 and for some time President of the Royal Society. Together with Wallis and Huygens, he investigated the laws of collision of bodies. He also discovered the two systems of generating lines on the hyperboloid of one sheet, though it is probable that he confined his attention to the hyperboloid of revolution. Besides these, he communicated papers on the resistance of fluids and the motion of the pendulum. He was a friend of Newton, and like Huygens, Hooke, Halley, and others, had made attempts to shew that the force under which the planets move varies inversely as the square of the distance from the sun. Wallis, Bruckner, Wren, and Boyle, the last named being a chemist and physicist rather than a mathematician, were the leading philosophers who had founded the Royal Society of London. The society arose from the self-styled Indivisible College in London in 1645. Most of its members moved to Oxford during the Civil War, where Hooke, who was then an assistant in Boyle's laboratory, joined in their meetings. The society was formally constituted in London in 1660 and was incorporated on 15th of July 1662. Hooke. Robert Hooke, born at Freshwater on July 18, 1635 and died in London on March 3, 1703, was educated at Westminster and Christ Church, Oxford, and in 1665 he became professor of geometry at Gresham College, a post which he occupied till his death. He is still known by the law which he discovered that the tension exerted by a stretched string is, within certain limits, proportional to the extension, or as it is better stated, that the stress is proportional to the strain. He invented and discussed the conical pendulum, and was the first to state explicitly that the motions of the heavenly bodies were merely dynamical problems. He was as jealous as he was vain and irritable, and accused both Newton and Huygens of unfairly appropriating his results. Like Huygens, Wren, and Halley, he made efforts to find the law of force under which the planets move about the sun, and he believed the law to be that of the inverse square of the distance. He, like Huygens, discovered that the small oscillations of a coiled spiral spring were practically isochronous, and was thus led to recommend, possibly in 1658, the use of the balance spring in watches. He had a watch of this kind made in London in 1675. It was finished just 3 months later than the one made under the directions of Huygens in Paris. Collins. John Collins, born near Oxford on March 5, 1625, and died in London on November 10, 1683, was a man of great natural ability, but of slight education. Being devoted to mathematics, he spent his spare time in correspondence with the leading mathematicians of the time, for whom he was always ready to do anything in his power, and he has been described not inaptly as the English Mersenne. To him we are indebted for much information on the details of the discoveries of the period. Pell. Another mathematician who devoted considerable part of his time to making known the discoveries of others and to correspondence with leading mathematicians was John Pell. Pell was born at Sussex on March 1, 1610, and died in London on December 10, 1685. He was educated at Trinity College, Cambridge. He occupied in succession the mathematical chairs at Amsterdam and Breda. He then entered the English diplomatic service, but finally settled in 1661 in London,
where he spent the last 20 years of his life.
His chief works were an edition, with considerable new matter, of the Algebra by Brenker and Ronius, London 1668, and a table of square numbers, London 1672. For further details see my History of Mathematics at Cambridge. Sluys. René Francois Walter de Sluys, or Slusius, canon of Liege, born on July 7, 1622, and died on March 19, 1685, found for the subtangent of a curve fxy equals 0 an expression which is the equivalent to negative y multiplied by the partial derivative delta f by delta y divided by the partial derivative delta f by dx. He wrote numerous tracts, and in particular discussed at some length spirals and points of inflection. Tschirnhausen. Ehrenfried Walter von Tschirnhausen was born at Kislingswald on April 10, 1631, and died at Dresden on October 11, 1708. In 1682 he worked out the theory of caustics by reflection, or as they were usually called catacaustics, and shewed that they were rectifiable. This was the second case in which the envelope of a moving line was determined. He constructed the burning mirrors of great power. The transformation by which he removes certain intermediate terms from a given algebraical equation is well known. Romer. Olaf Romer was born at Aranus in September 25, 1644, and died in Copenhagen on September 19, 1710, and was the first to measure the velocity of light. This was done in 1675 by means of the eclipses of Jupiter's satellites. He brought the transit and mural circle into common use, the altazimuth having been previously generally employed, and it was on his recommendation that astronomical observations of stars were subsequently made in general on the meridian. He was also the first to introduce micrometers and reading microscopes into an observatory. He also deduced from the properties of epicycloids the form of the teeth in the toothed wheels best fitted to secure a uniform motion.
End of part 23. Chapter 16, Part 1 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by RousePaul. Chapter 16. The life and works of Newton. The mathematicians considered in the last chapter commenced the creation of those processes which distinguish modern mathematics. The extraordinary abilities of Newton enabled him within a few years to perfect the more elementary of these processes, and to distinctly advance every branch of mathematical science then studied, as well as to create some new subjects. Newton was the contemporary and friend of Wallis, Huygens, and others of those mentioned in the last chapter, but though most of his mathematical work was done in between the years 1665 and 1686, the bulk of it was not printed, at any rate in book form, till some years later. I propose to discuss the works of Newton somewhat more fully than those of other mathematicians, partly because of the intrinsic importance of his discoveries, and partly because this book is mainly intended for English readers, and the development of mathematics in Great Britain was for a century entirely in the hands of the Newtonian school. Isaac Newton was born in Lincolnshire, near Grantham, on December 25th, 1642, and died at Kensington, London, on March 20th, 1727. He was educated at Trinity College, Cambridge, and lived there from 1661 till 1696, during which time he produced the bulk of his work in mathematics. In 1696 he was appointed to a valuable government office, and moved to London, where he resided till his death. His father, who had died shortly before Newton was born, was a yeoman farmer, and it was intended that Newton should carry on the paternal farm. He was sent to school at Grantham, where his learning and mechanical proficiency excited some attention, and as one instance of his ingenuity I may mention that he constructed a clock worked by water, which kept very fair time. In 1656 he returned home to learn the business of a farmer under the guidance of an old family servant. Newton, however, spent most of his time studying problems, making experiments, or devising mechanical models. His mother, noticing this, sensibly resolved to find some more congenial occupation for him, and his uncle, having been himself educated at Trinity College, Cambridge, recommended that he should be sent there. In 1661 Newton accordingly entered as a subsidar at Trinity College, where for the first time he found himself among surroundings which were likely to develop his powers. He seems somewhat to have but little interest for the general society or for any pursuits save science and mathematics, and he complained to his friends that he found the other undergraduates disorderly. Luckily he kept a diary, and we can thus form a fair idea of the course of education of the most advanced students at an English university at that time. He had not read any mathematics before coming into residence, but was acquainted with Sanderson's logic, which was then frequently read as preliminary to mathematics. At the beginning of his first October term he happened to stroll down to Southridge Fair, and there picked up a book on astrology, but could not understand it on account of the geometry and trigonometry. He therefore bought a Euclid, and was surprised to find how obvious the prepositions seemed. He thereupon read Oughtred's Clavis and Descartes' Geometrie, and the latter of which he managed to master by himself, though at some difficulty. The interest he felt in the subject led him to take up mathematics rather than chemistry as serious study. His subsequent mathematical reading as an undergraduate was found on Kepler's Optics, the works of Vieta, Van Schooten's Miscellanies, and Descartes' Geometrie, and Wallace's Arithmetica Infinitorum. He also attended Barrow's lectures. At a later time, on reading Euclid more carefully, he formed a high opinion of it as an instrument of education, and he used to express his regret that he had not applied himself to geometry before proceeding to algebraic analysis. There is a manuscript of his dated May 28, 1665, written in the same year as that which he took his BA degree, which is the earliest documentary proof of his invention of fluxions. It was about the same time that he discovered the binomial theorem. On account of the plague, the college was shut down in the summer of 1665, and for a large part of the next year and a half Newton lived at home. This period was crowded with brilliant discoveries. He thought out the fundamental principles of his theory of gravitation, namely that every particle of matter attracts every other particle, and he suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. He also worked out the fluxional calculus tolerably completely. Thus, in a manuscript dated November 13, 1665, he used fluxions to find the tangent and the radius of curvature at any point on a curve, and in October 1666 he applied them to several problems in the theory of equations. Newton communicated these results to his friends and pupils from and after 1669, but they were not published in print till many years later. It was also while staying at home at this time that he devised some instruments for grinding lenses to particular forms other than spherical, and perhaps he decomposed solar light into different colours. Leaving out details and taking round numbers only, his reasoning at this time on the theory of gravitation seems to have been as follows. He suspected that the force which retained the moon in its orbit about the earth was the same as terrestrial gravity, and to verify this hypothesis he proceeded thus. He knew that if a stone were allowed to fall near the surface of the earth, the attraction of the earth, that is, the weight of the stone, caused it to move through 16 feet in 1 second. The moon's orbit relative to the earth is nearly a circle, and as a rough approximation, taking it to be so, he knew that the distance of the moon, and therefore the length of its path. He also knew the time the moon took to go once round it, namely a month. Hence he could easily find its velocity at any point such as m. He could therefore find the distance mt through which he would move in the next second if it were not pulled by the earth's attraction. At the end of that second it was however at m prime, and therefore the earth must have pulled it through the distance tm prime in 1 second, assuming the direction of the earth pull to be constant. Now he and several physicists of the time had conjectured from Kepler's third law that the attraction of the earth on a body would be found to decrease as the body was removed further away from the earth in a proportion inversely as the square of the distance from the centre of the earth. If this were the actual law, and gravity were the sole force which retained the moon in its orbit, then Tm prime should be to 16 feet in a proportion which inversely is the square of the distance of the moon from the centre of the earth to the square of the radius of the earth. In 1679, when he repeated the investigation, Tm prime was found to have the value which was required by the hypothesis, and the verification was complete, but in 1666 his estimate of the distance of the moon was inaccurate, and when he made the calculation he found that Tm prime was about 1/8 less than it ought to have been on his hypothesis. This discrepancy does not seem to have shaken his faith in the belief that gravity extended to the moon and varied inversely as the square of the distance, but from Whiston's notes of a conversation with Newton it would seem that Newton inferred that some other force, probably Descartes' vortices, acted on the moon as well as gravity. This statement is confirmed by Pemberton's account of the investigation. It seems, moreover, that Newton already believed firmly in the principle of universal gravitation, that is, every particle of matter attracts every other particle, and suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. But it is certain that he did not then know what the attraction of a spherical mass on any external point would be, and he did not think it likely that a particle would be attracted by the earth as if the latter were concentrated into a single particle at its centre. On his return to Cambridge in 1667, Newton was elected to a fellowship at his college, and permanently took up his residence there. In the early part of 1669, or perhaps in 1668, he revised Barrow's lectures for him. The end of lecture 14 is known to have been written by Newton, but how much of the rest is due to his suggestions cannot now be determined. As soon as this was finished, he was asked by Barrow and Collins to edit and add notes to a translation of Kinghuizen's Algebra, which he consented to do, but on condition that his name should not appear in the matter. In 1670 he also began a systematic exposition of his analysis by infinite series, the object of which was to express the ordinate of a curve in an infinite algebraical series, every term of which could be integrated by Wallace's rule. His results on the subject have been communicated to Barrow, Collins, and others in 1669. This was never finished. The fragment was published in 1711, but the substance of it had been printed as an appendix to the Optics in 1704. These works were only the first of Newton's leisure, most of the time during these 2 years being given up to optical researches. In October 1669 Barrow resigned the Lucasian chair in favour of Newton. During his tenure of the professorship it was Newton's practice to lecture publicly once a week, from half an hour to an hour at a time in one term of each year, probably dictating his lectures as rapidly as they could be taken down, and in the week following the lecture to devote 4 hours to appointments which he gave to students who wished to come to his rooms to discuss the results of the previous lecture. He never repeated a course, which usually consisted of 9 or 10 lectures, and generally the lectures of one course began from the point at which the preceding course had ended. The manuscripts of his lectures for 17 out of the first 18 years of his tenure are extant. When first appointed, Newton chose optics for the subject of his lectures and researches, and before the end of 1669 he had worked out the details of his discovery on the decomposition of a ray of white light into rays of different colours by means of a prism. The complete explanation of the theory of the rainbow followed from this discovery. These discoveries form the subject matter of the lectures which he delivered as Lucasian professor in the years 1669, 1670, and 1671. The chief new results were embodied in a paper communicated to the Royal Society in February 1672 and subsequently published in the Philosophical Transactions. The manuscript of his original lectures was printed in 1729 under the title Lectiones Opticae. This work is divided into 2 books, the first of which contains 4 sections and the second 5. The first section of the first book deals with the decomposition of solar light by a prism in consequence of the unequal refrangibility of the rays that compose it, and a description of his experiments is added. The second section contains an account of the method which Newton invented for the determining of the coefficients of refraction of different bodies. This is done by making a ray pass through a prism of the material so that the deviation is a minimum, and he proves that if the angle of the prism be I and the deviation of the ray be delta, then the refractive index will be the sine of 1/2 I plus delta multiplied by the cosecant half I. The third section is on refractions at plane surfaces. Here he shews that if a ray passed through a prism with minimum deviation, the angle of incidence is equal to the angle of emergence. Most of this section is devoted to geometrical solutions of different problems. The fourth section contains a discussion of refractions at curved surfaces. The second book treats of the theory of colours of the rainbow. By a curious chapter of accidents, Newton failed to correct the chromatic aberration of 2 colours by means of a couple of prisms. He therefore abandoned the hope of making a refracting telescope which should be achromatic, and instead designed a reflecting telescope, probably on the model of a small one which he had made in 1668. The form he used is that still known by his name. The idea of it was naturally suggested by Gregory's telescope. In 1672 he invented a reflecting microscope, and some years later he invented the sextant, which was rediscovered by Hadley in 1731. His professorial lectures from 1673 to 1683 were on algebra and the theory of equations, and are described below. But much of his time during these years was occupied with other investigations, and I may remark that throughout his life Newton must have devoted at least as much attention to the chemistry and theology as to mathematics, though his conclusions are not of sufficient interest to require mention here. His theory of colours and his deductions from his optical experiments were attacked with considerable vehemence by Paradis of France, Linus and Lucas at Liege, Hooke in England, and Huygens in Paris, but his opponents were finally refuted. The correspondence which this entailed on Newton occupied nearly all his leisure in the years 1672 to 1675 and proved extremely distasteful to him. Writing on December 9, 1675, he says, "I was so persecuted with discussions arising out of my theory of light that I blame my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow." Again, after November 18, 1676, he observes, "I see I have made myself a slave to philosophy, but, if I get rid of Mr. Linus's business, I will resolutely bid adieu to it eternally, excepting what I do for my private satisfaction or leave to come out after me. For I see a man must either resolve to put out nothing new, or to become a slave to defend it." The unreasonable dislike to have his conclusions doubted, or to be involved in any correspondence about them, was a prominent trait in Newton's character. He next set himself to examine the problem as to how light was really produced, and by the end of 1675 he had worked out the corpuscular or emission theory, a theory to which he was perhaps led by his researches on the theories of attraction. Only three ways have been suggested in which light can be produced mechanically. Either the eye may be supposed to send out something which, so to speak, feels the object, as the Greeks believed, or the object perceived may send out something which hits or affects the eye, as assumed in the emission theory. Or there may be some medium between the eye and the object may cause some change in the form or nature of this intervening medium and thus affect the eye, as Hooke and Huygens supposed in the wave or undulatory theory. It will be enough here to say that on either of the two latter theories all the obvious phenomena of geometrical optics, such as reflection, refraction, etc., can be accounted for. Within the present century crucial experiments have been devised which give different results according as one or the other theory is adopted. All these experiments agree with the results of the undulatory theory and differ from the results of the Newtonian theory. The latter is therefore untenable, but whether the former represents the whole truth and nothing but the truth is still an open question. Until, however, the theory of interference suggested by Young was worked out by Fresnel, the hypothesis of Huygens failed to account for all the facts, and was open to more questions than that of Newton. It should be noted that Newton nowhere expresses an opinion that the corpuscular theory is true, but always treats it as a hypothesis from which, if true, certain results would follow. It would moreover seem that he believed that the wave theory to be intrinsically more probable, and it was only the difficulty of explaining diffraction on that theory that led him to reject it. His remarks on the other physical subjects shew a similar caution. Newton's corpuscular theory was expounded in memoirs communicated to the Royal Society in December 1675, which are substantially reproduced in his Optics, published in 1704. In the latter work he dealt in detail with his theory of fits of easy reflection and transmission, and the colours of thin plates, to which he added an explanation of the colours of thick plates, and observations on the inflection of light. Two letters written by Newton in the year 1676 are sufficiently interesting to justify an allusion to them. Leibnitz, who had been in London in 1673, communicated some results to the Royal Society, which he had supposed to be new, but which it was pointed out to him had been previously proved by Mouton. This led to a correspondence with Oldenburg, the secretary of the Society. In 1674 Leibnitz wrote, saying that he possessed general analytical methods depending on the infinite series. Oldenburg in reply told him that Newton and Gregory had used such series in their work. In answer to a request for information, Newton wrote on June 13, 1676, giving a brief account of his method, but adding the expansions of a binomial, i.e. the binomial theorem, and of the arc sine of x, from the latter of which he deduced that of sine of x. This seems to be the earliest known instance of the reversion of a series. He also inserted an expression for the rectification of an elliptic arc in an infinite series. Leibniz wrote on August 27th asking for fuller details, and Newton, in a long but interesting reply dated October 24th, 1676, and sent through Oldenburg, gives an account of the way in which he had been led to some of his results. In this letter, Newton begins by saying that altogether he had used three methods for expansion in a series. His first was arrived at from the study of the method of interpolation by which Wallis had found expressions for the area of a circle and hyperbola. Thus, by considering the series of expressions 1 minus x squared quantity to the power 0 over 2, 1 minus x squared quantity to the power 2 over 2, and 1 minus x squared quantity to the 4 over 2, and so on, he deduced by interpolations the law which connects the successive coefficients in the expansions of 1 minus x squared to the power of a half, 1 minus x squared to the power of 3 halves, and so on, and then by analogy obtained the expression for the general term in the expansion of a binomial, i.e. the binomial theorem. He says that he proceeded to test this by forming the square of the expansion 1 minus x squared to the power of a half, which reduced to 1 minus x squared. And he proceeded in a similar way with other expansions. He next tested the theorem in the case of 1 minus x squared quantity to the power of 1 half by extracting the square root of 1 minus x squared, more arithmetico. He also used the series to determine the areas of the circle and the hyperbola in infinite series, and found that the results were the same as those he had arrived at by other means. Having established this result, he then discarded the method of interpolation in series and employed his binomial theorem to express, when possible, the ordinate of a curve in an infinite series in ascending powers of the abscissa, and thus, by Wallis's method, he obtained expressions in an infinite series for the areas and arcs of curves in the manner described in the appendix to his Optics and his De Analysi per Equationes Numero Terminorum Infinitorum. He states that he had employed his second method before the plague in 1665-66, and goes on to say that he was then obliged to leave Cambridge, and subsequently, i.e. presumably on his return to Cambridge, he ceased to pursue these ideas as he found that Nicholas Mercator had employed some of them in his Logarithmotechnica published in 1668, and he supposed that the remainder had been or would be found out before he himself was likely to publish his discoveries. Newton next explains that he had also a third method, of which, he says, he had about 1669 sent an account to Barrow and Collins, illustrated by applications to areas, rectification, cubature, and etc. This was the method of fluxions, but Newton gives no description of it here, though he adds some illustrations of its use. The first illustration is on the quadrature of the curve represented by the equation y equals ax to the power m multiplied by the quantity b plus cx to the power n quantity to the power p, which he says can be effected as a sum of quantity m plus 1 divided by n terms if quantity m plus 1 divided by m be a positive integer, and which he thinks cannot otherwise be affected except by an infinite series. He also gives a list of other forms which are immediately integrable, of which chief are x is raised to the power of m times n minus 1 multiplied by open bracket a plus bx to the power n plus cx to the power of 2n close bracket raised to the power of minus 1. Next, x to the power of open bracket m plus 1 half close bracket n minus 1 multiplied by open bracket a plus b x to the power of n plus c x to the power of 2n close bracket raised to the power of minus 1. The next term x to the power of m times n minus 1 multiplied by open bracket a plus b x to the power of n plus c x to the power of 2n close bracket raised to the power of plus or minus a half. Next term x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket plus or minus a half open bracket c plus dx to the power of n close bracket raised to the power of minus 1. Next term x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket raised to the power of 1 half multiplied by open bracket c plus dx to the power of n close bracket raised to the power of negative 1 half, where m is a positive integer and n is any number whatever. Lastly, he points out that the area of any curve can be easily determined approximately by the method of interpolation described below, in discussing his Methodus Differentialis. At the end of his letter, Newton alludes to the solution of the inverse problem of tangents, a subject on which Leibniz had asked for information. He gives formulae for reversing any series, but says that besides these formulae he has two methods for solving such questions, which for the present he will not describe except by an anagram, which being read is as follows: Une methodis consistent in extractione fluentis quantitatis ex equationes simul evolvente fluxionem ejus. Alteratantum in assumptione seriae pro quantitate qualibet incognitia ex qua cetera commodi derivare possunt, et in collagione terminorum homologorum equationis resultantis, ad eruendos terminos assumptae seriae. He implies in this letter that he is worried by the questions he has asked and the controversies raised about every new matter which he produces, which shew his rashness in publishing Quod ombrum captando e tennis perdiderum, quietam rem prosus substantialem. Leibniz did not reply to this letter till June 21st, 1677. In his answer he explains his method of drawing tangents to curves, which he says proceeds not by fluxions of lines but by the differences of numbers, and he introduces his notation of dx and dy for the infinitesimal differences between the coordinates of two consecutive points on a curve. He also gives a solution of the problem to find a curve whose subtangent is constant, which shews that he could integrate. In 1679, Hooke, at the request of the Royal Society, wrote to Newton expressing a hope that he would make further communications to the Society and informing him of various facts then recently discovered. Newton replied, saying that he had abandoned the study of philosophy, but he added that the earth's diurnal motion might be proved by the experiment of observing the deviation from the perpendicular of a stone dropped from a height to the ground, an experiment which was subsequently made by the Society and succeeded. Hooke, in his letter, mentioned Picard's geodetical researches. In these, Picard used a value of the radius of the earth which is substantially correct. This led Newton to repeat with Picard's data his calculations of 1666 on the lunar orbit, and he found the verification of his view was complete. He then proceeded to the general theory of motion under a centripetal force, and demonstrated 1. The equitable description of areas, 2. That if an ellipse were described about a focus under a centripetal force, then the law was that of the inverse square of the distance. 3. And conversely, that of the orbit of a particle projected under the influence of such a force was a conic, or it may be, he thought, only an ellipse. Obeying his rule to publish nothing which could land him in scientific controversy, these results were locked up in his notebooks, and it was only a specific question addressed to him 5 years later that led to their publication. The Universal Arithmetic, which is on algebra, theory of equations, and miscellaneous problems, contains the substance of Newton's lectures during the years 1673 to 1683. His manuscript of it is still extant. Whiston extracted somewhat reluctant permission from Newton to print it, and it was published in 1707. Amongst several new theorems on various points in algebra and the theory of equations, Newton here enunciated the following important results. He explained that the equations whose roots are the solution of a given problem will have as many roots as there are different possible cases, and he considered how it happened that the equation to which a problem led might contain roots which did not satisfy the original question. He extended Descartes' rule of signs to give limits to the number of imaginary roots. He used the principle of continuity to explain how two real and unequal roots might become imaginary in passing through equality, and illustrated this by geometrical considerations. Thence he shewed that imaginary roots must occur in pairs. Newton also here gave rules to find a superior limit to the positive roots of a numerical equation, and to determine the approximate values of the numerical roots. He further enunciated the theorem known by his name for finding the sum of the nth powers of the roots of an equation, and laid the foundation of the theory of symmetrical functions of the roots of an equation. The most interesting theorem contained in the work is his attempt to find a rule analogous to that of Descartes for real roots, by which the number of imaginary roots of an equation can be determined. He knew that the result which he obtained was not universally true, but he gave no proof and did not explain what were the exceptions to the rule. His theorem was as follows. Suppose the equation to be of the nth degree arranged in descending powers of x, the coefficient of x to the n being positive, and suppose the n plus 1 fractions 1, n over n plus 1 multiplied by 2 over 1, n minus 1 over n minus 2 multiplied by 3 over 2, and so on. And then the middle term of the series would be n minus p plus 1 all divided by n minus p, that fraction multiplied by p plus 1 over p, and so on. And the second last term being 2 over 1 multiplied by the fraction n over n minus 1, and finally the final term 1. To be formed and written below the corresponding terms of the equation, then, if the square of any term when multiplied by the corresponding fraction be greater than the product of the terms on each side of it, put a plus sign above it, otherwise put a minus sign above it, and put a plus sign above the first and last terms. Now consider any two consecutive terms in the original equation and the two symbols written above them. Then we may have any one of the four following cases. Alpha, the terms of the same sign and the symbols of the same sign. Beta, the terms of the same sign and the symbols of the opposite signs. Gamma, the terms of opposite signs and the symbols of the same sign. Delta, the terms of the opposite signs and the symbols of the opposite signs. Then it has been shewn that the number of negative roots will not exceed the number of cases alpha, and the number of positive roots will not exceed the number of cases gamma, and therefore the number of imaginary roots is not less than the number of cases beta and delta. In other words, the number of changes of signs in the row of symbols written above the equation is an inferior limit to the number of imaginary roots. Newton, however, asserted that you may also know how many roots are impossible by counting the changes of sign in the series of symbols formed as above. That is to say, he thought that in general the actual number of positive, negative, and imaginary roots could be got only by the rule, and not merely superior or inferior to the limits of these numbers. But though he knew that the rule was not universal, he could not find what were the exceptions to it. This theorem was subsequently discussed by Campbell, Maclaurin, Euler, and other writers. At last, in 1865, Sylvester succeeded in proving the general result. In August 1684, Halley came to Cambridge in order to consult Newton about the law of gravitation. Hooke, Huygens, Halley, and Wren had all conjectured that the force of the attraction of the sun or earth on an external particle varied inversely as the square of the distance. These writers seem to have independently shewn that if Kepler's conclusion were rigorously true, as to which they were not quite certain, the law of attraction must be that of the inverse square, but they could not deduce from the law of the orbits of the planets. Halley explained that their investigations were stopped by their inability to solve this problem, and asked Newton if he could find out what the orbit of a planet would be if the law of attraction were that of an inverse square. Newton immediately replied that it was an ellipse, and promised to send or write out afresh the demonstration of it which he had found in 1679. This was sent in November of 1684. End of section 24, chapter 16, part 1. Recording by Paul King, pjk.scripts.mit.edu/pkj. Chapter 16, Part 2 of A Short Account of the History of Mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A Short Account of the History of Mathematics by Rouse, Chapter 16, The Life and Works of Newton, Part 2. Instigated by Halley, Newton now returned to the problem of gravitation, and before the autumn of 1684 he had worked out the substance of propositions 1 through 19, 21, 30, 32 through 35 in the first book of the Principia. These, together with the notes on the laws of motion and various lemmas, were read for his lectures in the Michaelmas term 1684. In November, Halley received Newton's promised communication, which probably consisted of the substance of propositions 1, 11, and either 17 or corollaries 1 of 13, and thereupon he again went to Cambridge, where he saw a curious treatise, De Motu, drawn up since August. Most likely this contained Newton's manuscript notes of the lectures above alluded to. These notes are now in the university library and are headed De Motu Corporum. Halley begged that the results might be published, and finally secured a promise that they should be sent to the Royal Society. They were accordingly communicated to the Society not later than February 1685 in the paper De Motu, which contained the substance of the following propositions in the Principia, Book 1. Propositions 1, 4, 6, 7, 10, 11, 15, 17, 32, and Book 2, Propositions 2, 3, and 4. It seems also to have been due to the influence and tact of Halley at this visit in November 1684 that Newton undertook to attack the whole problem of gravitation and practically pledged himself to publish his results. As yet Newton had not determined the attraction of a spherical body on an external point, nor had he calculated the details of the planetary motions, even if the members of the solar system could be regarded as points. The first problem was solved in 1685, probably either in January or February.
No sooner, to quote from Dr. Galishier's address on the bicentenary of the publication of the Principia, had Newton proved the superb theorem, and we know from his own words that he had no expectation of so beautiful a result till it emerged from his mathematical investigation, that all the mechanism of the universe at once lay spread before him. When he discovered the theorems that from the first three sections of Book 1, when he gave them in his lectures of 1684, he was unaware that the sun and earth exerted their attractions as if they were but points. How different must these propositions have seemed to Newton's eyes when he realized that these results, which he had believed to be only approximately true when applied to the solar system, were really exact! Hitherto they had been only true in so far as he could regard the sun as a point compared to the distance of the planets, or the earth as a point compared to the distance of the moon, a distance amounting to only about 60 times the earth's radius, but now they were mathematically true, excepting only for the slight deviation from a perfectly spherical form of the sun, earth, and planets. We can imagine the effect of this sudden transition from approximation to exactitude in stimulating Newton's mind to still greater efforts. It was now in his power to apply the mathematical analysis with absolute precision to the actual problems of astronomy. Of the three fundamental principles applied in the Principia, we may say that the idea that every particle attracts every other particle in the universe was formed at least as early as 1666. The law of equable distribution of areas, its consequences, and the fact that if the law of attraction were that of the inverse square of the orbit of a particle about a centre of force, would be a conic, were proved in 1679, and lastly, the discovery that a sphere, whose density at any point depends only on the distance from the centre, attracts an external point as if the whole mass were collected at its centre, were made in 1685. It was this last discovery that enabled him to apply the first two principles to the phenomenon of bodies of finite size. The draft of the first book of the Principia was finished before the summer of 1685, but the corrections and additions took some time, and the book was not presented to the Royal Society until April 28, 1686. This book is given up to the consideration of the motion of particles or bodies in free space, either in known orbits, or under the action of known forces, or under their mutual attraction. In it, Newton generalizes the law of attraction into a statement that every particle of matter in the universe attracts every other particle with a force which varies directly as the product of their masses and inversely as the square of the distance between them, and he thence deduces the law of attraction for spherical shells of constant density. The book is prefaced by an introduction on the science of dynamics. The second book of the Principia was completed by the summer of 1686. This book treats of motion in a resting medium and of hydrostatics and hydrodynamics, with a special application to waves, tides, and acoustics. He concludes it by shewing that the Cartesian theory of vortices is inconsistent both with the known facts and with the laws of motion. The next 9 or 10 months were devoted to the third book. Probably for this he had originally no materials ready. In it, the theorems obtained in the first book are applied to the chief phenomenon of the solar system, the masses and distances of the planets, and, wherever sufficient data existed, of their satellites are determined. In particular, the motion of the moon, the various inequalities therein, and the theory of the tides are worked out in detail. He also investigates the theory of comets, shews that they belong to the solar system, explains how from 3 observations the orbit can be determined, and illustrates his results by considering certain special comets. The third book, as we have it, is but little more than a sketch of what Newton had finally proposed to himself to accomplish. His original scheme is among the Portsmouth Papers,
and his notes shew that he continued to work at it for some years after the publication of the first edition of the Principia. The most interesting of his memoranda are those in which by means of fluxions he has carried out his results beyond the point at which he was able to translate them into geometry. Footnote. I take this opportunity of saying that I hope shortly to publish a memoir on the history and compilation of the Principia. The following brief summary of the contents of the work will give the reader a general idea of its arrangement. The Principia is preceded by a preface in which Newton says that his object is to apply mathematics to the phenomena of nature. Among these phenomena, motion is one of the most important. Now, motion is the effect of force, and though he does not know what is the nature or origin of force, still many of its effects can be measured, and it is these that form the subject matter of the work. The work begins, therefore, naturally with an introduction on dynamics or the science of motion. This commences with the 8 definitions of the various terms, such as mass, momentum, and so on. Newton then lays down 3 laws of motion which are incapable of exact proof, but are confirmed partly by direct experiments, partly by the agreement with observation of the deductions from them. From these he deduces 6 fundamental principles of mechanics, and adds an appendix on the motion of falling bodies, projectiles, oscillations, impact, and the mutual attractions of 2 bodies. The most important deduction is that of the parallelogram of velocities, accelerations, and forces. The first book of the Principia is on the motion of bodies in free space and is divided into 14 sections. The first section consists of 11 preliminary lemmas treated by the method of prime and ultimate ratios, and not by that of indivisibles. The second section commences by shewing that if a body, such as a planet, revolve in an orbit subject to a force tending to a fixed point, such as the sun, the areas swept out by radii drawn from the body to the point are in one plane and are proportional to the times of describing them. And conversely, if the areas be proportional to the times, the force acting on the body must be directed to the point. Newton then shews how, if the orbit be known and the centre of force be given, the law of force can be determined, and he finds the law for various curves. In the third section he applies these propositions to a body which describes a conic section about a focus, and proves that the force must vary inversely as the square of the distance, and that Kepler's third law would necessarily be true of such a system. Conversely, he proves that if a body were projected in any way and subject to a central force which varied according to this law, then it must move in a conic section having the centre of force in a focus. He concludes proposition 17, corollaries 3 and 4, with a suggestion as to how the effects of distributing forces should be calculated. This was first done by the brilliant investigations of Laplace and Lagrange. And Laplace says that Lagrange's paper in the Berlin Memoirs for 1786, on which the modern treatment of the subject is founded, was suggested by these remarks of Newton. The fourth and fifth sections are devoted to the geometry of conic sections, especially to the construction of conics, which satisfy 5 conditions.
In section 4, one of the conditions is that the focus is given.
This includes the problem of finding the path of a comet from 3 observations which Newton says he found the most difficult problem of any which he had to solve. Curiously enough, he gave a second solution of the problem in Book 3, Proposition 41, in which he recommended as more simple but which is inapplicable in practice. The sixth section is devoted to determining what at any given time is the velocity and what is the position of a body which is describing a given conic about a centre of attraction in a focus, together with various converse problems. To effect this, Newton had to find the area of a sector of a conic. This is easily done for the parabola. He then endeavours to shew that the exact quadrature of any closed oval curve having no infinite branches, such as the ellipse, is impossible.
The proof is not correct as it stands, since the result is not true for ovals of the form
y to the power of 2m equals the quantity a to the power of 2n minus x to the power of 2n, all multiplied by 2 to the power of 2m times n to the power of 2m multiplied by x to the power of 2m times 2n minus 1.
where m and n are positive integers.
Newton seems himself to have felt some doubt about inserting it,
though he believed the result to be true. An exact quadrature being impossible, he proceeds to give three ways, two arithmetical and one geometrical, of approximating to the sectorial area of an ellipse as closely as is desired. The seventh section is given up to the discussion of motion in a straight line under a force which varies inversely as the square of the distance, and its comparison with the motion in a conic under the same force. He concludes by giving a general solution for all the problems considered in this section for any law of force. He here determines geometrically what is equivalent to finding the integral of x divided by the square root of the quantity ax minus x squared. The eighth section contains a general solutions for any orbit described under any central force of some of the problems previously considered. In proposition 40 he states that the kinetic energy acquired by a body in moving from one point to another is equal to the total work done by the force between those 2 points. In the ninth section he discusses the case where the orbit is in motion in its own plane round the center of force and treats in detail of the motion of the apse line and the forces by which a given motion would be produced. Newton applied this reasoning, proposition 45 corollary 2, to the case of the moon. But the resulting motion of the apses only came out about 1/2 of the actual amount. The approximation was in fact not carried to a sufficiently high order. Newton was aware of the discrepancy, and as he explained the similar difficulty in the case of the nodes it had been long suspected. Goldfray's Lunar Theory, 2nd edition, article 68, that the scholium of the first edition to book 3, proposition 35, meant that he had found the explanation. Nowhere in the Principia does he, however, give any hint as to how this was effected, and that the true explanation of a difference which had long formed an obstacle to the universal acceptance of the Newtonian system was first given by Clairaut in 1752. The Portsmouth papers contain Newton's original work and shew that he had obtained the true value by carrying the approximation to a sufficiently high order. It also seems clear from these papers that Newton gave the corollary to Book 1, proposition 45 as a mere illustration to the motion of the apses and orbits which are nearly circular, and did not mean it to apply to the moon, but by an inadvertence in the second and third editions a reference to it as an authenticity for a result connected with the moon was added which would naturally deceive any reader. Newton left most of the revision to the second edition to Cotes, and it is probable that the mistake is due to a blunder of the editor. Other questions connected with lunar and planetary irregularities are also discussed in this proposition, but the extreme conclusions of Newton misled all the early commentators, and even Laplace in his Système du Monde, published in 1796, speaks of Newton as having only roughly sketched out this part of the subject, leaving it to be completed when the calculus should be further perfected. But in the last volume of his Mécanique Céleste, published in 1825, he says that on more careful reading he has no hesitation in regarding it as among the most profound parts of the work. The 10th section is devoted to the consideration of motion of bodies along given surfaces, but not in planes passing through the center of force, with special reference to the vibration of pendulums and the determination of the accelerating effect of gravity. In connection with the latter problem, Newton investigates the chief geometrical properties of cycloids, epicycloids, and hypocycloids. In the 11th section, are considered the problems connected with motions in orbits where the center of force is disturbed, or where the moving body is disturbed by other forces. Until calculus of variations was invented by Lagrange in 1755, it was impossible to do more than sketch out the principles on which the problem should be solved, and Laplace in his Mécanique céleste was the first to work out most of the questions in any detail. Newton commences by considering the disturbance produced by the mutual action of two bodies revolving around one another. He then proceeds to consider the problem of three or more bodies which mutually attract one another. He first solves the question completely if the force of attraction varies directly as the distance. He next takes the case of the three bodies moving under their mutual attractions as in nature.
This problem has not been yet solved generally, but in Newton's day it was beyond any analysis of which he had the command. He contrived, however, to work out roughly the chief effects of the disturbing action of the sun on the motion of the moon, proposition 66. This proposition was singled out by Lagrange as the most striking single illustration of the genius of Newton.
To this proposition 22 corollaries are appended in which it is applied to determine the motion in longitude, in latitude, the annual equation, the motion of the apse line and of the nodes, the evection, the change in inclination of the plane of the lunar orbit, the precession of the equinoxes, and the theory of the tides. The greater part of the third book consists of the numerical application of these principles to the case of the moon and the earth. Lastly, Newton shewed how from the motion of the nodes of the interior constitution of the body could be roughly determined. Up to this point Newton had generally treated the bodies with which he dealt as if they were particles. He now proceeds in section 12 to consider the attraction of spherical masses which are either of uniform density or whose density at any point is a single valued function of the distance of the point from the center of the sphere. These are worked out for any law of attraction. In section 13 he gives some general theorems on the theory of attractions and on some propositions dealing with the attractions of solids of revolution. But these problems are almost insoluble without the aid of the infinitesimal calculus, and the Newtonian account of them is incomplete. The 14th section contains a statement of some theories and experiments in physical optics, and a solution by geometry of some problems in geometrical optics, particularly on the form of aplanatic refracting surfaces of revolution. The second book of the Principia is concerned with hydromechanics, and especially with motion in a resisting medium. These questions are not worked out so completely as those treated in the first book, and though this book provided the basis on which much of the subsequent work of Daniel Bernoulli, Clairaut, D'Alembert, Euler, and Laplace were erected, it is not of the same epoch-making character as the first book. This book is divided into 9 sections. The motion of bodies in a medium where the resistance varies directly as the velocity is considered in the first section. The motions where resistance varies as the square of the velocity is discussed in the second section. The motion where the resistance can be expressed as a sum of two terms, one of which varies as the velocity and the other as the square of the velocity, is dealt with in the third section. The second section contains proposition 25, a construction for the shape of the solid of least resistance. No proof is given, and it had been long somewhat of a mystery to know how Newton had contrived to solve the problem without the use of calculus of variations. Newton's demonstrations, there are 2 of them, have been recently discovered in the Portsmouth collection. The fourth section is devoted to a spiral motion in a resisting medium. The fifth to the theory of hydrostatics and elastic fluids. The sixth to the motion of pendulums in a resisting medium. The seventh to hydrodynamics, especially to the motion of projectiles in air and other fluids. The eighth to the theory of waves, including the principles from which the chief effects of the wave hypotheses in light and sound are calculated, and in particular the velocity of sound is determined. In the ninth section, Newton discusses the Cartesian theory of vortices. He begins by shewing that if there were no internal friction, the motion would be impossible. He must therefore assume some law of friction, and as a working hypothesis he supposes that the resistance arising from want of lubricity in the parts of a fluid is caetis paribus, proportional to the velocity of which the parts of the fluid are separated from each other. This hypothesis, as he himself remarks, is probably not altogether correct, but he thinks that it will give a general idea of the motion. He next proves that on this hypothesis that the motion would be unstable. He must therefore suppose that some constraining force prevents this catastrophe, and he then shews that in that case Kepler's third law could not be true. Lastly, he shews by independent reasoning that the hypothesis must lead to results which are inconsistent with Kepler's other two laws, and that both the vortices and the motion of the planets would necessarily be unstable. Several continental mathematicians made attempts to modify the Cartesian hypothesis so as to avoid these conclusions, but they could never explain one phenomenon without introducing fresh difficulties. It may be taken that by 1750 the Cartesian theory was finally abandoned. The third book is headed on the system of the world and is concerned chiefly with the application of the results of the first book to the solar system. It is introduced by certain rules of philosophizing and as a list of certain data obtained from astronomical observations. The rules are: 1. We may only assume as the possible causes of phenomenon such causes as are sufficient to explain them and are also verae causae. A verae causa being one which is capable of detection and such that its connection with the phenomenon can be ultimately shewn by independent evidence. 2. Effects of a similar kind must have similar causes. 3. Whatever properties of bodies are found by experience to be invariable should be assumed to be so in places where direct experiments cannot be made. Newton commences by illustrating the universality of the law of gravitation and sketches out the principles which lead him to think that the solar system is necessarily stable. He determines that the mass of the moon, the masses of the planets, their distances from the sun, and their figures. In the first edition he estimated, proposition 37, that the ratio of the mass of the moon to that of the earth was approximately that of 1 to 26. In the second and third editions this was altered to a ratio which is nearly that of 1 in 40. But except for the mass of the moon, he approximates to the results now known with astonishing closeness. He finds the disturbing force exerted by the sun and the moon, and considers the 5 chief irregularities in the orbit of the moon. He next discusses the solar and lunar tides, determines the precession of the equinoxes, and finally shews how the elements of a comet can be determined by these observations, and applies his results to certain comets. Before this time it had been commonly believed that the comets had nothing to do with the solar system, though in 1681 Dorfel had shewn that the path of the great comet of 1680 was a parabola having the sun at its focus. Lastly, the Principia is concluded by a general scholium containing the reflection on the constitution of the universe and on the eternal, the infinite, and perfect being by whom it is governed. The chief alterations in the second edition, published in 1713, were the substitutions of simpler proofs for some of the propositions in the second edition of the first book, a more full and accurate investigation found on some fresh experiments made by Newton about the year 1690, and the resistance of fluids in the 7th section of the second book, and the addition of a detailed examination of the causes of the precession of the equinoxes and the theory of comets in the third book. The chief alterations in the third edition, published in 1726, were in the scholium on fluxions,
and the addition of a new scholium on the motion of the moon's nodes, book 3, proposition 53. End of footnote. The demonstrations throughout the work are geometrical, but to readers of ordinary ability are rendered unnecessarily difficult by the absence of illustrations and explanations, and by the fact that no clue is given to the method by which Newton arrived at his results. The reason why it was presented in a geometrical form appears to have been that the infinitesimal calculus was then unknown,
and had Newton used it to determine the results which were in themselves opposed to the prevalent philosophy of the time, the controversy as to the truth of his results would have been hampered by a dispute concerning the validity of the methods used in proving them.
He therefore cast the whole reasoning into a geometrical shape, which, if somewhat longer, can at any rate be made intelligible to all mathematical students. So closely did he follow the lines of Greek geometry that he constantly used graphical methods and represented forces, velocities, and other magnitude in the Euclidean way, by straight lines, book 1 lemma 10, and not by certain number of units. The latter and modern method had been introduced by Wallis and must have been familiar to Newton. The effect of his confining himself rigorously to classical geometry is that the Principia is written in a language which is archaic even if not unfamiliar.
The adoption of geometrical methods in the Principia for purposes of demonstration does not indicate a preference on Newton's part for geometry over analysis as an instrument of research, for it is known now that Newton used the fluxional calculus in the first instance in finding some of the theorems, especially those towards the end of book 1. And in book 2, and in fact one of the most important uses of that calculus is stated in book 2 lemma 2. But it is only just to remark that at the time of its publication and for nearly a century afterwards, the differential and fluxional calculus were not fully developed and did not possess the same superiority over the method he adopted by which they do now. And it is a matter of astonishment that when Newton did employ the calculus, he was able to use it to so good an effect. The ability shewn in the translation in a few months of theorems so numerous and of so great complexity into the language of the geometry of Archimedes and Apollonius is, I suppose, unparalleled in the history of mathematics. The printing of the work was slow, and it was not finally published till the summer of 1687. The whole cost was borne by Halley, who also corrected the proofs and even put his own researches on one side to press the printing forward. The conciseness, absence of illustrations, and synthetical character of the book restricted the numbers of those who were able to appreciate its value, and though nearly all competent critics admitted the validity of the conclusions, some little time elapsed before it affected the current beliefs of educated men. I should be inclined to say, but on this point opinions differ widely, that within 10 years of its publication it was generally accepted in Britain as giving a correct account of the laws of the universe. It was similarly accepted within about 20 years on the continent, except in France, where the Cartesian hypothesis held its ground until Voltaire in 1738 took up the advocacy of the Newtonian theory. The manuscript of the Principia was finished by 1686. Newton devoted the remainder of that year to his paper on physical optics, the greater part of which is given up to the subject of diffraction. In 1687, James II, having tried to force the university to admit as a Master of Arts a Roman Catholic priest who refused to take oaths of supremacy and allegiance, Newton took a prominent part in resisting the illegal interference of the king and was one of the deputation sent to London to protect the rights of the university. The active part taken by Newton in this affair led to his being, in 1689, elected member for the university. This parliament only lasted 13 months, and on its dissolution he gave up his seat. He was subsequently returned in 1701, but he never took any prominent part in politics.
On his coming back to Cambridge in 1690, he resumed his mathematical studies and correspondence. If he lectured at this time, which is doubtful, it was on the subject matter of the Principia. The two letters to Wallis, which he explained his methods of fluxions and fluents, which were written in 1692 and published in 1693. Towards the close of 1692, and throughout the two following years, Newton had a long illness, suffering from insomnia and general nervous irritability. Perhaps he never quite regained his elasticity of mind, and though after his recovery he shewed the same power in solving any question propounded to him, he ceased thenceforward to do original work of his own initiative, and it was somewhat difficult to stir him to activity in new subjects.
In 1694 Newton began to collect data connected with the irregularities of the moon's motion, with the view of revising the part of the Principia which dealt with that subject.
To render the observations more accurate, he forwarded to Flamsteed a table of corrections for refraction which he had previously made. This was not published till 1721, when Halley communicated it to the Royal Society. The original calculations of Newton and the papers connected with it are in the Portsmouth collection, and shew that Newton obtained it by finding the path of a ray by means of quadratures in a manner equivalent to the solution of a differential equation. As an illustration of Newton's genius, I may mention that even as late as 1754 Euler failed to solve the same problem. In 1782 Laplace gave a rule for constructing such a table, and his results agree substantially with those of Newton. I do not suppose that Newton would in any case have produced much more original work after his illness, but his appointment in 1696 as warden and his promotion in 1699 to the mastership of the Mint at a salary of £1,500 a year brought his scientific investigations to an end, though it was only after this that many of his previous investigations were published in the form of books. In 1696 he moved to London. In 1701 he resigned the Lacazian chair, and in 1703 he was elected president of the Royal Society. End of section 25. Recording by Paul King, Oakville, Ontario. pjk.scripts.mit.edu/pkj.
Chapter 16, Part 3 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading is by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 16. The Life and Works of Newton, Part 3. In 1704 Newton published his Optics, which contains the results of papers already mentioned. The first edition of this book were appended to two minor works which have no special connection with optics, one being on cubic curves, the other on the quadrature of curves and on fluxions. Both of them were old manuscripts with which his friends and pupils were familiar, but they were here published urbi et orbi for the first time. The first of these appendices is entitled Ratio Linearum Tertii Ordinis. The object seems to be to illustrate the use of analytical geometry, and as the application to conics was well known, Newton selected the theory of cubics. He begins with some general theorems and classifies curves according as to whether their equations are algebraical or transcendental, the former being cut by a straight line in a number of points, real or imaginary, equal to the degree of the curve, the latter being cut by a straight line in an infinite number of points. Newton then shews that many of the most important properties of conics have their analogues in the theory of cubics, and he discusses the theory of asymptotes and curvilinear diameters. After these general theorems he commences his detailed examination of cubics by pointing out that a cubic must have at least one real point at infinity. If the asymptote or tangent at this point be a finite distance, it may be taken for the axis of y. This asymptote will cut the curve in 3 points altogether, of which at least 2 are at infinity. If the third point be a finite distance, then, by one of his general theorems on asymptotes, the equation can be written in the form of xy squared plus hy equals ax cubed plus bx squared plus cx plus d, where the axes of x and y are the asymptotes of the hyperbola, which is the locus of the middle points of all chords drawn parallel to the axis of y, while if on the third point in which this asymptote cuts the curve be also at infinity, the equation can be written in the form xy equals ax cubed plus bx squared plus cx plus d. Next, he takes the case where the tangent at the real point at infinity is not at a finite distance. A line parallel to the direction in which the curve goes to infinity may be taken as the axis of y. Any such line will cut the curve in 3 points altogether, of which one is by hypothesis at infinity and one is necessarily at a finite distance. He then shews that if the remaining point in which this line cuts the curve be at a finite distance, the equation can be written in the form y squared equals ax cubed plus bx squared plus cx plus d, while if it be at an infinite distance, the equation can be written in the form y equals ax cubed plus bx squared plus cx plus d. Any cubic is therefore reducible to one of the 4 characteristic forms. Each of these forms is then discussed in detail, and the possibility of the existence of double points, isolated ovals, etc. is worked out. The final result is that in all there are 78 possible forms which a cubic may take. Of these, Newton enumerated only 72. 4 of the remainder were mentioned by Stirling in 1717, and one by Nicole in 1731, and one by Nicholas Bernoulli at about the same time. In the course of the work, Newton states the remarkable theorem that just as the shadow of a circle cast by a luminous point on a plane gives rise to all the conics, so the shadows of the curves represented by the equation y squared equals ax cubed plus bx squared plus cx plus d give rise to all the cubics. This remained an unsolved puzzle until 1731, when Nicole and Clairaut gave demonstrations of it. A better proof is that given by Murdoch in 1740, which depends on the classification of these curves into 5 species according to as to whether their points of intersection with the axis of x are real and unequal, real and 2 of them equal, 2 cases, real and all equal, or finally 2 imaginary and 1 real. In this tract, Newton also discusses double points in the plane and at infinity, and the description of curves satisfying given conditions, and the graphical solution of problems by the use of curves. The second appendix to the Optics is entitled De Quadratura Curvarum. Most of it had been communicated to Barrow in 1668 or 1669, and probably was familiar to Newton's pupils and friends from that time onwards. It consists of 2 parts. The bulk of the first part is a statement of Newton's method of effecting the quadrature and the rectification of curves by means of infinite series. It is noticeable as containing the earliest use in print of literal indices and also the first printed statement of the binomial theorem. But these are introduced only incidentally. The main object is to give rules for developing a function of x in a series of ascending powers of x so as to enable mathematicians to effect the quadrature of any curve in which the ordinate y can be expressed as an explicit algebraical function of the abscissa x. Wallis had shewn how this quadrature could be found when y was given as a sum of a number of multiples of powers of x, and Newton's rules of expansion here established rendered possible the similar quadrature of any curve whose ordinate can be expressed as a sum of an infinite number of such terms. In this way he effects the quadrature of the curves y equals a squared divided by the quantity b plus x, y equals the square root of a squared plus or minus x squared, or y equals the square root of x minus x squared, or y equals the square root of 1 minus ax squared divided by the square root of 1 minus bx squared. But the results are of course expressed as infinite series. He then proceeds to curves whose ordinate is given as an implicit function of the abscissa, and he gives a method by which y can be expressed as an infinite series in ascending powers of x, but the application of the rule to any curve demands in general such complicated numerical calculations as to render it of little value. He concludes this part by shewing that the rectification of a curve can be effected in a somewhat similar way. His process is equivalent to finding the integral with regard to x of the square root of 1 plus y squared in the form of an infinite series. I should add that Newton indicates the importance of determining whether the series are convergent, an observation far in advance of his time, but he knew of no general test for the purpose, and in fact it was not until Gauss and Cauchy took up the question that the necessity of such limitations were commonly recognized. The part of the appendix which I have just described is practically the same as Newton's manuscript De Analysi per Equationes Numero Terminorum Infinitas, which was subsequently printed in 1711. It is said that this was originally intended to form an appendix to Kinckhuysen's Algebra. The substance of it was communicated to Barrow and by him to Collins in letters of July 31st and August 12, 1669, and a summary of part of it was included in a letter of October 24, 1676, sent to Leibniz. It should be read in connection with Newton's Methodus Differentialis published in 1736. Some additional theorems are there given, and he discusses his method of interpolation, which had been briefly described in the letter of October 24, 1676. The principle is this: if y equals phi of x be a function of x, and if when x is successively put equal to a1, a2, and so on, the values of y be known, and be b1, b2, and so on, then a parabola whose equation is y equals p plus qx plus rx squared plus so on can be drawn through the points a1, b1, a2, b2, and so on, and the ordinate of this parabola may be taken as an approximation to the ordinate of the curve. The degree of the parabola will of course be one less than the number of the given points. Newton points out that in this way the areas of any curves can be approximately determined. The second part of this appendix to the optics contained in a description of Newton's method is fluxions. This is best considered in connection with Newton's manuscript on the same subject, which was published by John Coulson in 1736, and of which it is a summary. The fluxional calculus is one form of the infinitesimal calculus expressed in a certain notation, just as the differential calculus is another aspect of the same calculus expressed in a different notation. Newton assumed that all geometrical magnitudes must be conceived as generated by continuous motion. Thus a line may be considered as generated by the motion of a point, a surface by that of a line, a solid by that of a surface, a plane angle by the rotation of a line, and so on. The quantity thus generated was defined by him as the fluent or flowing quantity. The velocity of the moving magnitude was defined as the fluxion of the fluent. This seems to be the earliest definite recognition of the idea of a continuous function, though it had been foreshadowed in some of Napier's papers. The following is a summary of Newton's treatment of fluxions. There are two kinds of problems. The object of the first is to find the fluxion of a given quantity, or more generally, the relation of the fluents being given, to find the relation of their fluxions. This is equivalent to differentiation. The object of the second or inverse method of fluxions is from the fluxion or some relations involving it to determine the fluent, or more generally an equation being proposed exhibiting the relation of the fluxions of quantities to find the relations of those quantities or fluents to one another. This is equivalent either to integration, which Newton termed the method of quadrature, or to the solution of a differential equation, which was called by Newton the inverse method of tangents. The methods for solving these problems are discussed at considerable length. Newton then went on to apply these results to questions connected with the maxima and minima of quantities, the method of drawing tangents to curves, and the curvature of curves, namely the determination of the center of curvature, the radius of curvature, and the rate at which the radius of curvature increases. He next considered the quadrature of curves and the rectification of curves. In finding the maximum and minimum of functions of one variable, we regard the change of sign of the difference between two consecutive values of the function as the true criterion. But his argument is that when a quantity increasing has attained its maximum, it can have no further increment, or when decreasing it has attained its minimum and can have no further decrement. Consequently, the fluxion must be equal to nothing. It has been remarked that neither Newton nor Leibniz produced a calculus, that is, a classified collection of rules, and that the problems they discussed were treated from first principles. That, no doubt, is the usual sequence in the history of such discoveries, though the fact is frequently forgotten by subsequent writers. In this case, I think the statement so far as Newton's treatment of the differential or fluxional part of the calculus is concerned is incorrect, as the foregoing account sufficiently shews. If a flowing quantity or fluent were represented by x, Newton denoted its fluxion by x dot, and the fluxions of x dot, or second function of x, by x dot dot, and so on. Similarly, the fluent of x was denoted by x written in a box, or sometimes by x prime, or x inside square brackets. The infinitely small part by which a fluent such as x increased in a small interval of time measured by omicron was called the moment of the fluent, and its value was shown to be x dot omicron. Newton adds the important remark that thus we may in any problem neglect the terms multiplied by the second and higher powers of omicron, and we can always find an equation between the coordinates of x, y of a point on a curve and their fluxions x dot, y dot. It is an application of this principle which constitutes one of the chief values of calculus. For if we desire to find the effect produced by several causes of a system, then if we can find the effect produced by each cause when acting alone in a very small time, the total effect produced in that time will be equal to the sum of the separate effects. I should here note the fact that Vince and other English writers in the 18th century used x dot to denote the increment of x and not the velocity with which it increased. That is, x dot in their writing stands for what Newton would have expressed by x dot omicron, and what Leibniz would have written as dx. I need not discuss in detail the manner in which Newton treated the problem above mentioned. I will only add that in spite of the form of his definition, the introduction into geometry of the idea of time was evaded by supposing that some quantity, e.g. the abscissa of a point on a curve, increased equably, and the required results then depend on the rate at which other quantities, e.g. the ordinate or the radius of curvature, increased relatively to the one so chosen. The fluent so chosen is what we now call the independent variable. Its fluxion was termed the principal fluxion, and of course if it were denoted by x, then x dot was constant and consequently x dot dot equaled 0. There is no question that Newton used the method of fluxions in 1666, and it is practically certain that accounts of it were communicated in manuscript to friends and pupils from and after 1669. The manuscript from which most of the above summary has been taken is believed to have been written between 1671 and 1677, and to have been in circulation at Cambridge from that time onward. It was unfortunate that it was not published at once. Strangers at a distance naturally judged of the method by the letter to Wallis in 1692 or by the Tractatus de Quadratura Curvarum, and were not aware that it had been so completely developed at an earlier date. This was the cause of numerous misunderstandings. At the same time it must be added that all mathematical analysis was leading up to the idea and methods of the infinitesimal calculus. Foreshadowings of the principles and even of the language of that calculus can be found in the writings of Napier, Kepler, Cavalieri, Pascal, Fermat, Wallis, and Barrow. It was Newton's good luck to come at a time when everything was ripe for the discovery, and his ability enabled him to construct almost at once a complete calculus. The notation of the fluxional calculus is for most purposes less convenient than that of the differential calculus. The latter was invented by Leibniz in 1675 and published in 1684, some 9 years before the earliest printed account of Newton's method of fluxions. But the question whether the general idea of the calculus expressed in that notation was obtained by Leibniz from Newton, or whether it was invented independently, gave rise to a long and bitter controversy. The leading facts are given in the next chapter. The question is one of considerable difficulty, but I will here only say that from what I have read of the voluminous literature on the question, I think on the whole it points to the fact that Leibniz obtained the idea of the differential calculus from a manuscript of Newton's which he saw in 1675. I believe, however, that the prevalent opinion is that the inventions were independent. The remaining events of Newton's life require little or no comment. In 1705 he was knighted. From this time onward he devoted much of his leisure to theology and wrote at great length on the prophecies and predictions, subjects which had always been of interest to him. His Universal Arithmetic was published by Whiston in 1707, and his Analysis by Infinite Series in 1711, but Newton had nothing to do with the preparation of either of these for the press. His evidence before the House of Commons in 1714 on the determination of longitude at sea marks an important epoch in the history of navigation. The dispute with Leibniz as to whether he had derived the ideas of the differential calculus from Newton or invented it independently originated about 1708 and occupied much of Newton's time, especially between the years 1709 and 1716. In 1709 Newton was persuaded to allow Cotes to prepare the long talked of second edition of the Principia. It was issued in March of 1713. A third edition was published in 1726 under the direction of Henry Pemberton. In 1725 Newton's health began to fail. He died on March 20th, 1727, and 8 days later was buried with great state in Westminster Abbey. His chief works, Taking them in their order of publication are the Principia, published in 1687, the Optics, with appendices on cubic curves, the quadrature and rectification of curves by use of the infinite series, and the Method of Fluxions, published in 1704, and the Universal Arithmetic, published in 1707, the Analysis per series, fluxions, etc., published in 1711, Lectiones Opticae, published in 1729, Method of Fluxions, etc., i.e. Newton's manuscript on fluxions, translated by J. Coulson and published in 1736, and the Methodus Differentialis, also published in 1736. In appearance Newton was short, and towards the close of his life rather stout, but well set, with a square lower jaw, brown eyes, and a very broad forehead, and a rather sharp features. His hair turned grey before he was 30, and remained thick and white and silver till his death. As to his manners, he dressed slovenly, was rather languid, and was often so absorbed in his own thoughts as to be anything but a lively companion. Many anecdotes of his extreme absence of mind when engaged in any investigation have been preserved. Thus, once when riding home from Grantham he dismounted to lead his horse up a steep hill. When he turned at the top to remount he found that he had the bridle in his hand while his horse had slipped it and gone away. Again, on the few occasions when he sacrificed his time to entertain his friends, if he left them to get more wine or for any similar reason, he would as often as not be found after the lapse of some time working out a problem, oblivious alike of his expectant guests and of his errand. He took no exercise, indulged in no amusements, and worked incessantly, often spending 18 or 19 hours out of the 24 in writing. In character he was religious and conscientious, with an exceptionally high standard of morality, having, as Bishop Brunet said, the whitest soul he ever knew. Newton was always perfectly straightforward and honest, but in his controversies with Leibniz, Hooke, and others, though scrupulously just, he was not generous, and it would seem that he had frequently took offence at a chance of expression when none was intended. He modestly attributed his discoveries largely to the admirable work done by his predecessors, and once explained that if he had seen farther than other men it was only because he stood on the shoulders of giants. He summed up his own estimate of his work in the sentence, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." He was morbidly sensitive to being involved in any discussions. I believe that with the exception of his papers on optics, every one of his works was published only under pressure from his friends and against his own wishes. There are several instances of his communicating papers and results on condition that his name should not be published. Thus, when in 1669 he had at Collier's request solved some problems on the harmonic series and on annuities which had previously baffled investigation, he only gave permission that his results should be published, "so it be," as he says, "without my name to it, for I see not what there is desirable in public esteem. Were I able to acquire and maintain it, it would perhaps increase my acquaintance, the thing which I chiefly study to decline." In intellect he has never been surpassed and probably never been equalled. Of this his extant works are the only proper test. Perhaps the most wonderful single illustration of his powers was the composition in 7 months of the first book of the Principia. As specific illustrations of his ability I may mention his solutions of the problems of Pappus, of John Bernoulli's challenge, and of the question of orthogonal trajectories. The problem of Pappus is to find the locus of a point such that the rectangle under its distances from two different straight lines shall be in a given ratio to the rectangle under its distances from two other given straight lines. Many geometricians from the time of Apollonius had tried to find a geometrical solution and had failed, but what had proved insuperable to his predecessor seemed to have presented little difficulty to Newton, who gave an elegant demonstration as that the locus was a conic. Geometry, said Lagrange, was, when recommending the study of analysis to his pupils, is a strong bow, but it is one which only a Newton could fully utilize. As another example I may mention that in 1696 John Bernoulli challenged mathematicians 1. To determine the brachistochrone, and 2. To find a curve such that if any line drawn from a fixed point O cut it in P and Q, then OP to the power n plus OQ to the power n would be a constant. Leibniz solved the first of these questions after an interval of rather more than 6 months, and then suggested that they should be sent as a challenge to Newton and others. Newton received the problems on January 29, 1697, and the next day gave the complete solutions of both, at the same time generalizing the second question. An almost exactly similar case occurred in 1716 when Newton was asked to find the orthogonal trajectory of a family of curves. In 5 hours Newton solved the problem in the form in which it was propounded to him, and laid down in the principles for finding trajectories. It is almost impossible to describe the effect of Newton's writings without being suspected of exaggeration. But if the state of mathematical knowledge in 1669 or at the death of Pascal or Fermat be compared with what was known in 1687, it will be seen how immense was the advance. In fact, we may say that it took mathematicians half a century or more before they were able to assimilate the work which Newton produced in those 20 years. In pure geometry, Newton did not establish any new methods, but no modern writer has shewn the same power in using those of classical geometry. In algebra and the theory of equations, he introduced the system of literal indices, established the binomial theorem, created no inconsiderable part of the theory of equations. One rule which he enunciated in this subject remained, till a few years ago, an unsolved riddle, which had overtaxed the resources of succeeding mathematicians. In analytical geometry he introduced the modern classification of curves into the algebraical and transcendental, and established many of the fundamental properties of asymptotes, multiple points, and isolated loops, illustrated by a discussion of cubic curves. The fluxional or infinitesimal calculus was invented by Newton in or before the year 1666, and circulated in manuscripts amongst his friends in and after the year 1669, though no account of the method was printed till 1693. The fact that the results are nowadays expressed in a different notation has led to Newton's investigations on this subject being somewhat overlooked. Newton further was the first to place dynamics on a satisfactory basis, and from dynamics he deduced the theory of statics. This was in the introduction to the Principia published in 1687. The theory of attractions, the application of the principles of mechanics to the solar system, the creation of physical astronomy, and the establishment of the law of universal gravitation are wholly due to him, and were first published in the same work. The particular questions connected with the motion of the earth and the moon were worked out as fully as was then possible. The theory of hydrodynamics was created in the second book of the Principia, and he added considerably to the theory of hydrostatics, which may be said to have been first discussed by Pascal. The theory of the propagation of waves, and in particular the application to determine the velocity of sound, is due to Newton and was published in 1687. In geometrical optics he explained amongst other things the decomposition of light and the theory of the rainbow. He invented the reflecting telescope, known by his name, and the sextant. In physical optics he suggested and elaborated the emission theory of light. The above list does not exhaust the subjects he investigated, but it will serve to illustrate how marked was his influence on the history of mathematics. On his writings and on their effects it will be enough to quote the remarks of two or three of those who were subsequently concerned with the subject matter of the Principia. Lagrange described the Principia as the greatest production of the human mind, and said that he felt dazed that such an illustration of what a man's intellect might be capable. In describing the effect of his own writings and those of Laplace, it was a favourite remark of his that Newton was not only the greatest genius that had ever existed, but he was also the most fortunate. For as there is but one universe, it can happen but to one man in the world's history to be the interpreter of its laws. Laplace, who is in general very sparing of his praise, makes of Newton the one exception, and the words in which he enumerates the causes which will always assure the Principia's a preeminence above all other productions of the human intellect have often been quoted. Not less remarkable is the homage rendered by Gauss. For other great mathematicians or philosophers he used the epithets Magnus or Clarus or Clarissimus. For Newton alone he kept the prefix summus. Finally, Biot, who had made a special study of Newton's works, sums up his remarks by saying, Comme géométrie et comme expérimentateur, Newton est sans égal. Par la réunion de ces deux genres de génie et leur plus haut degré, elle est sans exemple. End of section 26. Recording by Paul King, Oakville, Ontario. pjk.scripps.mit.edu/pkj.
Chapter 17 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripps.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 17. Leibniz and the mathematicians of the first half of the 18th century. Part 1. I have briefly traced in the last chapter the nature and extent of Newton's contributions to science. Modern analysis is however derived directly from the works of Leibniz and the elder Bernoullis, and it is immaterial to us whether the fundamental ideas of it were obtained by them from Newton or discovered independently. The English mathematicians of the years considered in this chapter continued to use the language and notation of Newton. They are thus somewhat distinct from their continental contemporaries, and I have therefore grouped them together in a section by themselves. Leibniz and the Bernoullis. Leibniz. Gottfried Wilhelm Leibniz was born at Leipzig on June 21st, 1646, and died at Hanover on November 14th, 1716. His father died before he was 6, and the teaching at the school to which he was then sent was inefficient, but his industry triumphed over all difficulties. By the time he was 12 he had taught himself to read Latin easily, and had begun Greek, and before he was 20 he had mastered the ordinary textbooks on mathematics, philosophy, theology, and law. Refused the degree of Doctor of Laws at Leipzig by those who were jealous of his youth and learning, he moved to Nuremberg. An essay which he there wrote on the study of law was dedicated to the Elector of Mainz and led to his appointment by the Elector on a commission for the revision of some statutes, from which he was subsequently promoted to the diplomatic service. In the latter capacity he supported unsuccessfully the claims of the German candidate for the crown of Poland. The violent seizure of various small places in Alsace in 1670 excited universal alarm in Germany as to the designs of Louis XIV, and Leibniz drew up a scheme by which it was proposed to offer German cooperation if France liked to take Egypt and use the possession of that country as a basis for attack against Holland in Asia, on the condition that Germany was to be left undisturbed by France. This bears a curious resemblance to the similar plan by which Napoleon I proposed to attack England. In 1672 Leibniz went to Paris on the invitation of the French government to explain the details of the scheme, but nothing came of it. At Paris he met Huygens, who was then residing there, and their conversation led him to study geometry, which he described as opening a new world to him, though he had as a matter of fact previously written some tracts on various minor points in mathematics, the most important of them being a paper on combinations written in 1668, and a description of a new calculating machine. In January 1673 he was sent on a political mission to London, where he stopped some months and made the acquaintance of Oldenburg, Collins, and others. It was at this time that he communicated the memoir to the Royal Society, in which he was found to have been forestalled by Mouton. In 1673 the Elector of Mainz died, and in the following year Leibniz entered the service of the Brunswick family. In 1676 he again visited London, and then moved to Hanover, where till his death he occupied the well-paid post of librarian in the Ducal Library. His pen was thenceforth employed in all the political matters which affected the Hanoverian family, and his services were recognized by honours and distinctions of various kinds. His memoranda on the various political, historical, and theological questions which concerned the dynasty during the 40 years from 1673 to 1713 form a valuable contribution to the history of that time. His appointment in the Hanoverian service gave him an increased leisure for his favourite pursuits. Leibniz used to assert that as the first fruit of his increased leisure he invented the differential and integral calculus in 1674, but the earliest traces of the use of it in his extant notebooks do not occur till 1675, and it was not till 1677 that we find it developed into a consistent system. It was not published until 1684. Nearly all his mathematical papers were produced within the 10 years, from 1682 to 1692, most of them in a journal called the Acta Eruditorum, which he and Otto Mencke founded in 1682, and which had a wide circulation on the continent. Leibniz occupies at least as large a place in the history of philosophy as he does in the history of mathematics. Most of his philosophical writings were composed in the last 20 or 25 years of his life, and the point as to whether his views were original or whether they were appropriated from Spinoza, whom he visited in 1676, is still in question among philosophers, though the evidence seems to point to the originality of Leibniz. As to Leibniz's system of philosophy, it will be enough to say that he regarded the ultimate elements of the universe as individual percipient beings who he called monads. According to him, the monads are centres of force, and substance is force, while space, matter, and motion are merely phenomenal. Finally, the existence of God is inferred from the existing harmony among the monads. His services to literature were almost as considerable as those to philosophy. In particular, I may single out his overthrow of the then prevalent belief that Hebrew was the primeval language of the entire human race. In 1700 the Academy of Berlin was created on his advice, and he drew up the first body of statutes for it. On the accession in 1714 of his master George I to the throne of England, Leibniz was practically thrown aside as a useless tool. He was forbidden to come to England, and the last 2 years of his life were spent in neglect and dishonour. He died at Hanover in 1716. He was over fond of money and personal distinctions, was unscrupulous, as might be expected of a professional diplomat of that time, but possessed singularly attractive manners, and all who once came under the charm of his personal presence remained sincerely attached to him. His mathematical reputation was largely augmented by the eminent position that he occupied in diplomacy, philosophy, and literature, and the power thence derived was considerably increased by his influence in the management of the Acta Eruditorum, which I believe was the only private scientific journal of the time. The last years of his life, from 1709 to 1716, were embittered by the long controversy with John Keill, Newton, and others as to whether he had discovered the differential calculus independently of Newton's previous investigations, or whether he had derived the fundamental idea from Newton and merely invented another notation for it. The controversy occupies a place in the scientific history of the early years of the 18th century, quite disproportionate to its true importance, but it so materially affected the history of mathematics in Western Europe that I feel obliged to give the leading facts, though I am reluctant to take up so much space with questions of a personal character. The case in favour of the independent invention by Leibniz is stated in Gerhardt's Leibnizissimus Mathematische Schriften in Biot and Lefort's edition of the Commercium Epistocolum, Paris, 1856. The arguments on the other side are given in H. Sloman's Leibnizens Anspruch auf die Erfindung der Differentialrechnung, Leipzig, 1857. Of which an English translation with the additions by Dr. Sloman was published at Cambridge in 1860. The history of the invention of the calculus is given in an article of it in the 9th edition of the Encyclopaedia Britannica, and in P. Manson's Esquisse de l'histoire de calcul infinitésimal, Gand, 1887. End of footnote. The ideas of the infinitesimal calculus can be expressed either in the notation of fluxions or in that of differentials. The former was used by Newton in 1666 and communicated in manuscript to his friends and pupils from 1669 onwards, but no distinct account of it was printed until 1693. The earliest use of the latter in the notebooks of Leibniz is dated 1675 and was employed in the letters sent to Newton in 1677, and an account of it was printed in the memoir of 1684 described below. There is no question that the differential notation is due to Leibniz, and that the sole question is as to whether the general idea of the calculus was taken from Newton or discovered independently. The case in favour of the independent invention by Leibniz rests on the ground that he published a description of his method some years before Newton printed anything on fluxions, that he always alluded to the discovery as being his own invention, and that for many years this statement was unchallenged. While of course there must be a strong presumption that he acted in good faith. To rebut this case it is necessary to shew that 1. He saw some of Newton's papers on the subject in or before 1675 or at least 1677, and 2. That he thence derived the fundamental ideas of the calculus. The fact that his claim was unchallenged for some years, in my opinion, in the particular circumstances of the case is immaterial. That Leibniz saw some of Newton's manuscripts was always intrinsically probable, but when, in 1849, C. J. Gerhardt examined Leibniz's papers, he found among them a manuscript copy, the existence of which had been previously unsuspected, in Leibniz's handwriting, of extracts from Newton's De analysi per equationes numero terminorum infinitas, which was printed in the De Quadratura Curvarum in 1704, together with notes on their expression in the differential notation. The question of the date at which these extracts were made is therefore all important. It is known that a copy of Newton's manuscript had been sent to Tschirnhausen in May 1675, and that in that year he and Leibniz were engaged together in a piece of work. It is not impossible that these extracts were made then. It is also possible that they may have been made in 1676. For Leibniz discussed the question of analysis by infinite series with Collins and Oldenburg in that year, and it is a priori probable that they would have then shewn him the manuscript of Newton on that subject, a copy of which was possessed by one or both of them. On the other hand, it may have been supposed that Leibniz made the extracts from the printed copy in or after 1704. Leibniz shortly before his death admitted in a letter to Conti that in 1676 Collins had shown him some Newtonian papers, but implied that they were of little or no value. Presumably he referred to Newton's letters of June 13th and October 24th, 1676, and to the letter of December 10th, 1672, on the method of tangents, extracts from which accompanied the letter of June 13th. But it was curious that, on the receipt of these letters, Leibniz should have made no further inquiries, unless he was already aware from other sources of the method followed by Newton. Whether Leibniz made no use of the manuscript from which he had copied extracts, or whether he had previously invented the calculus, are questions on which at this distance of time no direct evidence is available. It is, however, worth noting that the unpublished Portsmouth papers shew that when in 1711 Newton went carefully into the whole dispute, he picked out this manuscript as the one which had probably somehow fallen into the hands of Leibniz. At that time there was no direct evidence that Leibniz had seen this manuscript before it was printed in 1704, and accordingly Newton's conjecture was not published. But Gerhardt's discovery of the copy made by Leibniz tends to confirm the accuracy of Newton's judgment in the matter. It is said by some that to a man of Leibniz's ability the manuscript, especially if supplemented by the letter of December 10, 1672, would supply sufficient hints to give him a clue to the methods of the calculus, though as fluxional notation is not employed in it, anyone who used it would have to invent a notation, but this is denied by others. There was at first no reason to suspect the good faith of Leibniz, and it was not until the appearance in 1704 of an anonymous review of Newton's tract on quadrature, in which it was implied that Newton had borrowed the idea of the fluxional calculus from Leibniz, that any responsible mathematician questioned the statement that Leibniz had invented the calculus independently of Newton. It is universally admitted that there was no justification or authority for the statements made in this review, which was rightly attributed to Leibniz, but the subsequent discussion led to a critical examination of the whole question, and doubt was expressed as to whether Leibniz had not derived the fundamental idea from Newton. The case against Leibniz, as it appeared to Newton's friends, was summed up in the Commercium Epistolicolum issued in 1712. The evidence there collected may be inconclusive, but at any rate detailed references are given for all facts mentioned. No such summary with facts, dates, and references of the case for Leibniz was issued by his friends, but John Bernoulli attempted to indirectly weaken the evidence by attacking the personal character of Newton. This was in a letter dated June 7, 1713. The charges were false, and when pressed for an explanation of them, Bernoulli most solemnly denied having written the letter. In accepting the denial, Newton added in a private letter to him the following remarks, which are interesting as giving Newton's account of why he was last induced to take any part in the controversy. I have never, said he, grasped at the fame among foreign nations, but I am very desirous to preserve my character for honesty, for which the author of that epistle as if by the authority of a great judge, has endeavoured to wrest from me. Now that I am old, I have little pleasure in mathematical studies, and I have never tried to propagate my opinions over the world, but I have rather taken care not to involve myself in disputes on account of them. Leibniz's defense or explanation of his silence is given in the following letter, dated April 19, 1716, from him to Conti. Pour répondre de point à point à l'ouvrage publié contre moi, il falloit un autre ouvrage aussi grand pour le moi que celui-là. Il falloit entrer dans un grand détail des quantités de ministres passés il y a 30 et 40 ans, dont je ne me souviens guère. Il me falloit chercher mes vieilles lettres dont plusieurs se sont perdues. Outre que le plus souvent je n'ai point gardé les minutes miennes, et les autres sont salvés dans une grande tasse de papier que je ne prévois débrouiller qu'avec du temps et de la patience, mais je n'en avoir guère le loisir, étant chargé présentement d'occupations d'une toute autre nature. The death of Leibniz in 1716 only put a temporary stop to the controversy which was bitterly debated for many years later. The question is one of great difficulty. The evidence is conflicting and circumstantial, and everyone must form for themselves the opinion which seems most probable. I think the majority of modern writers would accept the view that probably Leibniz's invention of the calculus was independent of that of Newton, and everyone will hope that they are right. For myself, I cannot however but think it probable that Leibniz read Newton's manuscript De Analysi before 1677 and was materially assisted by it. His unacknowledged possession of a copy of part of one of Newton's manuscripts may be explicable, but the admitted fact that on more than one occasion he deliberately altered or added to important documents before publishing them seems to me to make his own testimony of little value. In mitigation of his conduct I can only say that it must be recollected that what he is alleged to have received was rather a series of hints than an account of the calculus, and it seems to me that the facts that he did not publish his results of 1677 until 1684, and that the notation and subsequent development of it were all of his own invention, may have led him 30 years later to minimize any assistance which he obtained originally and finally consider that it was immaterial. If we must confine ourselves to one system of notation, then there can be no doubt that that which was invented by Leibniz is better fitted for most of the purposes to which the infinitesimal calculus is applied than that of fluxions, and for some, such as the calculus of variations, it is indeed almost essential. It should be remembered, however, that at the beginning of the 18th century the methods of the infinitesimal calculus had not been systematized, and either notation was equally good. The development of that calculus was the main work of the mathematician of the first half of the 18th century. The differential form was adopted by continental mathematicians. The application of it by Euler, Lagrange, and Laplace to the principles of mechanics laid down in the Principia was the great achievement of the last half of that century, and finally demonstrated the superiority of the differential to the fluxional calculus. The translation of the Principia into the language of modern analysis and the filling in of the details of the Newtonian theory by the aid of that analysis were effected by Laplace. The controversy with Leibniz was regarded in England as an attempt by foreigners to defraud Newton of the credit of his invention, and the question was complicated on both sides by national jealousies. It was therefore natural, though it was unfortunate, that in England the geometrical and fluxional methods as used by Newton were alone studied and employed. For more than a century the English school was thus out of touch with continental mathematicians. The consequence was that, in spite of the brilliant band of scholars formed by Newton, the improvements in the methods of analysis gradually effected on the continent were almost unknown in Britain. It was not until 1820 that the value of analytical methods was fully recognized in England, and that Newton's countrymen again took any large share in the development of mathematics. Leaving now this long controversy, I come to the discussion of the mathematical papers produced by Leibniz, all the more important of which were published in the Acta Eruditorum. They are mainly concerned with the applications of the infinitesimal calculus and with various questions on mechanics. The only papers of first-rate importance which he produced are those on the differential calculus. The earliest of these was one published in the Acta Eruditorum for October 1684, in which he enunciated a general method for finding maxima and minima, and for drawing tangents to curves. One inverse problem, namely to find the curve whose subtangent is constant, was also discussed. The notation is the same as that with which we are familiar, and the differential coefficients of x to the power n and of products and quotients are determined. In 1686 he wrote a paper on the principles of the new calculus. In both of these papers the principle of continuity is explicitly assumed, while his treatment of the subject is based on the use of infinitesimals and not on that of the limiting value of ratios. In answer to some objections which were raised in 1694 by Bernard Nieuwentyt, who asserted that dy by dx stood for an unmeaning quantity like 0 over 0, Leibniz explained, in the same way as Barrow had previously done, that the value of dy by dx in geometry could be expressed as the ratio of two finite quantities. I think Leibniz's statement of the objects and methods of the infinitesimal calculus as contained in these papers, which are the three most important memoirs on it that he had produced, is somewhat obscure, and his attempt to place the subject on a metaphysical basis did not tend to clearness. But the notation he introduced is superior to that of Newton, and the fact that all the results of modern mathematics are expressed in the language invented by Leibniz has proved to be the best monument of his work. In 1686 and 1692 he wrote papers on osculating curves. These, however, contained some bad blunders, as for example the assertion that an osculating circle will necessarily cut a curve in 4 consecutive points. This error was pointed out by John Bernoulli, but in his article of 1692 Leibniz defended his original assertion and insisted that a circle could never cross a curve where it touched it. In 1692 Leibniz wrote a memoir in which he laid the foundation of the theory of envelopes. This was further developed in another paper in 1694 in which he introduced for the first time the terms coordinates and axes of coordinates. Leibniz also published a good many papers on mechanical subjects, but some of them contain mistakes which shew that he did not understand the principles of the subject. Thus, in 1685 he wrote a memoir to find the pressure exerted by a sphere of weight W placed between two inclined planes of complementary inclinations, placed so that the lines of the greatest slope are perpendicular to the line of the intersection of the planes. He asserted that the pressure on each plane must consist of two components, unum quo decliviter descendere tensit, alterum quo planum declive premit. He further said that for metaphysical reasons that the sum of the two pressures must be equal to W. Hence, if r and r prime be the required pressures and alpha and 1/2 prime minus alpha the inclination of the planes, he finds that r minus 1/2 W multiplied by the quantity 1 minus sine alpha plus cos alpha and r prime equals 1/2 W multiplied by 1 minus cos alpha plus sine alpha. The true values are r equals W cos alpha and r prime equals W sine alpha. Nevertheless, some of his papers on mechanics are valuable. Of these, the most important were two.
in 1689 and 1694, in which he solved the problem of finding an isochronous curve, one in 1697 on the curve of quickest descent. This was the problem sent as a challenge to Newton, and two in 1691 and 1692, in which he stated the intrinsic equation of the curve assumed by a flexible rope suspended from 2 points, i.e. the catenary, but gave no proof. This last problem had been originally proposed by Galileo. In 1689, that is 2 years after the Principia has been published, he wrote on the movements of the planets, which he stated were produced by a motion of the ether. Not only were the equations of motion which he obtained wrong, but his deductions from them were not even in accordance with his own axioms. In another memoir in 1706, that is nearly 20 years after the Principia had been written, he admitted that he had made some mistakes in his former paper, but adhered to his previous conclusions, and summed the matter up by saying, "It is certain that gravitation generates a new force at each instant to the centre, but the centrifugal force also generates another away from the centre. The centrifugal force may be considered in two aspects according as the movement is treated as along the tangent to the curve or as along the arc of the circle itself." It seems clear from this paper that he did not really understand the manner in which Newton had reduced the dynamics to an exact science. It is hardly necessary to consider his work on dynamics in further detail. Much of it is vitiated by a constant confusion between momentum and kinetic energy. When the force is passive, he uses the first, which he calls his vis mortua, as the measure of force. When the force is active, he uses the latter, the double of which he calls the vis viva. The series quoted by Leibniz comprise those of e to the x and log of 1 plus x, sine of x, versine of x, and the arctangent of x. All of these have been previously published, and he rarely, if ever, added any demonstrations. Leibniz, like Newton, recognized the importance of James Gregory's remarks on the necessity of examining whether infinite series are convergent or divergent, and proposed a test to distinguish the series whose terms are alternatively positive and negative. In 1693, he explained the method of expansion by indeterminate coefficients, though his applications were not free from error. To sum the matter up briefly, it seems to me that Leibniz's work exhibits great skill in analysis, but much of it is unfinished, and when he leaves his symbols and attempts to interpret his results, he frequently commits blunders. No doubt the demands of politics, philosophy, and literature on his time may have prevented him from elaborating any scientific subject completely, or writing any systematic exposition of his views, though they are no excuse for the mistakes of principle which occur so frequently in his papers. Some of his memoirs contain suggestions of methods which have now become valuable means of analysis, such as the use of determinants and of indeterminate coefficients. But when a writer of manifold interests like Leibniz throws out innumerable suggestions, some of them are likely to turn out valuable, and to enumerate these, which he never worked out, without reckoning the others, which are wrong, gives a false impression of the value of his work. But in spite of this, his title to fame rests on a sure basis, for it was he who brought the differential calculus into general use, and his name is inseparably connected with one of the chief instruments of analysis, just as that of Descartes, another philosopher, is with analytical geometry. Leibniz was only one amongst several continental writers whose papers in the Acta Eruditorum familiarized mathematicians with the use of differential calculus. The most important of these were James and John Bernoulli, both of whom were farm friends and admirers of Leibniz, and to their devoted advocacy his reputation is largely due. Not only did they take a prominent part in nearly every mathematical question they discussed, but nearly all the leading mathematicians on the continent for the first half of the 18th century came directly or indirectly under the influence of one or both of them. The Bernoullis were a family of Dutch origin who were driven from Holland by the Spanish persecutions and finally settled at Bâle in Switzerland. The first member of the family who attained any marked distinction in mathematics was James. James Bernoulli. Jacob or James Bernoulli was born at Bale on December 27, 1654. In 1687 he was appointed to a chair of mathematics in the university there and occupied it until his death on August 16, 1705. He was one of the earliest to realize how powerful as an instrument of analysis was the infinitesimal calculus, and he applied it to several problems. But he did not himself invent any new processes. His great influence was uniformly and successfully exerted in favor of the use of differential calculus, and his lessons on it, which were written in the form of 2 essays in 1691 and are published in volume 2 of his works, shew how completely he had even then grasped the principles of the new analysis. These lectures, which contain the earliest use of the term integral, were the first published attempt to construct an integral calculus, for Leibniz had treated each problem by itself and had not laid down any general rules on the subject. The most important discoveries of James Bernoulli were his solution of the problem to find an isochronous curve. His proof that the construction for the catenary which had been given by Leibniz was correct, and his extension of this to strings of variable density under a central force, his determination of the form had taken by an elastic rod fixed at one end and acted on by a given force in the other, the elastica, also of a flexible rectangular sheet with 2 sides fixed horizontally and filled with a heavy liquid, the lentiaria, and lastly of a sail filled with wind, the velaria. In 1696 he offered a reward for the general solution of isoperimetrical figures, i.e. the determination of a figure of a given species which should include a maximum area, its perimeter being given. His own solution, published in 1701, is correct as far as it goes. In 1698 he published an essay on the differential calculus and its applications to geometry. He here investigated the chief properties of the equiangular spiral, and especially noticed the manner in which the various curves deduced from it reproduced the original curve. Struck by this fact, he begged that, in imitation of Archimedes, an equiangular spiral should be engraved on his tombstone with the inscription Eadem numero mutata resurgo. He also brought out in 1695 an edition of Descartes' Géométrie. In his Ars Conjectandi, published in 1713, he established the fundamental principles of the calculus of probabilities. In the course of the work he defined the numbers known by his name and explained their use, and he also gave some theorems on finite differences. His higher lectures were mostly on the theory of series. These were published by Nicholas Bernoulli in 1713. John Bernoulli. Johann Bernoulli, the brother of James Bernoulli, was born at Bale on August 7, 1667, and died there on January 1, 1748. He occupied the chair of mathematics at Groningen from 1695 to 1705, and at Bale, where he succeeded his brother from 1705 to 1748. To all who did not acknowledge his merits in a manner commensurate with his own view of their importance, he behaved most unjustly. As an illustration of his character, it may be mentioned that he attempted to substitute for an incorrect solution of his own on isoperimetrical curves another stolen from his brother James, while he expelled his son Daniel from his house for obtaining a prize from the French Academy which he had expected to receive himself. After the deaths of Leibniz and L'Hopital, he claimed the merit of some of their discoveries. These claims are now known to be false. He was, however, the most successful teacher of his age, and had the faculty of inspiring his pupils with almost as passionate a zeal for mathematics as he felt for himself. The general adoption on the continent of the differential rather than the fluxional notation was largely due to his influence. Leaving out of account
his innumerable controversies, the chief discoveries of John Bernoulli were the exponential calculus, the treatment of trigonometry as a branch of analysis, the conditions for a geodesic, the determination of orthogonal trajectories, the solution of the brachistochrone, and the statement that a ray of light traversed such a path that sigma mu ds was a minimum, and the enunciation of the principle of virtual work. I believe that he was the first to denote the accelerating effect of gravity by an algebraical sign g, and he thus arrived at the formula v squared equals 2gh. The same result would have been previously expressed by the proportion v1 squared is to v2 squared as h1 is to h2. The notation phi x to indicate a function of x was introduced by him in 1718 and displaced the notation chi or xi proposed by him in 1698, but the general adoption of symbols like little f, big F, phi, and psi to represent functions seemed to be mainly due to Euler and Lagrange. Several members of the same family but of a younger generation enriched mathematics by their teachings and writings. The most important of these were the three sons of John, namely Nicholas, Daniel, and John the Younger, and the two sons of John the Younger who bore the names of John and James. To make the account complete, I add here their respective dates. Nicholas Bernoulli, the eldest of the three sons of John, was born on January 27, 1695, and was drowned at St. Petersburg, where he was professor, on July 26, 1726. Daniel Bernoulli, the second son of John, was born on February 9, 1700, and died on March 17, 1782. He was professor first at St. Petersburg and afterwards at Bâle, and shares with Euler the unique distinction of having gained the prize proposed annually by the French Academy no less than 10 times. I refer to him again a few pages later. John Bernoulli the Younger, a brother of Nicholas and Daniel, was born on May 18, 1710, and died in 1790. He was also a professor at Bâle. He left two sons, John and James. Of these, the former, who was born on December 4, 1744, and died on July 10, 1807, was Astronomer Royal and Director of Mathematical Studies at Berlin, while the latter, who was born on October 17, 1759, and died in July 1789, was successively professor at Bâle, Verona, and St. Petersburg. End of section 27. Recording by Paul King. Oakville, Ontario. pjk.scripts.mit.edu/pkj